a talk in this esteemed with esteemed the colleagues who are working very actively in their research work, and I am not very much actively involved in research nowadays. But anyway, he persuaded me to give a lecture. So I acceded to his request, and then I of course thank him for all the efforts he has done. And at the same time, I also express my sincere thanks to all those involved, so-called hidden force, who make this type of programs a success. Having said that, then when I was talking to Dr. Tiwari, then I thought that I should make the topic a bit attractive in the sense that it should motivate the students for choosing their career, whether they become entrepreneur later on or whether they become the researchers in academics or anywhere. So attractive in this sense, and lucrative in the sense that I thought that I should add automotive sector here, because automotive sector is the most lucrative sectors in India nowadays, and it is one of the sectors which is contributing to maximum, economic growth of the country. And moreover, we are talking of this driverless car, autonomous driving, and electric driving, and all that. And whatever advantage, the advancement have taken place in this particular field of automotive sector is because of the basic research that is going on in this direction. So I selected the talk as new technologies for paradigm shift in automotive sector. So I will be talking basically on these three things. And if time permits, then I will be, of course, talking about SPDC, which is called spontaneous parametric time conversion. And this was the experiments which I had been doing at NPL before superannuation. So I would be talking about metamaterials because it is one of the very short topic these days, very prominent topic these days. It has got many advantages, and you will see in the next slides how advantageous these materials are nowadays. And when I was in NPL, then I with Dr. Budhani, Professor Budhani, who was the then director there, we started some work on metamaterials, and there is a fellow, Dr. Sudhir Hosale, he is working on these materials at NPL. Well, in plasmonics, I worked on some theoretical things, but I will cite some of the examples, experiments which have been done in this direction of plasmonics. And then finally, I will come to laser lighting. And this was the topic which we are pursuing right now with the National Physical Laboratory. The idea is to produce very high intensity sources where we can have the intensity in several lakh candelas, so that the propagation of the light goes up to something like 1,000 meters, 1 kilometer. Because of the high speed of cars and all that, it is necessary that the driver should be able to see at large distances. So having said that, now I come to the main topic. Metamaterials, the word meta is the Greek word. Meta means either superior or beyond. It means that these materials which are man-made materials, these are man-engineered materials. So these have got many superior properties. So that's why they have been given the name meta, or this is beyond materials. That's why they are called metamaterials. And these are periodic materials. They derive their properties from structure rather than components. For example, in superconductors, the material is important, but in this case, the structure is important rather than the components. And they are designed to achieve advantageous and unusual electromagnetic properties, which you will come to know in the next slides. The biggest advantage is through tunable dielectric property, which is one of the properties, for designing flexible materials. And how this flexibility is achieved and how much has been achieved and what is the advantage of this flexibility, I will discuss with some of the examples, of some of the cars which have been designed. And these, of course, will provide optical properties in the length scales, where below wavelength of light, so wavelength of light is in between 380 nanometers to 780 nanometers. So we can go well below those wavelengths, So this is the so this now I will come to this, because these metamaterials have got one of the unique property, which is called negative index of refraction. You know that optical devices, lenses, and displays, they work on the phenomena of refraction. And refraction, everybody knows that it is the ratio of the speed of light in vacuum to that of material. But in most of the cases in lenses, that usually those are available, lenses, prisms, and all that, the index of refraction is positive. And the on the other hand, metamaterials are negative index materials, and one can see on the right side of this slide. Is this slide visible, or this is making a difference because the names are coming here in my this thing?
No, it's visible.
You are look. This is visible, na? There is no
Yes, sir.
problem
Yes.
in this thing in the slides, right?
No, it's perfect.
So negative index materials, on the right side of this slide, you can see where this can be shown to students in a simple way, that whenever there is a positive refractive index medium like water, if it is filled with, a glass is filled with water, at the interface, when a glass rod is put, it bends at the interface, and bending is towards the direction of the rod, which is inserted inside the glass. On the other hand, in the case of negative index material, the bending will be towards the rod. And that is the property of negative refractive index. And such type of medium are called negative refractive index medium. This is possible because of the research done for several years, and the materials have got unique properties, that the permittivity, the permeability, that is permittivity epsilon, the electrical, the flux penetrating a medium, and that magnetic flux permeability, and these are negative. As a result of that, the refractive index becomes also negative. So that is the beauty of these materials, that they are negative index, refractive index material, because of the permittivity and permeability being negative in that. And what happens that it has been a question that whether such type of properties will violate the rules of physics, but no, none. For example, n1 sine theta 1 will be equal to n2 sine theta 2. That holds. The energy conservation holds. Only the thing which is very important in this case is that the right-hand rule, this E cross H, which shows the direction of pointing vector where the energy flow takes place. In the case of positive material, the wave vector, wave propagating vector K, and pointing vector will be directing in the same direction. On the other hand, in this case of refractive index material, the wave propagating vector will be in the backward direction, in the reverse direction of the pointing vector. That is the biggest achievement which is obtained as a result of the negative refractive index material. So in this case, actually, there was a long history. In 1968, the concept was on NIM was given by Vesilago, but this subject was almost neglected for over 30 years. And 30 years means somewhere in 1998, or rather in 1999, John Penry, who was given this knighthood later on, now he is addressed as Sir John Penry. he gave seminal paper in 1999, which gave breakthrough this technology. And one of the papers, very lucrative paper, very seminal paper, which I read, was on cloaking. And here is something wrong. In 2025, by Smith, the applications were shown. And for example, in cloaking and light manipulation. And what will be the striking advantage of these materials are that we can have, since we have that thing to play with us is the permittivity and permeability in mind. Therefore, we can have wider set of reflective indices in nature, and nature offers that because these are man-engineered materials. So we can do this thing. As I told you that we can also manipulate the dielectric properties in order to achieve flow, in order to achieve flexibility. So therefore, it opens the doors for new technological possibilities. And since they have got typical electromagnetic properties, so we can increase the bandwidth. We can have a wide range of frequencies, including the bandwidth, and also now the research is going on to make it possible in the visual part of the electromagnetic spectrum, which is called light. That is from 380 nanometers to 780 nanometers. Most of the work has been confined to infrared and microwave and all that. But recently, these are being done in this thing. And one of the sectors which is most being benefited by this type of research is automotive sector. That's why I took this topic. And I told you that this application that have emerged after this research, are in automotives, basically integration of lidar system, light direction and ranging systems in the vehicles for intelligent lighting system, because the talk of the day is to go for autonomous driving, that is called driverless driving. In that case, the sensing system should be very, very, sensitive and intelligent also. So LiDAR is one of them. And those such type of vehicles will have all radio waves systems, radio antenna, and all sort of whatever is required for getting the signals so that the accidents are not taking place. Then one of the examples, one of the examples which can help making the headlamps very attractive would be super lenses. I will be showing you next slide, where we can have diffraction-free imaging, because diffraction is one of the constraints that mars many times the imaging properties of many devices. And similarly, hyperlenses will be used for medical applications where the magnification can be of several order of magnitudes. I will show you that also. Then cloaking, one of the examples is cloaking, and one of the seminal papers I told you that was written by Sir John Pendry. Then of course, because of the structure which is below visible wavelength, the telecommunication will be affected by that. There will be advancement in this direction. Then aerospace, medical instrumentation, and military and defense. So this example, for example, this cloaking could be used in military and in defense. And one of the news items which you would have heard, that one of the missiles which struck somewhere could not be detected by the radar. And I feel that they might have used this metamaterials in order to cloak that missile. And this is the advantage, the advancements that are taking place in the field of metamaterials. Then optics, of course, terahertz and infrared, these are and of course in sensing. So these are the various examples which are there as far as metamaterials are concerned. One of in order to make you that it is of course not a dream today, In China, they have made this type of headlamps of the car where they have put lidar and these type of lenses, whatever I have discussed in the previous slide. And this type of system becomes very intelligent and which is very important for human safety because of the number of that vehicles increasing on the roads. Human safety is the great concern. And with these type of intelligent lighting and intelligent sensing systems, which will be coming into play as a result of the work, the research going on in metamaterials, this type of advancement will be possible. Next. This, I told you that I will be showing you some of the applications. You know what happens that whenever there is an interface, the light is lost in the form of so-called evanescent waves. Many of my colleagues who are very veterans in this field and working in this field, they must be working on the field of capturing the evanescent waves. And because of that evanescent waves, some of the important informations are lost. And with the help of metamaterials, if super lenses are made, then these lenses can be used to capture that lost treasure because of the evanescent waves. And then, of course, we can get a perfect image. And I would like to tell the students that they should refrain from using the word point focus, because a lens does not make point focus, because initially when the refraction takes place, if the lost treasure is due to evanescent wave, so you are not getting every information at the focus of a lens, convex lens, for example. So it is, of course, focus, but not at the point. There is nothing like point in the case of focus. Here, they have to be, but on the other hand, with the help of super lens, of course, we can get a perfect image and perfect focusing. And the other application is making hyper lenses. This will be for medical applications, of course, where the magnification is about, this is about a year ago or something like that. Then I found that the magnification was 2.3. The next is cloaking. In this case, the material, matter which is made of metamaterials will be there, but it will not be affecting the waves which will be going around it. So waves will not be disturbed by the material which is present there. At the same time, therefore, whatever I said, that it can be used for military and defense, and one of the examples is the news item, perhaps. So these new technologies offer ever increasing focus on performance and safety. And here I would like to cite one of the examples of BMW, that recently they have made the body of the car by using metamaterials with polymers. And the flexibility was so high that despite the severe accidents, there was hardly any damage caused to the body. So these are the advancement taking place in this thing. But high-end cars, those are coming in the market. Everybody is getting attracted to that. That's why I thought that I should talk about the automotive sectors. And the most advantage of all these researches will be in the direction of materials, will be mostly in automotive sectors. And next slide, I will be talking on plasmonics. It is a science where it deals with interaction of electromagnetic field with metals. Of course, in this case, the metal should be in the nanoscale. The material property, this will be shown by not by the bulk material, but when the material goes to nano dimensions, and we get nanostructures, then of course we will get such type of properties, and this science is called plasmonics, where in the metals generally we know that the electron density is 10 to the power 22 per centimeter square, and such type of properties will be used to route and manipulate the light at nanometer scales, and I will show you the applications in a moment from now. And what are these oscillations? When these nanostructures are interacting with light, then rapid oscillations are produced on the surface of the metal, and these oscillations are called plasma oscillations. And any wave nature is related to a particle. For example, light wave is related to photon. Similarly, here these plasma oscillations are related to a quasi-particle that is called plasmon. So then we call this as plasmonics. Next slide is that because I have done something in this direction, and one of the one of the studies which we conducted was to make high efficiency LEDs using these gold nanoparticles and silver nanoparticles and all that. Then in NPL, something was going on using plasmonics, infrared to visible upconversion. This is a phenomena in which lower energy is converted into higher energy, because visible has got lower wavelength than infrared. So frequency being inversely proportional to wavelength and energy related to frequency, then this is called infrared to visible up conversion. Otherwise, mostly down, it is down conversion. And then plasmonic lasers. And plasmonics are being used for making efficient solar cells, and especially organic photovoltaic cells are being probed by these plasmonics. And one of the speakers, my earlier colleague, at Nainital, Dr. Pradeep Pant, might have talked about this. I was there, of course, but and the government of India must be taking in this note of this, that plasmonics is going to change the dynamics of solar cells. Then nanoscale antenna. In this case, the antenna can be used to propagate light within the system, and that can be used for communication. Then, of course, biomedical applications and integrated circuits, because of the nano dimensions, they can be used. And one of the this plasmonics is being used by one of my previous students, Dr. Dilip Mehta at IIT Delhi, for many biomedical applications. So that is what I have made certain contributions to society by training some of the students who are doing very good, great job in science. Anyway, this was one of the studies on SPP, though this is not our slide, but by incorporating the nanoparticles of noble metals like aluminum, silver, and gold, we can have enhancement in the luminous efficiency or the photoluminescence efficiency of the LEDs. One of the examples on the left-hand side, where the AG nanoparticles doped on LED are enhancing the photoluminescence intensity to several orders of magnitude. And such type of LEDs are available and are being used in vehicles for making efficient headlamps etc. And at the same time, on the right hand side, it is gold doped indium gallium nitride and gallium nitride quantum wells, where intensity is again getting enhanced to several orders of magnitude. So these plasmons can increase the field as a result of interaction of light with nanoparticles, nanostructures. Therefore, such type of stupendous applications we are seeing in the field of this emission of light intensity, increasing light intensity. Another this thing is the upconversion, where infrared radiation can be converted into visible radiation. And here, right-hand side is the example that we are getting red, blue, and green emissions converted by means of the interaction of infrared with plasmonic doped materials, where the enhancement is very high, and we are getting that infrared is getting converted into visible light. So these are the few examples which I have shown in the field of plasmonics. And if somebody wants to pursue work in these directions. So these are the most lucrative subjects these days. And then I come to the work which I have been doing for 4 years with the help of NPL. We have got a joint collaboration program between FIAM Industries Limited and CSIR NPL, where our main idea is to increase the luminous intensity of the headlamps to several lakh candelas. Because as I told you that speed is going to increase by several folds, so that time the driver should be able to see a large distance. As I told in the beginning, that we should be capable of looking at a distance of something like 500 meters or 2 kilometers. And BMW has developed some headlamps where they can propagate the light up to 1 kilometer. So this was one of the, because this project was taken because of the fact that if we are importing the phosphor from outside, then it is very, very costly. So with CSI and NPL, we have developed a phosphor, which is cerium doped aluminum garnet phosphor incorporated, and it shows outstanding light properties. And one of the biggest advantage of the research which has been done by one of the groups led by Dr. Bipin Kumar Gupta, you must be seeing his name, and rest of the people are his colleagues there. And I'm also there for discussing the things with them. But the work which they have done has got and the advantage that when such type of phosphor, this cerium doped yttrium aluminum garnet phosphor is the blue laser is incident on that, which works at 445 nanometers blue laser, having very high power of something like 2 watts. Then this blue light is converted into bright white light. And the next slide will show you this white light, and this shows the discs which are there, which have been developed for making such type of sources. And here you are seeing that the phosphor has been developed, and the bright white light at the slide number D on the left hand side is showing that when the laser, blue laser at 445 nanometer is hitting the phosphor, then we are getting very bright light, and it has got its intensity several thousand candela. And idea is to go to several lakhs of candela, so that the intensity, the illuminance, the light which is falling on the road should have a very bright light, and so that driver feels as if he is driving in the daytime. Because daytime, the human eye efficiency is more than 3 candela per meter square, and that in order to achieve that luminance and illumination as a result of that, it will require very high luminous intensity, and that is being one of the targets which we are doing with CSIR NPL. And here are various gadgets those have been made in transmission mode, how much intensity will be obtained, and how much the intensity will be in the reflection mode, and so on and so forth. And finally was how we can kill the blue light which otherwise is surrounding the white light. And one of the slides which shows here in the slide number H is showing bright white light. So this is what has been done here. And one of the brightest source that has been made, and last year we achieved this thing, and there has been a bit slow progress in this direction. But recently, this phosphor, which was in the form of a disc, has been coated on a sapphire surface. And by using button lasers of high power, something like 2 watt or 1.5 watt or so, we would be, miniaturizing the size of the lamp in order to increase more space for whatever you saw for the lidar, for other gadgets in this thing, so that the headlamp becomes very, very small by using button lasers. And using that button laser and this vacuum coated phosphorus on the surface, is to achieve several lakh candela, so that the light could be propagated to a distance of something like, the target is to propagate to 200 meters. And so far, the state of art today is that when we drive the car, we see the light at a distance of 25 meters, and all the measurements are done in order to see how much light is falling on the road, or are done at 25 meters. But with these advancements in this direction, this will be going to increase the intensity. And of course, after achieving this feat, that with button laser and all that, the source is made, we will try to incorporate plasmons in the plasmon, the gold nanoparticles and this thing, so that the field of plasmonics could be used to further enhance the intensity of the sources. And lastly, I would like to go into metrology, because I would like to mention that metrology is measurement science. It is different from meteorology, the weather science. Metrology means measurement science. And measurement science is one of the sciences, most difficult sciences, because it deals with assigning a number to a physical parameter. So one of the most lucrative constants is Planck's constant, where the status today is that rather than using 6.62 into 10 to the power minus 34 joule second, we can use the precision up to 7th decimal of this Planck's value with a minimum uncertainty in that measurement. So one of the work which I had been doing in NPL since I was working with photometry division, and it was one of the SI units is luminous intensity. So there was a big program going on, that how we can uh, go to revise the definition of luminous intensity. And that can be done with the help of this phenomena called parametric down conversion. It is called spontaneous parametric down conversion, SPDC. It has got the beauty that when a nonlinear crystal hits a high energy photon hits a nonlinear crystal, two photons are generated simultaneously. And the beauty is that the conservation of momentum and conservation of energy, both working together, here we can have two photons generated. It can be degenerate, it can be non-degenerate. But the point is that the two photons will be generated, and then this type of particular phenomena, spontaneous parametric down conversion, can be used to make absolute photon sources, where we are sure that when we detect one photon, the other is there. If it is at other wavelength, then we can have detection at that wavelength. Then we can count the number of photons which are being obtained as a result of this parametric down conversion, this hitting of a nonlinear crystal by means of high energy beam, of course, blue light, and then we can get the photons in red region, mostly, and we can make absolute photon source where we can count the number of photons that are being emitted. Otherwise, it is very difficult to measure the number of photons which are being emitted from a source. Generally, the usual lights at home or on the streets have got several 10 to the power 15,000 10 to the power 15 photons per second and something like that. But here, on the other hand, we can count the number of photons. So therefore, this phenomena can be used for absolute measurement. And I dedicate this part of my talk to World Meteorology Day, which is celebrated every year on 20th of May. Please remember that 20th May is the World Meteorology Day, and the boys should be made sensitive to how important meteorology is in every branch of science, because mostly in recent years, the Nobel Prizes are going in meteorological science, precision measurements and all that, because these are only precision measurements can make human life better and better. So therefore, I thought that in the this thing dedicating to World Meteorology Day, which was the other day, on day before yesterday, I thought that I should talk to you on these measurements. And one of the difficult proposition in measurement is radiance measurement, because radiance or luminous intensity, these are the property of the sources. But here, on the other hand, with the help of this SPDC, we can measure the radiance of sources, which is otherwise a very difficult parameter to be measured. And just by calculating the number of photons that are being emitted with the source, this, R0 I have written here, it is visible on your screens. And without that, and with that, we can calculate the radiance of the source, which is hitting this nonlinear crystal, and then increasing this crystal, whatever was photons were being produced, the number can be enhanced when another light hits that. Uh, so I think that I have not overshot the time, though I feel that it was slightly more than that. But anyway, I thank you very much for your patience. And if you have any questions on that, I would be happy to answer that. Thank you very much.
Participants may ask questions by raising their hand, or they may write in the chat box.
If they have got not ready-made answers, they can send it to me at my email by contacting Dr. Tiwari or Dr. Singh, and I would be very glad to answer those questions, because I want that the students should pursue these type of research, because this is most attractive and lucrative research that is going on throughout the globe, you see.
Yeah,
This is my contention.
there is one question.
Hmm.
What challenges do engineers face when integrating these new technologies into the automotive sector, automotive industry?
Yeah, there are several, that cannot be counted as such. The challenges cannot be counted on fingers, The challenge is to integrate the whole of these systems. For example, plasmonics. For example, plasmonics is a simple technique where any LED, whatever is achieved, the surface is corrugated, and the nanoparticles are put on the surface. And when we supply the power, then that is increased. And of course, in that case, the integration is very simple. But on the other hand, when it comes to LiDAR systems, light direction and ranging, that is a very difficult proposition, because uh, as far as I know, that none in India has done this thing. So whatever difficulty they face, since I am not directly in the field where I would have seen engineers working in this direction, I would be rather hesitant to answer this question. How much, but there are of course many problems that are faced, and integration is one of the biggest challenges.
Thank you. Thank you, Dr. Kantwal, for taking us to a journey into the future of lighting and cutting-edge technology in the field of metamaterials, plasmonics, and laser lighting. It was great hearing you, as always, and I thank you on behalf of all the participants. So
Thank
someone
you very much.
asked that can we get the PDF of this session?
Yeah, of course,
We can
this I
share
will
it.
send it to you. I have no hesitation in telling, because, I believe on this Vidyadanam Mataparam. That is one of the biggest dance that can be done. And if students can learn something from it, I will be doing it. Though I had sent you that, but since I have made certain changes in these slides, I will definitely send you by this evening or tomorrow morning.
Please take your own time. Thank you.
Okay, thank you. Anybody else?
So we move onward to our next lecture. The presentation was almost self-explanatory. Our next guest speaker is Professor Prem Vallabh Bisht. Professor Bisht, I think he has joined. Sapna?
Yes, sir, he has joined.
I have joined. Neeraj, I will introduce myself. So
Okay, that would be very nice.
take a lot of time.
You will give me a 5 button. Okay.
So let
Please,
me
please,
try
yeah.
to, where is this share the screen button?
Screen share, yeah. It's in the Zoom, I think, at the bottom.
Share, yeah, it is there. Green button, right?
Yeah,
Right.
green button, green button.
Multiple participant advanced sharing, but no, I have to just share the screen. Okay. Just share the screen. Okay. This will stop other screen sharing. Do you want to continue? Yes. Okay. This one share. And just tell me if you already see this. Can you see the screen? तिवारी जी कुछ दिख रहा है?
दिख रहा है, स्क्रीन दिख रही है? वो वाले मोड में चले जाइए. हाँ यार.
Yes, sir.
Presentation mode में आ गए. Okay, fine.
Yes, so as you can see on my back there is a Hitachi bag. I don't know whether you can see. So I'm already planning to go to North India. So tomorrow morning. So you contacted when? Last week or a week before, or when was that? 10 days before? Sudden planning. तिवारी जी सो गए?
हाँ, 23rd you are moving ना, आप इधर को आ रहे हैं.
हाँ.
23 तारीख को.
Yeah, tomorrow morning. So what I mean to say is, I made this amidst a lot of other works because there was grading going on and all that. So, but I thought a little bit whatever we have new ideas we should share with the students and other colleagues, so that fulfills the intention which you have. So I would try to make it simple, but let us see how it goes. So this is imaging an object without detecting the photon that passes through. That means imaging with undetected photons. So this presentation basically is on sensing and imaging. And this slide, which is taken from this NASA website, it's spooky action at a distance. It's a very famous sentence by Einstein. And here there is some photon source in the middle, and which is sending some photon to the, they say Alice and Bob and so on. And then they make some measurements. She makes some measurements, and then they see that they are entangled. So it's more about the entanglement of the photons, how they are used for sensing. And in this respect, I just have taken a snapshot of Professor Kantpal's slides, which he introduced the SPDC in the previous talk. So I'll also show you that slide. This one is, I just wanted to close this. Yes. So this is me working in the laboratory, and the title says that higher order nonlinear optical susceptibilities, Chi2 and Chi3. These are the parameters which we will be using. And on the left side, there is a white light continuum by using photonic crystal fiber, and this white light is being this white light is being spectrally resolved here on the roof of the lab. So lasers are basically have become interdisciplinary field, as they have not yet come to the kitchen, I think, but just now Professor Kanpal mentioned how they are coming on the headlights of the vehicles. And light amplification by stimulated emission of radiation, which we already know. So it's basically light is an electromagnetic wave, and these amplifiers, oscillators, resonators. Actually, if you look at the laser books in the library, they will be kept in the electrical engineering section where there are amplifiers and oscillators, but just optical amplifier. And they are used everywhere now in spectroscopy as well. Spectroscopy basically is the mother of modern science. And this, so in this respect, I have also written a book on lasers. So textbook on lasers, which is this. And it has about 400 pages, 24 chapters. It has basics of photonics and lasers, and ultra-fast lasers and applications in photonics. So you can actually split into 2 courses. These photographs which you see, this photograph is from my laboratory, which we did about 20 years back. And most of the photographs in this book have originated from the lab after working. So what we did was like, we started some experiments in the laboratory, and then I started also, using that experience into putting into the form of book, and that's how it has come. So this is one image from the Mars by Curiosity rover. Kind of imaging, I just want to connect everything to the imaging and sensing. So this is just images, very famous images. And also you can use the laser-induced breakdown spectroscopy for identifying the elements in these stones in the Mars, and look like something similar in Earth. And so that shows the strength of spectroscopy. We also do sensing with another kind of systems, which are small particles, symmetric particles, spherical particles, or cylindrical particles, fibers, bottles, micro bottles. The connection to these comes from those symmetric structures like Gol Gumbad or the St. Paul's domes in London, as well as I have even noticed that in the Lucknow in Imambada, when you put this matchbox at one corner, you can see the acoustic waves come along the sides of the structures. Similar to these acoustic waves, we can also have these total internal reflections on these symmetric micro cavities, optical cavities, and we have these modes generated. And these modes have kind of laser cavity also has these modes. So these modes can be made use of for various applications. They can be connected with the luminescence. They can be, have interaction with the plasmonics. So plasmonics itself is an enhancement of these, as in the previous slide we saw, previous lecture, that they were able to enhance the luminescence of metal nanoparticles. Similarly, those whispering gallery modes and these plasmonics, so that becomes a hybrid system for enhancing those things. And the mathematics involved is very simple, but there are some Bessel functions and Hankel functions come in these modes. But those are all can be simulated with the programs. So this kind of work can be done for simulations as well as for so electric field simulations. You can have the COMSOL software with your institute, and you can do some electric field distribution as well as several other kind of things. But these particles, what happens is they are very sensitive to the radius change and refractive index change. So refractive index is of the order of 10 to the power minus 4, or radius of the order of 10 to the power minus 9. So nanometer changes can be, it can be monitored accurately with these studies. So what we do is we did last 20 years, several students have got PhD on those. That you can see we can select one particle there, and then that particle can be studied by aperture control. And you can have two particles close together, like two pendulum interacting with each other, two oscillators. You can have micro lasing, like it's laser cavity kind of distribution here, spherical cavity, which you can have this R1 is equal to R2 is equal to D by 2. So all these kind of systems can be considered while with the studies of these, and they are very educative and very interesting, and they can be done in the laboratory as well as they can be made after simulations. One of the important things which one of my student did when he visited after PhD, he went to the postdoc in New York, and he found that he can actually sense the virus with the help of these whispering gallery modes. So if there is one virus coming, there is a change of some wavelength, another virus coming, this is change in the other wavelength for the whispering gallery mode of one of these this micro resonator. Okay, so this is what was and they patented it, and I think it got quite good citations also. The title which I gave today for this lecture was imaging with undetected photons. So this is one paper which is published by Zeilinger's group, which is the Nobel laureate of recent Nobel laureate in quantum optics. That quantum indistinguishability by path identity, the awakening of a sleeping beauty. This is just the archives paper, which are other versions of this paper are also published by this group. So in this figure I have taken from this particular reference, and these blue things is what I have added here. So this photon source is there, and it's hitting a magic tray, like magic tray 1, and it is generating two photons, one red photon and one green photon. A part of this photon source is again hitting another magic tray 2, which is identical to that the tray 1, and it is again producing one photon of red and one green. But we have placed one object, this like Schrodinger's cat, on one of the path of this magic tray 1, and this cat is seen by this beam, and this beam goes straight, it's not detected. What is detected is the red beam generated by the tray 2 and red beam generated by tray 1. The interference between these two is generated, and then what we see is the image made by this interference pattern is seen here. So the idea of this undetected photon is that the photons which are detected are only the red ones. The green ones are not detected at all, although the object is kept in the green path. Okay. Now, only thing I have to explain that what is it going on, magic tray 1 and magic tray 2. Let's see in the next slide. So this deals with the nonlinear optics, which is now textbooks are available, and it's a generally course in the MSc Masters, I'm sure, in various colleges, in various universities as an elective. I think it should more or less, Griffith's book of electrodynamics gives you this dielectric, the polarization is proportional to the electric field, and this chi E is the electrical susceptibility for normal electric fields. Okay, and if you have the higher electric fields incident on a dielectric, then this P is not only proportional to the E, but it starts becoming kind of a not the simple harmonic motion, but vigorously, if you pull the spring, then various other Hooke's law is no more followed there, and you can have F is equal to minus K1x minus K2x square, and so on and so forth. So therefore, the polarization equation at high incident electric fields would be not only chi E, but chi 2 E and E, then chi 3. So you see that the chi here was a dimensionless quantity. We know from electrodynamics. It has been introduced here to balance the dimensions of P and E. But here the chi 2 has dimensions of 1 by E, meter by volt. And similarly, chi 3 will have dimensions of 1 by E square. So this is the first nonlinearity, and this is second nonlinearity. So these, for example, symmetric systems do not have these chi2, and some systems have chi3. Water will have chi3 but not chi2 at the except at the surface. So generally, the crystals are birefringent crystals, and they are chi2 materials which are used for this nonlinear optics. So that's the magic tray parameter which I mentioned in the previous slide. So nonlinear optics with chi2 is very simple, some frequency generation or even the second harmonic generation or difference frequency generation. So what happens here is that you have, if a general case, if I take omega 1 and omega 2, two frequencies, then I can have omega 3. That's the sum frequency of omega 1 and omega 2. And there is a virtual levels here, and any frequency you place, you put 1000 nanometer, you will get 500 nanometer. You put 800 nanometer, you will get 400 nanometer here. So omega 3 will be, so it can be degenerate or it can be non-degenerate. You can have 400 plus 600 depending upon what frequency you get. Similarly, in difference frequency, omega, if you put omega 1 here, then it can be, the omega 1 can be destroyed and you can get omega 2 and omega 3. This is known as difference frequency generation. So omega 3 will be omega 1 minus omega 2. So that's the, and this is the wave vector or energy and momentum conservation is followed. The interesting part is that the sum frequency is very well known, and second harmonic generation is so well known that we don't even know that we have a second harmonic generating laser in our hands. These green lasers, green pointers actually have second harmonic of the Nd:YAG laser, and that already has a crystal inside the cavity. So it's very straightforward. You have some nonlinear crystal, even urea can be used for second harmonic generation. So these are, this is some BBO crystal which has been used for second harmonic of 800 to see the blue light here. And this is a sum frequency. You have two 800s and then they can generate the sum frequency. The only difference between this and this right side figure is that this blue spot in the middle, I don't know whether you are able to see. दिख रहा है blue वाला?
दिख रहा है, blue dot दिख रहा है clearly.
So this blue dot will disappear if I block any one of them, either this one or that one. That blue will disappear with the blocking of each other. But some frequency is very well known and very easy to see. But difference frequency is what is interesting, in which what happens is if you have omega 1, which is generating omega 2 and omega 3, but if you have some small omega 2, like this bulb light also present, you can actually amplify that omega 2 to 1. So this becomes an amplifier, optical parametric amplifier, and they can generate lots of wavelengths. These are very popular now, OPO or OPA, optical parametric oscillator or optical parametric amplifier. These are the principles of difference frequency generation. The side light of this DFG, difference frequency generation, is so these are actually two beams which are generated by omega 1. If you just forget this omega 2 on top on the blue side. So this omega 1 generates omega 2 and omega 3 on the right side. Omega 1 is coming also on the right side. Omega 2 is known as signal. Omega 3 is known as, idler. So this slightly it has come down on while writing. So omega 2 is signal. Omega 3 is idler. So that red one, that's the longer wavelength is idler. The shorter wavelength is signal. Okay. So these are all signal wavelengths amplified. Now, let me just skip this for a moment. But you see this slide now. चार्जू किसकी स्लाइड है दिख रही है अंदाज आ रहा है
Yes, sir.
Whose slide is this?
Correlated photons for absolute photon flux.
Yeah, but this slide is not mine actually. You remember whose slide is this?
Sir slide.
Yeah, so
previous slide.
Yeah, previous speaker and Dr. Kanpal's slide, in which he very smartly explained this while.
Kanpal ji wali.
So actually, this, if you look at from this green box, so now that's what is better teaching in the sense you repeat something which already is taught by someone. There's a nonlinear crystal. K0 omega 0 is falling on this and it is generating K1 and K2. So this is signal, this is idler. So in principle, this is what I just now told, that I am just reproducing what Dr. Kanpal already said. So this is known as parametric down conversion, actually spontaneous parametric down conversion, or SPDC. So now we have Chi2 material, we have incident photons, photon source, and we have two wavelengths coming out with K1 and K2, or omega 1, omega 2, or these two. So here I go back to our diagram, which I mentioned in the beginning. So we have a photon source, and we have a Chi2 material, which is generating a signal beam and an idler beam. We have a part of incident photon again falling on another Chi2 material, which is generating again signal and idler. Now we place our object in the signal, this idler beam, and the idler beam just goes, but it is synchronized with the idler which is generated by the Chi2 material second. Okay, and the signal which is coming from the Chi2 material and the signal which is coming from the Chi2 material on the first case, they are both interfere in this beam splitter, and we can make out the Fourier transform of this interference, and we get the image of the object. So this is one of the applications of imaging with undetected photons. The another one which I also found is that infrared spectroscopy with visible light. Now in this case, what they have done, this is a 2016 paper. In this case, again, the second harmonic of a Yag laser is used to generate the signal and idler beams from two crystals of lithium neoprene. So there's one crystal, there's another crystal. This is expanded here. You can see this is one, and this is the distance between these two crystals is Lm. And this is one Chi2 material, another Chi2 material. The signal and idler is generated on Chi2 1, and then the pump beam keeps on propagating through this particular chamber where the gas is inserted, carbon dioxide gas, which is being sensed by this particular experiment. Now what happens is the visible region is very easy to detect. You can have eyes, you can have all detectors, because visible region has been the most exploited region. Therefore, we have detectors, we have spectrometers and sensitive devices, CCDs. But infrared region is not that easy as visible region, although there are all very, at high technological level, they have detectors available. But this particular thing, what it says is, if we look at only the signal beams coming out of this chamber, we could see what happened in the idler beams in the infrared region. So this is another example of detecting the signals, but actually looking at what happened with the carbon dioxide at infrared region. Okay, so that's what I think my aim is about the lecture. So I would also be completing this. And these delta, this phase shift in this particular case is in the crystal's case, and delta M is the crystal, the phase shift in case of when we have the gas inside. So these two differences, if we can find out, we can find out what happened in the infrared region by looking at the visible region. That was so that is all actually, and lots of people have been collaborating. I'm thankful to all of them. Some of the names are not here. So that's all. Gauraji, thank you very much. I would like to actually thank you for giving this opportunity to interact with your people.
Thank you very much, Professor West. बहुत बहुत धन्यवाद। और आपका बड़ा इल्यूमिनेटिंग लेक्चर था और बड़ा इंटरेस्टिंग, उसका टाइटल ही बहुत इंटरेस्टिंग था कि
Yeah, but it was related, quite related to the last Dr. Kanpal. Kanpal ji, is it true or not?
The floor is open for questions.
Professor Best, I am here.
हाँ, मैं वही कह रहा था कि आपकी स्लाइड यहाँ चेप दी है चुरा के।
नहीं नहीं, गलत बात कह रहे हैं आप। वो ऐसा नहीं है, मैं हूँ, बराबर हूँ इसमें।
एक्नॉलेज करा।
I heard your very nice lecture, thank you very much. And
अगर ऑडियंस में कुछ क्वेश्चंस, कुछ क्वेरीज हो तो हैंड रेज कर सकते हैं या चैट बॉक्स में लिख सकते हैं।
Okay, I think that's fine. So you can proceed with your speaker. Thank you very much. I hope they enjoyed.
Thank you very much for the illuminating talk.
Thanks.
Thank you so much. Dr. Hem Joshi is our next speaker. Sapna, has he joined?
Yes, sir.
I have shared my screen. See,
It's, screen is not visible, but
now it is available.
Sapna, please check.
The screen is not visible, but you are audible. You have to share your screen. There is a green
Yes.
dot.
You have opened the screen share option?
Now you
Yes,
see.
sir.
Hello.
No, no. Hello, sir. We are not able to see your slides.
You are
there-
visible, but
So
the
there is
slides
an
are.
option. So there is an option in the bottom, green dot, green share option. From there, you have to go to screen and then share. Put the share button.
Otherwise, you can share. Have you got the presentation? Yeah.
No, sir.
Neeraj,
Ha.
can you see the screen?
No. We are seeing you, but not the screen actually.
What should I do? I have taken the option for sharing the screen.
So you have to press the share button also.
Share, multiple participants can share simultaneously. I have given it. So why it is not shared?
You may join once again after, I think.
Should I send it you in mail?
Yes, sir. You can mail me. I will run the slide.
Okay.
By the time
No,
Dr.
just a second.
Joshi,
Dr. Hem, just a second. See, in this green button, you are pressing the up arrow, the on the right side जो
हरा वाला.
the power है ना, वो वाला बटन आप कर रहे हैं. आप सिर्फ arrow को करिए तो. See, what you are pressing was the multiple participants can share or one participant. Not that. Just on the left of that, the above arrow is there. Not
Middle
that
one, green one.
Yeah, the green is there, but share में एक up arrow है.
हाँ.
वो नहीं जो जिसको आप प्रेस कर रहे हैं उसको ना करके जो ग्रीन बटन का मेन है उसको प्रेस करिए तो.
अच्छा.
जो ग्रीन बटन का मेन है ना उसको प्रेस करिए तो. वो जो साइड वाला छोड़ दीजिए आप. हाँ, नाउ यू शुड बी एबल टू.
स्क्रीन में फ्रेम लिस्ट आ रहा है.
नहीं है.
अब आया.
हाँ, अब शायद आ जाएगा. यस, नाउ इट इज विजिबल.
है ना.
हाँ, आ गया.
ओके.
So Before Dr. Joshi starts his presentation, I would like to introduce him. Dr. Joshi obtained his PhD from Kumaon University, Nainital, like our both previous speakers. He joined the Institute for Plasma Research, Gandhinagar in 1996. He was a postdoc fellow and visiting researcher at Utrecht University and Free University of Amsterdam, respectively. He is superannuated in 2022. He has published several papers and review articles in photophysics, photochemistry, laser-produced plasma, and study of supersonic beams. All the students of photophysics lab over a generation have looked towards him for his advice, and still they are doing this. We are really thankful to you, Hemda. You can now start your presentation. Thank you on behalf of audience. Please, the floor is yours.
Thank you, Neeraj, and the organizing committee for inviting me to give a talk on the work which I did. Because I was involved in the development of various spectroscopic and laser-based diagnostics, as well as study of laser-produced plasma in Institute for Plasma Research. So I thought it is proper I should briefly discuss about various aspects of laser-produced plasma and their applications and how these will be implemented in coming times. So yeah. Hello.
You
Nothing,
may go
sir.
ahead. Yeah. Listen.
The title of this talk is Various Facets of Laser-Produced Plasma in a Nutshell.
You can go to screen share mode
Yeah.
at the bottom.
So what is first thing is what is plasma? It is the states of matter are solid, liquid, gas, and of course, fourth state that is called plasma. So it comes from the Greek word that is called that is to mold. What is plasma? Actually, it is ionized form, or mostly it exists in the ionic forms. But 99% of the observable universe that is constitutes of plasma means it is made of plasma. So now I go to the classification of plasma. The plasma is actually classified according to the temperature and the number density. So different density and temperature ranges classify the plasma from ultra cold to extremely hot plasma. For example, in inertial confinement fusion, temperature and density are very high, solar cooled, and magnetic fusion in tokamaks, the density is slightly lower, but temperatures are higher. Similarly, various nebula, interstellar, the density and temperatures, these are used to classify the plasma. Now, laser-produced plasma has some applications. Plasma is formed by many methods, by electric discharge, or other microwave, and other several methods are used to form the plasma. But I am confining myself to the plasma which is formed by the lasers. The laser plasma has many applications and but some of them I just briefly mention in this talk. First thing is laser breakdown spectroscopy RIPS. Second is inertial confinement fusion, laser-based plasma accelerators. The other applications are surface modification, micromachining, and nanoparticle synthesis. Several other applications are there. First thing, what is a basic LIPS setup? In a basic simple LIPS setup, you have a and Q-switched pulse and YAG laser, it is focused on the sample, and emission is collected and by optical fiber and given to a spectrograph where it is analyzed. Now I come to more detailed systems. In this one, this first one is the same which I described. Fiber collects the light, laser ablates sample, plasma is formed, and then this is transferred by the fiber to a spectrometer to analyze the light, to disperse and analyze them. In the second case, we are using a femtosecond laser, shorter pulse laser. Here, a mass, quadrupole mass spectrum, because ions are also formed, not only neutrals are there, ions are there. As I have told, in plasma, there will be neutrals also, ions are there. A quadrupole spectrometer that can collect the ions and can give information about particular element. The two configurations are basically used. One is front ablation, another is back ablation. In the front ablation, the laser strikes a sample and it is ablated, and the plasma plume goes in the same direction in which laser came. So this is the configuration for this configuration for front ablation. In back ablation, laser comes from behind this sample and it ablates the plasma, travels the opposite in the same direction in which laser came. So this is plasma. The plasma plume has, it comes in the same direction, opposite direction of the laser in case of front ablation, but in the same direction in case of front ablation. Now, Gibbs principles. Gibbs, what is the importance of laser-induced down spectroscopy? It basically determines elemental composition, because in this plasma plume formed by the laser, you will have neutrals, ions, as well as small, sometimes small molecules are present. So what it will give? It will give the elemental composition, which element is present. The line emission from neutral ionic species is generally used to estimate elemental composition, because the neutrals and ionic species are there. They are excited by the collision with electron impact excitation or recombination processes. There are other processes also. They get excited from there, then the line emission comes. And this line emission is used to identify the element as well as estimate the elemental composition. Line emission intensity depends on the transition probability of particular line. A number of density which particular you are taking a ionic line or a neutral line. So number density, what are the neutrals, what are the ions? It also determines, because these are the things which estimate the concentration of the elements. Now, plasma parameters, electron density and temperature also determine, because the excitation rate, ionization rate, all depend upon these factors, electron density and the temperature. Moreover, the experimental constant, for example, sensitivity in the spectrometer, it also puts a limit on the detection of the lines, whether the spectrograph is sensitive in that region, it can detect the lines or not. Using optical, and this is, I am describing about optical emission spectroscopy. It lips, as I have told, the line emission is there, or even some cases, molecular band emission is there. The analysis can be either by enhancing the signal itself or by doing some software manipulations, for example, by subtracting the background or these things. But the active method of enhancing the signal is very efficient to increase this limit of detection as well as to enhance the sensitivity. Now I tell you small difference when short pulse or long pulse lasers ablate, and what happens in this process. In nanosecond laser, this laser is absorbed and the temperature rises, thermal vaporization or plasma for thermal vaporization happens, then plasma forms. In plasma, there will be reflection. Plasma can reflect light, plasma absorption. This is the thing. And then plasma, if there is some ambient gas, for example, if gas or is there is no vacuum, but ambient gas is there. So it will have interaction with it. There may be a shock wave generation, and the plasma may also be confined by the ambient gas. Then we come to the Lipps regime. In this one, the actually elemental composition is a line emission is recorded, and the elemental composition can be detected. The last stage of very long times in milliseconds, the particle ejection happens even the plume condenses itself. Now, in femtosecond laser ablation, there is no such thermal vaporization or such because equilibrium is not reached. So there happens inverse bremsstrahlung or multiphoton. Inverse bremsstrahlung, the laser is absorbed and it accelerates the electrons. The multiphoton absorption also wavelength is low, then multiphoton absorption is shorter wavelength, multiphoton absorption can happen. Then happens the Coulomb explosion. In this case, the electrons are ejected by this field of this intense laser, the eruptive field of the then the energy transfer to ions happens, then electron lattice heating. Then, of course, thermal vaporization happens. After that, if there is ambient gas again, plume will travel, it will have shock wave generation and whether plasma confinement. So same now in the longer times, the regimes are same as in case of shorter. Now I come to Lipps applications. Why we do Lipps or what is the importance of Lipps? Numerous applications, they are not a few applications, but numerous applications from archaeological investigations to medical diagnosis here. So other thing is you can determine the depth profile. If you ablate the part of the laser, the surface is ablated, you can put the laser part which is not beyond this surface, below this ablated surface. So you can get the depth profile, how the elemental composition changes with depth. Or third aspect is in laser pulse deposition, the plasma plume comes, then it deposited on a substrate. So it also depends how your plasma is striking this substrate. What are the parameters? What is the ambient gas or not? So it can control the PLD property. Increasing absorbability. If laser is there, it can abrade the materials, and in some cases it decreases the reflectivity and increases absorptivity. For example, in silicon, if it is ablated by laser, its absorbability is increased, which increases the efficiency of the solar cell, thin film deposition, tailoring weathering properties. Laser comes, laser is treated a sample, its wetting property. For example, it is hydrophilic. It may become hydrophobic or hydrophobic. It is hydrophobic. It may become super hydrophilic. As in case of silicon, it is observed. Silicon is generally hydrophobic. Once treated with laser, it becomes super hydrophobic. Other aspects are in lithography and in ion source generation. In healthcare also, Lipps is being explored nowadays. People are trying to explore what will be how Lipps will help in establishing a reliable diagnostics. Because in Lipps, very small amount of material is ablated in few micrograms, and there is no need of sample preparation. So Lipps technique can be used in these things. The another aspect is space exploration. Space the material, whichever is there in space, so you can get the elemental composition as well as elemental identification of various things. So when you are, for example, in Moon mission and your Mars mission, a LIPS system can give you the information which elements should be present there. First, I come to healthcare. As a diagnostics for various diseases, cancer is one of the deadliest disease and still very reliable diagnostics doesn't exist. So it is important whether LIPS can be helpful in diagnosing cancer at various stages or for different type of cancers. So it will depend upon which element get varies from different in various stages or in different cancers, type of cancers. Second is as a tool for quality control in various drugs, supplements. In drugs and supplements, there may be sometimes adulteration. So you can find if some elements are added there, or so by using the leaves, you can get the information about. Estimating elemental concentration in stones. Stones, if you want to remove the stones by medication, so you have to know the composition, which elements are present, so that after medication you can remove them efficiently. So, but you have to know which elements are there in this one. This example I give, a experiment was done for breast cancer, cancer-affected breast tissue. In normal tissues, it is shown by blue color, and cancer-affected tissue, it is shown by red color. As you see, the amount of calcium has increased significantly in this one. So this is only one example. There are other elemental composition elements also which are identified, which vary with the cancerous, cancer affected, vary in the cancerous affected tissue. So now, what is the reliability of this diagnosis? If we make a laser-induced background spectroscopy diagnostics, now what should be the efforts? We should accurately diagnose cancer in the early stage or advanced stage. First thing is signatures, which elements are present and which vary at different stages, how much there is variation. If complete study to be done, then one should know how various cancerous tissues have different type of variation in elemental composition. You have to establish reliable footprints, and then you have to use machine learning to actually predict what should be the cancerous stage. But these works are still going on, and maybe in future they may come up with some very reliable diagnostics using leaves. But as leaves depends on elemental composition, some other techniques, for example, Raman, also has to be used as a complementary to see whether this composition has something to do with the diagnosis. Now, I've come to second aspect, that is LIPS important tool in space missions. LIPS system in CAM of NASA regularly sends the information about various elements present there. In Chandrayaan also, the LIPS system of there, it identified presence of sulfur. Elemental analysis can be done by the samples from space. As in Chinese moon missions, they plan to bring the sample from the moon and then analyze in the laboratory. And LIPS will be one of the very important systems to do it. As I have already told, LIPS is confined to elemental analysis only. A LIPS hybrid Raman system can provide details. Hybrid Raman systems are used Raman Gibbs systems are used for more detailed information. This is this typical Gibbs spectrum. I think Dr. Gist also showed in this one. So, this was sent by CAM and it shows various in different regions of titanium, manganese, calcium, visible and infrared, lithium, potassium, various elements. But the system, the spectrograph detector system should be able to accurately record the spectra in different regions so that a very nice information about the elemental composition can be made. Now come to another aspect, because there was a discussion about energy also. So there are conventional sources, for example, solar energy, tidal energy, and so on. But for these, you have to depend upon solar, sun, and tides or wind, whatever is there. You can, of course, increase the efficiency of extracting the energy or detecting the energy by your solar cells, using that energy utilization by making efficient solar cells or similar systems. But another aspect is there, energy is directly generated either by fusion or fission, atomic energy. Fusion, you have, as you know, the deuterium and tritium, tritium and the deuterium. These combined form helium and a neutron. The mass effect that results in energy. Fission, a heavy nucleus, disintegrates in smaller nuclei with neutron, but of course, in fusion, cleaner and safe energy. But in case of fission, you have the danger of radioactive fragments also. For fusion reaction, however, plasma should be confined. In suns and stars, it is the pressure and gravitation, very high density plasma is there that confines the plasma itself, because very high density is there, the pressure is there. But in Earth, we have to adopt other methods to confine the plasma. First method is magnetic confinement, tokamak, stereotypes, etc. For example, ITER tokamak ITER machine is based on the magnetic confinement. So you have to confine the plasma using high magnetic field. The another is inertial confinement. You have to use high power lasers, and these high power lasers are used to compress the sample in small size. Inertial versus magnetic confinement, you know, this magnetic field that confines the plasma itself, but pressure is very low, and confinement times becomes a seconds. In East tokamak, it was around 1,000 seconds. It was reported steady state. In case of inertial confinement, on the other hand, the density becomes very high. Pressure is very high as compared to the solar interior. But confinement, because your laser is a pulsed laser, the confinement time is very small. Now, what are the various stages of inertial confinement? Inertial confinement, the laser energy is laser energy strikes the material, and this ablated material comes outwards and transports the thermal energy inwards, which in turn, which compresses the fuel, and a thermonuclear reaction takes place there. This is the RNN, Lawrence Riverborne National Laboratory, is home to NIF system, where 192 lasers were used with 1.9 megajoules of ultraviolet rays. And they were used to compress the fuel and a release of this. On December 5, 2020, they achieved scientific history by achieving 3.5 megajoule of energy from an input of 2.05 megajoule of energy. Means you got the energy from this fusion reaction. Future and challenges for inertial fusion. But there are several challenges in case of inertial fusion. This you need first thing is a very efficient system or compact system should be there, and you need very stable lasers and stable and compact lasers. Again, energy gain has to be increased. There will be technological diagnostic aspects, they have to be upgraded. So in this, briefly in this talk, I just covered what are the, I could not cover all the aspects of the plasma generated by laser, but there are two very important aspects. And I was involved with the LEAPS work where I studied various atomic processes while laser produce plasma is formed, how we can be also worked on the with various geometry using magnetic field, using providing plasma, how the detection efficiency can be increased, or we also thought of making a hybrid Gibbs Raman system to have better analysis of the material which we have to identify or which we have to analyze. So, second aspect comes about energy. As I have told you, inertial fusion depends upon the ray because it has a very short confinement time and depends upon many lasers. They are perfectly aligned on the sample, and of course, several technological aspects are involved there. But this gives a ray of hope that fusion reaction is possible in these systems. Another aspect about it, the ITER experiments, various experiments are going on, and there are tokamaks in India and also which will study various physics phenomena as well as what will be the difficulties that will come in building a fusion machine. For example, the impurities are deposited in the walls of the machine, which can be identified by LIPS technique. And other diagnostics are also used, for example, machine diagnosis for the health of the machine or for the functioning of the machine also. I think there will be a future, the natural sources of energy, for example, solar, tidal energy will be exploited by devising better detection systems as efficient detection systems, but at the same time, thrust will be also there in harnessing the fusion energy. Thank you very much.
Thank you, Dr. Him Joshi, for your illuminating talk. Session is now open for questions. Those who are interested in any questions, may raise their hands or write in the chat box on various facets of laser-produced plasma, laser-induced breakdown spectroscopy, or inertial confinement used for fusion.
Yes. Actually, for inertial confinement, the fuel is very, even in micrograms, fuel is used. That is not much. And generally, and very high power lasers are used. In case of this, the energy can be lower, but you have to whatever electron temperature or density, electron temperature is in a few electron volt, and the density is around 10 to the power 20 or 10 to the power 19 per centimeter cube. But inertial fusion density is very high, as well as temperature is also very high. That's why you need number of lasers simultaneously striking the hologram to heat or compress the plasma.
I think this is the first time this break even or even more energy has been produced using
Yes, yes.
last year's.
Actually, that was the gain of the fusion experiment, that they got more energy as compared to the total laser energy that was put on the hologram itself. This was the first demonstration that energy will be can be achieved from the inertial fusion reaction.
Any questions from the audience? Questions from the audience are welcome.
Hello.
Yes.
Yeah. Hi, this is Sachin. I have a question, sir. How do you detect the basically characterize the plasma? Do you use some laser beams or
Sorry?
how do you characterize the plasma, temperature and other parameters? How do you
This
measure them?
plasma is characterized by its temperature and density. For temperature measurement, we need some spectroscopic methods. For example, line ratio method is used to estimate its plasma temperature, electron temperature. And the lines observed are broadened by Stark effect. The Stark width, from the Stark width, we can find out what is the density of that plasma. And the elemental composition, whether they are ions, neutrals. So if you observe the particular line from ion or neutral, so you can give the information about the composition.
Okay. Okay, thank you, sir.
So we move to our next lecture of the day. Dr. Sachin Barthwal. I think Sachin asked this question.
Yeah.
Yeah.
Hi.
Good to see you.
Thank you.
A person from the very coolest of cool region asking about plasma. Hmm. So let me introduce Dr. Sachin. Dr. Sachin Barthwal holds a doctorate in laser cooling and spectroscopy from University of Hyderabad, India. He has done his master's in physics from JNU. Currently, he is a postdoc fellow at Parker Lab Laser Cooling Group at Georgia Institute of Technology. He is working on quantum interaction experiments on lithium-cesium ultra-cold systems. He is an experimental atomic physicist with extensive experience of more than 14 years in laser-cooled atomic spectroscopy, including quantum simulator systems, quantum sensor technology, etc. He has worked at various institutes of repute, including Georgia Tech, Raman Research Institute, Bangalore, Wuhan Institute of Physics and Mathematics, University of Hyderabad, Indian Institute of Sciences, Bangalore. He has a number of patents and published work. I thank you for accepting our invitation. Yeah, and you are working in cutting edge technology. We are very keen to hear you. The floor is now all yours.
Thank you, Dr. Tiwari. Thanks for that kind introduction. First, I'd like to thank the organizers who have given me this opportunity to present my work, what I have been doing for little more than a year now here at Georgia Tech. And as you are hearing to Dr. Joshi before my talk, he was talking about the fourth state of matter. And I'll be actually, when I was in my school, we had heard this news of fourth or fifth state of matter is discovered, made actually. And that was what is called Bose-Einstein condensate. Yeah. So, or in short, it's called BEC. So this was basically a work by an Indian scientist, Satyendranath Bose, and in collaboration with Einstein. Actually, he sent this paper to Einstein, a theoretical paper, where he proposed this kind of interaction happening in bosons, basically at a very, very low temperatures of the order of nanokelvins, wherein they'll show quantum behavior, and they'll show coherent behavior, and all the particles in such a state will behave coherently, just like a laser beam, like photons in the laser beam. Yeah. And this was a story in 1920s or 1930s, but it could get realized way later in 1990s, mid 1990s, I'll say, when people like Eric Cornell, Wolfgang Ketterle, and Carl Weinman made this elusive kind of state of matter, what is called Bose-Einstein condensation. And I actually started my career at ISC Bangalore, starting to trying to kind of chase to make this as the to make the first BEC in India. We could not do it at for various reasons, but I'm happy that I'm working on one of these systems here at Georgia Tech right now, and I'll be talking a bit about that. So I'll not go into the results and other things, but I'll be telling you more about what all things are involved in these kind of experiments, and what are the technologies, what kind of lasers, and how do we control them, and all these things. So, and hope I'll be able to answer the curiosities of various students, probably a lot of students I see here. So the thing is called the technique. What we use is what is called laser cooling. Yeah, and I'll be talking about quantum emulators using ultra-cold lithium cesium systems. Yeah. So we use we basically laser cool lithium and cesium atoms separately, and then combine them together to make this what are called quantum emulators. And these things have come up very recently, in the last 25 years, that these kind of systems, what are called the ultra-cold atomic systems, wherein the atoms are can be cooled to very low temperatures of nanokelvins scale, few hundreds of nanokelvins. And once they go to that state, they can be controlled very precisely using various magnetic fields, using various laser beams and all. And then they can basically mimic they can basically mimic a quantum, a solid state system, a condensed matter system, wherein there are heavy nuclei sitting all across the crystal in a periodic fashion. And then there are electrons who are which are hovering around, making an electronic gas kind of a system. And then there are phenomena like magnetic behavior of these systems, or superconductivity shown by these systems, or things like what is called a Kondo effect, which is so in the regular circumstances, as you lower down the temperature to these kind of temperatures, like nanokelvins, or these kind of ranges of temperatures, you should be ideally seeing the resistance should be, the electrical resistance should be going down, because you are letting the electrons move, there is no hindrance of on the movement of the electrons in these cases, at lower temperatures. But in certain cases, what happens is the reverse happens, and the resistance goes a little higher than expected, and this is what is called a Kondo effect. And so all these kind of various phenomena can be very nicely done using experimentally done using what are called these quantum emulators. So that's why they are called quantum emulators. So they can basically mimic the quantum systems, in beat condensed matter systems, and many other things, as you see in these slides. And this is a very recent paper. Just last week, I was just making these slides, and I saw this paper by Gu et al. In this journal called Science, where they basically have a bilayer atoms of dysprosium. They are cooled to very low temperatures, and they are made to come 50 nanometer away from each other, and they could basically see the interaction, the dipolar interaction happening between the two, in actual. Yeah. So these are the kind of interesting experiments which can happen, which can be done using these techniques, what I'll be talking about. And as I told, about the Kondo effect, so one of our main aim of using lithium and cesium atoms here. So lithium is it's one of the lightest element in the periodic table, and cesium is one of the heaviest ones. So using lithium and cesium, the reason behind using lithium and cesium is because lithium is very lighter compared to cesium. So lithium can act as an electron gas, as in case of a solid in a condensed matter system. And the cesium can be pinned nuclei, which are basically the ions, which are sitting at the lattice sites, basically. And then how they interact with the electronic gas or things like that. So how do we achieve the pinning of the cesium atoms at a certain position? Is by what we do is the lattice trapping. We trap them in a lattice form and then make these lithium move through them. Okay, so this is one of the main motivation behind this kind of this particular experiment we are doing here. And then there are exotic states like spin glasses and spin liquids, which can be again studied using these spin interactions of these kind of in these kind of systems. And Kondo effect and high TC superconductivity also can be, because lithium, okay, just a thing that lithium comes in two varieties, lithium-6 and lithium-7. These are the two main stable isotopes of lithium. And we are using lithium-6, which is so we use an enriched source of lithium-6, which is not a naturally, very much naturally abundant. It's 8 to 10% of abundance is there for lithium-6, and this is the fermionic system. So as it goes down in temperatures, there'll be a state it'll reach wherein no two fermions can come together and sit in the same state. There's a Fermi's this thing. So what we do is we use a kind of a trick to make them come together and make them combine together to form a boson. Using what is called Feshbach resonance by swiping the high field. So at a certain field, they can interact in a way that they can form a lithium molecule. And now, because they both are fermionic, once they combine together, they form bosons, and then they can do what is called they can make BEC basically. And that's the same thing which happens in case of superconductors. If you have heard of Cooper pairs, two electrons which are fermionic, they come together and they form Cooper pairs, and that's how the superconductivity happens. Yeah. So these kind of experiments using lithium and these kind of ultra-cold atomic systems can tell us more about superconductivity as well. And people are already doing great on kind of experiments on using these. Yeah, so like these are some of the things which we plan to do with our experiments. And like just to give you a brief of how the lithium structure, the hyperfine structure, which is relevant to this laser cooling is there. So lithium is like an alkali atom, and like similar to like sodium atom, like you would have done the D1, D2 lines of sodium in your experimental labs, in optics labs, basically. So similar to sodium, lithium also has a D1 and D2 lines. So transition going from S to P, P half and P3 half. And like these two, in sodium, it comes at 5890 and 5896 angstroms. In case of lithium, it comes at, both of them are like very near to each other, around 10 gigahertz away from each other. And the wavelength for which for lithium is around 671 nanometers for these D1 and D2 transitions. And these are the ones which we use for laser cooling. So this is the system which we use for laser cooling. So I'll be telling about lithium first, and then I'll be telling about the cesium, and then I'll be telling about some more details of the experiment we have done on lithium, basically. Yeah. So if you see this, the whole chamber, the experimental chamber, the vacuum chamber, this is the ultra high vacuum chamber. Like this is like 10⁻⁻12 torr of vacuum is there. And it starts with a lithium oven, which is basically heated to around 400 degrees Celsius to get enough vapors of lithium to be used in the experiment. And then there are capillary collimators, which collimate this lithium beam, like atomic beam coming out of these collimators. And there are ion pumps, which evacuate the chamber. And then there is a gate valve, which basically separates out the atomic source to the experimental chamber. And then there's a Zeeman slower, which basically slows down the atoms so that we can trap them and cool them further down to microkelvins and nanokelvins for our experiment. And then there are magnetic coils, which basically confine like either in the anti-Helmholtz configuration or in Helmholtz configuration in two different cases. And then there is a main chamber, which wherein we basically do the experiment. And like this is the laser system which we use for addressing the doing this laser cooling in lithium. So we use a D1 diode, D1 line diode laser, which is logged using a vapor cell. So all these experiments basically need very precise control of the frequency of the lasers. So we use a vapor cell and do the spectroscopy to log this D1 laser, and the D2 laser beam, which comes out of a second harmonic generated laser beam. And this is locked to the D1 laser using beat lock frequency, using a beat lock technique. And then both of these, they go to the experimental chamber to do the what we call as MOT, the magneto-optic trap. So magneto because we are using magnetic field, and optico because we are using the lasers to cool them, basically. Yeah. And then there is a certain thing in case of lithium, what is called the lithium molasses, which is what is used to cool the temperature. So these cooling techniques are basically, they basically depend on Doppler's cooling. But then because lithium, as I showed you in my previous slide, sorry. Okay, so like lithium has a structure that here it is. So lithium has a structure in the 2p3 half. The separation of these hyperfine levels are much it's around 4.4 megahertz, the whole spectrum of these. This is much smaller than the natural line width of lithium, which is about 6 megahertz. So what happens? This the cooling is doesn't seem to be very effective. So we use what is called D1 molasses cooling, and we use the D1 hyperfine levels for that. And that D1 beam is generated by a totally different laser, and this what is called a FP laser here, and the tapered amplifier. TA is a tapered amplifier. And what you see over here, all written as AOMs, are the acousto-optic modulators, which basically control the switching on and off the beam during the experiment. So like as we do all this laser cooling sequence, So how which one is switched on and then which one is switched off is controlled by all these AOMs, and they are again controlled by the control system which we use. I'll be telling you about that a little later. And so this is the whole experimental setup. The first figure over here shows the lithium source first, and then there is a G1 slower, and these are like because they have to be baked to very high temperature to get the required vacuum. You have to basically like take out the adsorbed gases inside the vacuum chamber walls outside, and then they can get sucked by the vacuum pump, the ion pump or the getter pump. So we have to heat them to very high temperatures of about like 200 to 300 degrees Celsius for weeks, and that's why you see those aluminum foil wrapped around them. And then the second one is the main chamber, which basically where we basically do the experiment. And then the third table is the lithium, the laser setup. On this extreme corner, you see this D2 laser, which is a second harmonic generated laser, and then a tapered amplifier is there. And then we have this D1 laser, and then there is a tapered amplifier for doing the D1 molasses cooling here. Okay, so this was for the story of this was the story for lithium. And cesium also we have a corresponding like a cooling transition, which is the D2 line, and this is the same D2 line which is used like cesium is the same element which is used to define second, and the second is defined as the ground state oscillation based on the ground state hyperfine oscillations, which comes to about 9.19 gigahertz separated, and then the D2 line in cesium is well separated and all, and like it comes to about like 850 nanometers, and we use DBR layers to access this particular line. And here you see the whole vacuum chamber, which and the cesium comes from this arm of the vacuum chamber. This has a cesium 2D MOT. So we first cool the cesium atoms in 2 dimensions, and then send them to this main chamber so that they can be cooled further in 3 dimensions. And yeah, so, and then this is the spectroscopy setup which we use for basically frequency locking cesium. And this is a polarization gradient, spectroscopy setup, wherein we use the different polarization of the 2 components of the coming out of the polarizing beam splitter, and then lock the laser using this technique. And then there is one more thing. Once we laser cool them, we reach the temperature of few tens or hundreds of microkelvins. But then we need to go further down in temperature, and then we have to basically trap them, collect them in a certain place, and which is done using what is called a dipole laser or a dipole trap, which gets formed by a very high power 1070 nanometer beam coming out of this ytterbium fiber laser sitting in this corner here. And this gives out a 200-watt beam, which can basically drill a hole through this wall where I'm sitting or where you are sitting. So this is a very powerful beam, and then this beam is basically separated into two different beams, as you see in this green this thing, and this is in IR. This is an IR beam, so green is just for depiction, it will not be visible actually. So it gets divided into 2 beams, and then the 2 beams are crossed at an angle of around 15 degrees or so, and then they are focused, and then focused at the center of this place where we are doing the laser cooling. And once the focus matches with the trapped the cooled atoms, those cooled atoms get trapped in this dipole trap, and once they are trapped, then we further cool them using what is called evaporative cooling. Yeah. So as I was telling you before, all these experiments are done in a certain sequence. So we first do switch on the atomic oven, heat the lithium atoms, And then like once they are heated up, they go through the G-man slower, they get slowed down. Then the laser cooling beams are switched on by using the IYNS, and like for around 10 seconds. And once we load what is called a MOT, the magneto-optic trap, we then go to the what is called a compressed MOT phase. And one second, I have a slide for that. Yeah. So we first okay. So this is just a lithium spectroscopy cell which we use for doing the spectroscopy. So this is also heated to around 400 degrees to get the lithium vapors. And then once we have the from the lithium oven, the lithium is coming out. We cool them using the magneto-optic trap. This is shown here. And once they get cooled down, then the next thing is what is called a compressed MOT phase, wherein we basically compress the atoms to a higher density so that we can achieve more number of atoms in a very small volume to make sure that we get enough atoms getting trapped in the dipole trap. And so this is achieved by basically detuning the laser beams more towards the resonance and making the magnetic field higher so that the gradient is more higher. And then the next thing is the D1 molasses, which achieves about 100 microkelvin of we have been this is an old number actually. We have been recently doing to about 40 microkelvin, 40 to 30 microkelvin as well. And the number of atoms is about 1E8. This again an old number. And then once these molasses achieved, then we do the dipole trapping, which is shown here and in this cartoon. And then once we do the dipole trapping, next stage is the evaporative cooling. And all these things are kind of controlled in a very sequential way. The MOT happens for around 10 seconds, and the CMOT happens for about 5 milliseconds. About 2 to 3 milliseconds is what the D1 molasses happens, and then the dipole trap happens for about 3 seconds, 3 to 4 seconds. So how do we control our whole experiment in this sequence in a particular pattern in a way? So how it is done is using these electronic control systems. So we use 5 modular systems to generate these specific type of signals to control our laser beams, as I told you before. And these are parallel digit, serial digit, analog, and the microwave, RF and the microwave. And some of these things are generated by these evaluation boards, the DAC, the digital to analog converters, and the direct digital synthesizers. The frequencies are generated using them, and the VCO also, voltage control oscillator, which basically generates the frequency for the beat locking, and which is of the order of few gigahertz. And yeah, so these are the control systems. And then once these are the control systems, but then how these signals are generated and how they are controlled in a way using a computer is what we do is we use different what we call as sequences of the experiment. We basically define certain parameters. So how many milliseconds the cooling will happen, how many seconds the cooling will happen, how many milliseconds the CMOT stage will happen, then D1 molasses will happen, and all these things. These are all parameterized here. And then we control the run of the sequence also using these programs. And these are mostly, these are written in XML, and then the sequences are written in MATLAB, as XML sequences. And this is one of the sequences which you use for doing the Bose-Einstein condensate experiments. And this has various parts wherein we control the magnetic field. And so these are the various time instances, and then what will be the current which will be passing through the magnetic field coils to control the magnetic field. And these are the various the amplitudes of the various cooling layers, how they are controlled at this time it will be this much, this time it will be this much, like that. And then this is the final thing, which is the dipole trap here. So how the dipole trap will do the what is called the evaporative cooling. And I don't know if you noticed something here in my first slide is okay. I have a cup of tea over here. So this is actually to depict you how the evaporative cooling happens. So the evaporative cooling basically happens the same way we cool our coffee or a teacup. We basically blow away the hot molecules by blowing air onto the cup. And like, so the hot molecules will go away, and what remains back is like cooler than the original thing. And that's how this in the same way the evaporative cooling also happens. And yeah, so the evaporative cooling is the next step in our cooling cycle, and which can like lead to the temperatures of few nanokelvins. So these are the like various sequences which are done in this using programs run using the computer. And like this is a typical CGM magneto-optic trap, wherein the like about 10⁸ cesium atoms are cooled to about 100 microkelvins, about the temperature of that order. And like these are the various steps of lithium cooling. And then like this is a typical lithium D1 molasses time of flight. So we basically cool the atoms, and then to basically measure the temperature of the atoms, what we do is we let we just switch off the trap and let the atoms like fly away. Okay, and like what you see over here is like an image of the atom cloud after 0.1 milliseconds, 2 milliseconds, 3 milliseconds, 4 and 5 milliseconds. So as they expand, as they move out, they expand, and we basically measure the velocity of those atoms, which is inherently coupled to the temperature, which tells us the temperature, tells us the kinetic energy of the cloud, and hence the temperature, which is half mv square is connected to the 3.5 kBT, and that's how we can measure the temperature of this cloud. And the typical temperature here, what is shown over here, is about 40 microkelvin, and these are some of the latest numbers we have. And the number of atoms trapped here is about 1E8 number of atoms. And then once we have this D1 molasses cooling, the next stage is the dipole trap. And here you can see I was telling you about these high power laser beams, which are crossed at about 13 degree angle. And so these are the two beams over here, these straight lines, and the central the yellow thing is what is the cooled D1 molasses. And once these laser beams are switched on, the atoms get trapped in these the focus is of these beams, and you can clearly see it here, and then in some of the subsequent slides. And okay, this is what the evaporative cooling mechanism is. As I was telling you, you blow away the hot atoms out of the trap, so whatever remains is the cool, and they basically thermalize to go to the lower temperatures. And this is a typical evaporation optimization sequence we do. So there are various stages of evaporation. So as I told, so we don't blow air around the trapped atoms. Basically, what we do to do this evaporation is slowly lower down the power of the dipole trap laser, slowly down. And these are the amplitudes which are given to the acousto-optic modulators to lower the power of the lasers going down, 70, 40, 27, and so that's how we keep on going down. And these are the various temperatures in microkelvin. And then this is again an old number. We have recently reached about 20 nanokelvins or so. This is about 260 nanokelvins here, the last number. And this is these are various stages of evaporation. This thing, and these are the temperatures, and these are the atoms which we have reached to. And there are various optimizations which happen in this evaporation. So we basically so these high power dipole trap beams, the waste of that beam is about 30 microns or so, but this atom cloud size is about a few millimeters. So we have to basically center it very nicely into the where the beams are getting focused, so that we can get maximum number of atoms. And so there are various optimizations which we do for this evaporation, and and then we do it at different stages of evaporation. At step 3, if you see, a TOF is for time of flight. So we just let the atoms fly away, as I told you before. That's a technique which we use to measure the temperature. And in this particular instance, there are about 10^5 atoms here. And in the case of after step 8, we get about 1e5 atoms. So the atoms are getting reduced, as I told before. The evaporation. What we are doing is we are removing off the hot atoms. So whatever remains cooled. So we basically lose atoms. So this is a destructive kind of a technique. So we start with 3-5 atoms, and then we end up 1e5 atoms. But the temperature is much lower here, is a few tens of nanokelvins. And that's the temperature which is actually needed for achieving the BEC, the Bose-Einstein condensate. And this is a typical dipole time of flight. And here the number of atoms is 1e6, and the temperature is 70 microkelvins. And this is the evaporation time of flight, where the temperature is in the order of nanokelvins. And the number, this number is actually not very good number. We should be actually having 10^6 atoms. So we are about 100 times lower than what we should be having to have a healthy Bose-Einstein condensate in our lab now. And these are the various sequences which are used to basically control these things. So this is the orange one shows the dipole trap. So the dipole trap amplitude as it goes down to do the evaporative cooling. And the blue one at the bottom is basically the magnetic field, how it is ramped down to the high field so that we can form this BEC using what is called Feshbach resonance. And then these are the various field ramping trials we are doing for BEC, but we are yet to actually make it here, but hopefully we'll do it maybe this week or next week, hopefully. Yeah. And these are the other ramping trials. Okay. Thank you very much for your attention. And this is how it looks like when we actually work on these lasers. So this is in red color. So that's how you see this red hue across the table. Yeah. And at the end, I would like to acknowledge Professor Parker, with whom I am working, and Dr. Sung, who has graduated last year when I was here, joined, and then other PhD student Kaiyue, Yang, and Yang Hao. Thank you very much for your kind attention. And you can have questions.
Audience may ask questions. They may write on chat box or raise hands.
Okay.
Okay,
So
or you may ask your questions later. We can forward it to Dr. Saji.
okay.
Yeah, there is one question. You are using lithium for research. Is lithium not hazardous?
Okay. So what we are doing over here is we are using lithium, but this is all inside the vacuum chamber. So everything is isolated and all. It sits inside the vacuum chamber, and it's ultra high vacuum. So there is nothing else other than just lithium there, because we have to, if there is other kind of gas or other things so we won't be able to control the lithium atoms that nicely the way we want them to be controlled. So that is one thing. And yeah, so that's it. So we don't actually so when we are making the oven, we do it in a glove box and all. So so that we don't get in contact with it. But I have basically cut lithium with my hands also, with just using gloves and all. So it's So we use like very few grams. Like, so we recently got our recent supply of lithium-6, which is a big container, about $1,000 or something, and like which has like 4 grams of lithium. So it's like very small quantity. Like, so, and that it'll last for years for us. Yeah.
So I would like to thank Dr. Sachin for
Yeah,
such
thank
a
you.
nice talk and interesting talk, which includes emulating quantum phenomena using ultra-cold systems, Bose-Einstein condensates, exotic states for quantum information systems, and also showing us their experimental work on lithium CGM ultra-cold system. Thank you very much.
Thank you.
So we have slightly rescheduled the program. So as our distinguished guest for today and the keynote speaker for the photophysics, photochemistry section, Dr. Ramin Kumar Pandey has an important meeting. So as we are running slightly behind the schedule, so Dr. Neeraj Joshi's talk will be after this. Sorry for the inconvenience. It's my pleasure to introduce our esteemed speaker, Dr. Raveen Kumar Pandey. He is Distinguished Professor of Oncology and Director of Pharmaceutical Chemistry at Roswell Park Comprehensive Cancer Center. He has worked on the use of certain photosensitizers, nanoparticles for cancer imaging, PET, MRI, fluorescence imaging, and therapy, photodynamic therapy, chemotherapy, and more. He is also a founder and CSO of Photolytic LLC, a spin-off of Roswell. 3 of the products developed by Dr. Pandey are at various stages of human clinical trials. Photolytic has also established a partnership with AMI Organics, a pharma company in Surat, for further development and commercialization of these products for head and neck cancer and brain cancer by photodynamic therapy and cancer imaging by positron emission tomography. He was awarded PhD in medicinal chemistry from University of Rajasthan, Jaipur, and then worked as a postdoc fellow at the University of California, Davis, USA, and University College Cardiff, Wales, UK. He worked as a scientist at Oncological Foundation of Buffalo, USA, founded by Johnson & Johnson. Dr. Pandey has published over 350 research articles, including books, book chapters, and review articles, and has 42 patents to his credit. He has received several awards: American Chemical Society John F. Sholkoff Medal, Excellence of Photodynamic Therapy Award, Rajiv Gandhi Award in Heterocyclic Chemistry, China 1000 Talent Award, Albert Nelson Marcus Lifetime Achievement Award, Inventor of the Year Award, Niagara Frontier, Roswell Park President Award, and recently in 2023, he also received the National Academy of Inventors Fellow, USA. Thank you for accepting our invitation. We are keen to listen to you. I hand over the mic to you.
Okay. Can you hear me? Hi.
Yeah.
Okay. So just see if you can see my the presentation. So can you see my presentation also, please? Hello?
Presentation is not there yet. Okay.
So I see that in my screen. I don't know then.
The green share button is there. At the bottom.
Let's see.
Green colored share.
Yeah, just 1 second. Let me see. Green color at the bottom of
This Zoom. There something like participants and chat.
yeah, okay. Do you see it now?
The window is visible actually. The desktop is visible. Yeah, now it is there.
Okay. Let's see if I put it in a full screen.
Yeah,
Okay. Is it okay?
yeah, it's fine. Yeah.
Okay. Okay, so first of all, I'm really highly thankful to Dr. Neeraj Tiwari as well as Dr. Singh for inviting me for this presentation. And though it is a little bit different than the theme of the conference, so the only topic I saw in the program is the use of light for different methods. So what I'm going to do is just going to present the use of light for the treatment of the cancer. And we have been working in this project for last so many years, and we'll just discuss some of the importance of the light as well as the ultrasound for the treatment of cancer imaging and cancer therapy. So in brief, the concept is that when a drug, or we call it photosensitizer, is injected into the patient, it has the ability to localize in the tumor. It is in the other part of the body also, but it remains in the tumor for a longer period of time. And then it is exposed. So it is with the light. So it is a local treatment. So when it is exposed with the light, the photosensitizer gets excited, and then it reacts with the oxygen in the tumor because there is a lot of blood and blood has the oxygen. And that converts to reactive oxygen species. Generally in the PDT, it makes the singlet oxygen. Besides, there is some radical, but mainly the singlet oxygen. And that singlet oxygen is responsible for the photodestruction of the vessels, the capillaries, which supply the blood. So then there is no supply of blood to the tumor, and tumor starves to death. But besides that one, what the singlet oxygen does is also destroy a part of it, of the photosensitizer, and the one which still remains, that goes to the same process. In the patient, the treatment is done for around 20 minutes. So this is, I'm not going to go in the details, but this is the mechanism of the PDT. Photosensitizer is excited, it goes to the excited, sensitizer goes to excited triplet state. From that it releases the energy. The energy that is released converts the oxygen, the molecular oxygen that we breathe, to the cytotoxic agent, and it does so many things. And one of them is the destruction of the tumor that I mentioned before. Now, so this is the same thing which is presented in the diagram. And as I mentioned that, sorry. So as I mentioned that there are two reactive oxygen species. One is the singlet oxygen and one is the free radical. But we don't see much free radical in PDT. It is mainly the singlet oxygen which does all the destruction of the tumor. So now, what is the advantage and limitations of PDT, that is photodynamic therapy? The advantage is it has very few adverse side effects if it compared to the chemotherapy. It is little invasive if you compare it with surgery and surgery mainly, and the short treatment time, usually in outpatient setting, which is really important for the economy or point of view, can be repeated at the same location if necessary, little or no scar after healing, and lower cost than other treatment. So which plays very important role. But what is the limitation? So the compound that is currently is used in PDT, and it has been approved by USA and number of the other countries, that it also accumulates in the skin. So it has skin phototoxicity, which is problematic, especially in those countries where there is a lot of sun. Accurate light delivery to the tumor, and that is where the physics plays very important role, the light delivery, how to do it. And the tissue oxygenation is crucial. In other words, most of the tumors are highly vascularized because so there is a lot of oxygen, so that is not the issue. But there are some tumors which are hypoxic, and that where PDT has the limitation. But it can be done by changing the light dosimetry. Impossible to treat metastatic cancer, and that is true. It is if the tumor has metastasized all over the body, then this treatment is not useful. So it is very important, the imaging part of it is very important, that we can image the cancer at an early stage. Depth of penetration, as you all know, you guys all are in the physics, longer the wavelength, deeper the tissue penetration. So that's why the longer wavelength lights are important, and that is where the ultrasound could be useful, though which is at the preliminary stage, and tumor specificity, and that is where the drug development plays important role. That is the medicinal chemist, they can make the drug which is more specific to tumor. So now it is just to show you how the near infrared agents are important and how important role they play. So as you know, the blood has the absorption around about 600 to 610. So it is better not to use the photosensitizer above that wavelength. But you don't want to go too far, because if you go too far, and that is where the water start absorbing the light, and then it could generate heat, and that is the principle, as we all know, about the microwave. So for the chemistry, I don't know if there is any chemist there, but that is the window which we need to use above 600 nanometers. So 700 to 800, or we can go up to 900 is the window which will give us the maximum tissue penetration. So now I just mentioned, though PDT is being used for the number of the thing, but there are the two important one. One of the important one is the brain. Because in the brain cancer, the problem is there is no treatment whatsoever. So the survival of the patient is only 7 to 12 months. The main thing which is done in the brain treatment is the surgery, and after the surgery is the chemotherapy. So now the other interesting part in the brain tumor is generally it is in the form of like a solid the tumor. So if you picture this one, this is from the Mayo Clinic picture I have taken. So this is the tumor. So the surgeon can remove the tumor. That is not the issue. The issue is the margin of the tumor, because there is where there are a lot of the neurons. So in the neurons, so the physicians are a little bit, or clinicians are very careful about it so that they don't destroy the neurons. If they destroy the neuron, the patient could paralyze. So therefore, the important part is where these photosensitizer, which are derived from porphyrins or the chlorophyll, that they have the ability to fluoresce. So in other words, if they are injected, and after that, when they are doing the surgery, so definitely in the brain, the skull is going to open. When they are doing the surgery, if we can see them, So then it will be much easier for the clinician to do the surgery to remove as much as tumor possible. So that is the fluorescence plays very, very important role in the surgery. And then the residual tumor can be exposed with the light. And that way, at least there is a number of the cases in which the survival is at least up to 5 years. So it is even if it is not a cure. So it plays very important role in PDT in combination with surgery. And the same thing is being done now by using the ultrasound. This is from the Cleveland Clinic, where they are using the ultrasound for not only for the imaging, because the prostate cancer is very difficult to image. So they are using the fusion ultrasound and MRI that was used for imaging the prostate cancer, and then the ultrasound probe is used, as you can see, and then from the rectum and from the rectal wall, the cancer is irradiated. Now, the interesting part of ultrasound, as we know, the depth penetration is not an issue. So the only thing is the dose of the ultrasound, because if you are using the high dose, it can generate heat. So if it is the local, then you can change the light, the ultrasound dosimetry, and so that the treatment can be used. So in the Cleveland Clinic, it is one of the way to treat the prostate cancer. So now what I'm going to just mention a little bit about what is the difference between the photodynamic therapy and sonodynamic therapy. In other words, where we are using ultrasound instead of light. So the good part is these are the compound which we have developed. So we are using as they are at the final stage of the various trials. So these are the 3 compounds which we are using to compare it, which one is the best. And so what happened is PDT, I already mentioned how the PDT plays the role. In ultrasound is the cavitation impact. So what happens is when we are doing the ultrasound, irradiating it, you must have seen when you are using these ultrasound probes, another thing, that it reacts with the water. And the good thing is, and also the energy that is produced, that also excites the photosensitizer. In other words, the same compound can be used for the PDT as well as can be used for the ultrasound. And some of the compounds are reported to make the radical ions and the singlet oxygen, but what we have noticed in our compound, they make mainly the radical ion. So it is a very interesting thing because you are doing the PDT, which makes the singlet oxygen, and ultrasound mainly make the radical ion. So you are using 2 different techniques to kill the tumor. And so these are the different photosensitizer that is currently being used. Some of them are at the earlier stage. This is the only compound which has been approved all over the world, and these are at the different stages. The another one that is being used is for the alpha-linolenic acid, especially for the treatment of basal carcinoma. And the concept of that one is the ALA. It is an amino acid. It is in a form of the cream is used, and the surface of the tumor, for example, in basal carcinoma. And as we know, the ALA converts into this 5-aminolevulinic acid by using the glycine, the enzyme that converts into porphobilinogen that go to uroporphyrin to the coproporphyrin to protoporphyrin, and protoporphyrin is the one which is used in the photosensitizer. So by using this amino acid, then you are converting that to protoporphyrin, and this whole thing, the biosynthesis, it happens in the mitochondria, and then you are using the light treatment, and it does the job. So just to give you an example, see the fluorescence diagnosis, which is done for use of this for skin cancer and basal cell carcinoma. So if by using these compounds, it gives such a great benefit to the physician. They can clearly see the clinician, so they know where the light treatment can be done. So it helps the guiding the light delivery to the patient. And we get some fantastic data. You can see is over here, and this is after the PDT. And this is the oral cancer. This is one of the main problem. One is because in India, especially, the people use a lot of tobacco and others, these things, and betel nuts especially, and it creates the oral cancer is one of the country where there's the highest number of the oral and lung cancer. So it can be used for the diagnosis, and the treatment works like a charm. And so now for the how you increase the specificity of the tumor, that is the drug development. I'm not going to go into great detail, but there are two approaches in the drug development. One is called the passive approach, and another is called the active approach. In the passive approach, you are using a series of the compound, which is very common in the pharmaceutical world. You take one compound, you look at its efficacy. Depending on the efficacy, you change the moiety and its overall lipophilicity, tumor specificity, and if it is chiral, you see whether is the single component or single isomer is more effective than the other, and you design the compound on that basis. Most of the drug development is actually done on this one, not limited to PDT, but the other also. The other approach is the active approach. The active approach could be more specific. You look at the receptor, which has the high expression in certain particular compound of the tumor. Then you start targeting that receptor to make it more tumor effective. And then once you get the target specificity, then you, by using the overall lipophilicity, you direct the overall pharmacokinetics and pharmacodynamics of the compound. That is how it clear out of the system, how fast you want it to be retained, because you also want to make sure the compound doesn't stay in the system for longer time. So it is the active approach. And so I'm just going to give you a little bit about our work. So these are the compound. Look at these are all derived from chlorophyll and bacteriochlorophyll. The reason we did is because, as we know, we all eat, have a lot of spinach and other things. So there are a lot of chlorophyll. Cows use a lot of grass. So there is no toxicity there. So the compound, if we derive from them, the chances then it will not have the problem, the skin phototoxicity that has been the main problem of photofilm, the current clinical standard. So if you look at these compounds, the chemistry part, I'm not going to go in detail, but it is amazing. You look at this structure here, 5-cyclic ring, you change it to the 6-member ring, you see the shift in the wavelength from 660 to 700. Now you change this pyrrole group diagonal to each other, reduce this. This is only one pyrrole ring is reduced. They are the two pyrroles which are diagonal to each other reduced. Now you are up to 800 nanometer. So by using these compounds, you can go from 650 to 800 nanometer wavelength. And this is the fluorescence. As we mentioned, fluorescence play important role. We are exciting. And this is the fluorescence. Look at here. In this compound, we have fluorescence above 800. And it does not overlap the absorption. So now this, I give you some example of the SPPH, which is currently in the phase 2 clinical trial. We are trying to have that in India with a company in Surat called AMI Organics. We have just recently signed an agreement with them. So we are working with this. And this, I just want to show you some of the data. This is the compound derived from chlorophyll A. We call it SPPH or photochlor. Look at this. This is not done by us. This was done by in the UC Davis. These were these cats. They have this the tumor, and it was not it was somebody's pet. They did the radiation, didn't work, and the PDT was done. Look at the dose, in a very small dose, 0.3 milligram per kg. One dose, one treatment, and this is for 5 years. It was after that one, the cat was very old and died, not with the cancer, but the age, but it was very tumor-free. This is the horse, which was done by in the St. Louis. and we send our drug there. It was a racing horse. It has the cancer in the eyelid. So, and then the treatment, this photosensitizer, this HPPH was injected directly into eyelid. Treatment was done, and you can see that it was gone. This was a dog of the Bill Gates, as you all have known, his treasurer's dog. So we sent our compound from here to Seattle. It was treated, and this was the tumor before and after. This was done here by late Ostroff, who was the dermatologist, and this was the basal cell carcinoma, the skin cancer before and after. You can see before and after. So it can be removed by surgery also, but the thing is after that there will be this scar in the face and other thing, but here there's no scar. So that is the advantage of this drug. And this is in the lung, and this is the esophagus. This was the lady which was 43 years old. She was from Florida. So after that one was treated with the PDT. It is a true story. And after she was in the hospital for 14 days. And last day, she was asked by the clinician what she would like to have. And she said she would like to have hamburger. So she had hamburger. So it is one of the amazing story of the treatment. And so it worked really, really well. So this also now what we are doing is we are using the trials in India where we are using the PDT with the immunotherapy. So this is for the esophageal cancer. We are starting in India and hope it will be in the market soon. And now this is, I'm talking about now for the tumor histology, that is for the brain cancer. So this was initially before going into the patient, it was in the rat. So the tumor was implanted in the brain of the rat. And then you can see this is the tumor. These are overexpression 10 times than this. And this is after the treatment. 30 days and 40 days works really beautifully in that one. And now it is currently in the phase 1 clinical trial at Roosevelt Park Cancer Institute. So this is this compound, that is the 800 nanometer compound. The reason we use this because in the brain, there are nest of the cells which are deeply treated. So the idea is if you are using the 800 one, so at least it can go up to 2 centimeters deep, and that the cells, the nest of the cells, if they're there, they can be treated. So this is the utility of this one. Once the phase 1 is done over here, the goal is then move it to India and other countries. So now for the target specificity point of view, I will go very quickly now. I know that I don't have much time. So we can use the targeting moiety attached to this one and make a series of targeting galactins, integrin, folate receptor, and EGFR. So targeting can be made. So the other thing is when we have the linker, now we are attaching the photosensor with the linker in such a way. So if we have the problem is, as I mentioned before, the PDT is only for the local treatment. So now if the tumor has already been metastasized, then we are using the PDT in combination with the chemotherapy. So doing that one, the photosensitizer is attached with the chemotherapy agent. And now when we are treating the PDT, what PDT will do is it will make the singlet oxygen, and that singlet oxygen will cleave this double bond. So now we have the free chemotherapy agent and we have a free photosensitizer. So that way, what we are trying to do is using this type of the approach for using these for those patients which has the cancer has already been metastasized. So these are the different targeted we are using, for example, in the prostate cancer. At the initial stage, the galectin-3, that receptor has the high expression, in the galectin-1 has the high expression in the advanced stages. And the good thing is this compound, the beta-galactose, it binds both galectin-3 and galectin-1. It works very beautifully. You saw that it is in the lysosome, and we have to use this HPPS-GAL, this is lysotracker, and this is the merge images. And you can see with and without, there is a significant difference in efficacy. And the other one we are using is for targeting the epidermal growth factor receptor. We are using the erlotinib. This is the Pfizer drug. So we are in touch with the Pfizer in this project. So we made a series of the compound, and this compound, number 10, is very much effective. As you can see, it's a very high uptake also in the tumor cells. And look at the difference. It is very interesting if you look at the chemistry and the biology and the physics together, which is a wonderful thing we can achieve. The only difference in these two is the chiral center. So if you have a chiral center, it works beautifully. If it does not have the chiral center, it doesn't work that great. So the way it is interacting with the protein and the other thing and the receptor, which is really, really interesting. So this is at the uptake. We look at the compounds uptake at the different time points so that the PDT can be treated at that time. And this is just to show at the various doses. And you can see the efficacy. Efficacy increases tremendously when we are using the erlotinib in the HPPH moiety. So this compound is currently at the toxicological stage. And so now I'll just discuss a little bit. So we made a series of the nanoparticles where we are using these compounds. The beauty of the nanoparticle is we can load both the compound HPPH and chemotherapy agent, because you need the chemotherapy agent in large amount and the photosensitizer you need small amount. So on that basis, we can do both together in this combo. And the thing is, we can increase and decrease because these are made with the different components. So depending on what we want to include, how much material we want to include of the photosensitizer and the chemotherapy agent, we can modify accordingly and make our customized nanoparticle. And this is just to show you that in hypoxia, the environment, this is the control. And if so, the SDT works even in the cell death, because if you look at it here, it is in the hypoxic environment, PDT does not work. As you can see, all cells are available. And here, if you do SDT, you can see the cell kill. Where if the non-hypoxic, both PDT and SDT work. So what I'm trying to stress is that when we are using this same photosensitizer, when we use light, it makes the singlet oxygen. When we are using ultrasound, they are emitting radical. So we're using the same compound by changing either ultrasound or by light, we can increase the overall efficacy of the drug. And one of the reasons could be that there are two different mechanistic pathways. And so this is the release of the drug from the compound. So in other words, if you have the nanoparticles and the drug is inside the nanoparticle, use the ultrasound slowly, you can reduce it. And so this is the HPPS release with the ultrasound. So if there is no ultrasound, there is no release. So this was done in the test tube experiment. So you take the drug. In this one, use the test tube, irradiate with the ultrasound, and then filter it, and you can see the release with the time. And this is also, we can use the doxorubicin. In other words, if you are doing the chemo and the PDT together, you have the nanoparticles, and nanoparticles, you do the PDT first, and slowly doxorubicin is also getting released. And now you can use the primary tumor as the metastasized, you can treat by this approach. And this is in the prostate cancer. We are working on the use of ultrasound and PDT. So as you can see, this is the drug before the pre-PDT and after the PDT. As you can see, what is happening, some of the drug is also going to be exposed, but if you can look at it, it is in circulation. Now, when you're using the ultrasound, the tumors, the delivery vehicles, that is the capillaries, the blood capillaries are being dilated, and now you have the more photosensitizer in the tumor. And when you are using now the PDT first PDT, and then with the SDT, you see a significant difference in the long-term the tumor cure. These are the 80 days one. I mean, it is really, really interesting. So this is again when we are using the nanoparticles instead of the drug alone. By using the nanoparticles, when we are using the PDT, we are getting better response. So in other words, delivery vehicle make the difference, and the nanoparticles play a very important role. But we have to be careful what type of nanoparticles we are using. They should be biodegradable and biocompatible. And we have now done another thing is when we are using the PDT and SDT, and in combination with the doxorubicin, we see the better response for the chemotherapy and photodynamic therapy. And here, this is what we use is called STAT3 dimerization. It is as a biomarker. By using this biomarker, we can also make the PDT more effective. Depending on that one, do we need more light there because the drug is already there? So can we do that one and increase the efficacy? So finally, these are the students and the postdoc. They were involved in this project, and without collaboration, it is next to impossible to do any research. So we have a very good collaboration with the different clinicians and pharmacologists, and also thankful to Naresh Patel. He's the managing director of AMI Organics, and we have been fortunate getting the funding from NIH and private organization. And finally, this is Niagara Falls. As you know, we are having, I'm the chair and host for this conference. This is the International Conference on Porphyrin and Phthalocyanin. It is next month from 23 to 28. And this is the way the Niagara Falls looks in the winter. This is in the summertime. This is in the evening when there is a sunset. And this is when Nick Willinda, when he crossed the Niagara Falls. That is a picture of that time. So we invite you all, and if you could come over, it will be wonderful. There is if you are interested in attending this, please let me know. We can still work on it. So thank you so much, and I really appreciate everyone for the organizing committee for giving me this opportunity.
Thank you, Professor Pandey, for this wonderful talk. It opened many areas and discussed many areas, so many fields where a young researcher can work, including photosensitizers, application of singlet oxygen therein, photodynamic therapy, and diagnostics, limitations at the current stage, and application of sonodynamic therapy, drug development, advantage of near-infrared agents, and ultrasonics, and efficacy of photodynamic therapy in the case of brain tumors, for example, glioblastoma, in combination with surgery. And it was very interesting to know that how slight structural changes in chlorophyll class of compounds can convert these compounds to fluorescent region compounds, and using PDT in combination with chemotherapy in case of metastasis, and also using nanoparticles as drug delivery agent. So it was really a very illuminating talk. We are very thankful for the talk and accepting our offer.
Yeah. Thank you very much, Neeraj. Actually, I think the interesting thing in this the project is that it is a very interdisciplinary. It cannot be done by one person. So it is the input of the physicist, because without light, we cannot do anything. So we need light. We need the delivery. So we need the people, those who are working in the materials and other things. We need the chemists, we need the biologists, and we need the clinician. So it is a wonderful project if it can be done in one center where all these peoples, they work together with for the same goal. And I was lucky that in Roswell Park, we got that opportunity. Actually, it was started with the Tom Doughty, who passed away a few years ago. And he was the person, his vision, he's the one who started accumulating the scientists in the different discipline. And not only in the USA, I think that's why he's called father of photodynamic therapy, that it is currently all over the world. People are working on this therapy. And I hope in India, my goal is with the help of the AME Organics, we will be able to move it to commercialization and the benefit of the patient.
Yeah, I would like to tell the audience that Dr. Pandey has made tireless efforts so that the therapy can be used in India also. And he's doing so for quite some time. There are certain questions from the audience. I think Dr. Neeraj Joshi has raised hand.
So
Neeraj,
thank you, thank you, Professor Pandey, for a very interesting talk and the nice work you are doing. So recently I was looking at the photoacoustic imaging, which sounds similar to the sono treatment of your molecules. But I'm curious, do you use the ultrasound to create ROS, or you still use light?
Yeah.
That create photoacoustic mechanism to create that kind of effect.
Yeah, no, fantastic. I think photoacoustic is a way to go, especially for the breast cancer. We are working on it. We did not mention it over here. But see, the main thing in ultrasound, the sonodynamic therapy is there are thousands of papers. The problem is that how to use the ultrasound and for how long to use the ultrasound. And depending on the compounds, for example, I give you one example because you mentioned about the photoacoustic. In the photoacoustic, the lot of work is going on, and I hope someone in India does it. You are doing it. It's wonderful. If I can be a part of your research together, if you can do something, I would very love to do it. So the one thing what we have noticed, and I did not mention it over here, if we are using the gold nanoparticles, and in the gold nanoparticles, the wonderful thing about it is if you look and if you believe in the Vedic science and all the stuff in India, the gold by itself was used in the therapy before also. And now we have given the name of the nanoparticles to it. Actually, the Swarna Bhasm, we used to call it, that was the nanoparticle, So, but anyway, now the good thing about that one is if you use these gold nanoparticles, and in that one at the periphery, if you have any compound with the SH bond, then you can have that, you can decorate the gold nanoparticle with this. Now, if you use the photosensitize, the perfluorine base, the amazing part is, and you guys are the physics, you have all that much of knowledge. What happens because of the aggregation of the molecule, if you just picture a ball of the gold nanoparticles and these porphyrin-based compounds are at the periphery, they aggregate a lot. So they will not good for the PGT, but they are wonderful for photoacoustic. I mean, they are amazing, really. We have done some of the work and they work very nicely. And now what happens is, I gave just one slide. In that one, when we are connecting these porphyrin-based compound to gold nanoparticle, if we have a linker which can be cleaved by the singlet oxygen, then these particles, after the photoacoustic, we use the light, and from that one, we cleave it because it will make singlet oxygen, and now they will be wonderful, these compounds for the PDT point of view. So photoacoustic is you are already working, so you have much more knowledge than I do, but especially for number of things, for head and neck, but besides that one, I think for the breast cancer, it has a great opportunity, and we have in the longer wavelength compound, because in the breast it's a soft. So if it deeply seated the tumor, they will penetrate more by using the 800 nanometer light. So it could be a wonderful thing for photoacoustic imaging and for the therapy. So I'm so happy that you are working on photoacoustic.
Thank you, Professor, for answering.
And Dr. Vandana Dwivedi have a question related to drug delivery method. Sapta, can you unmute Dr. Vandana Dwivedi? She is a chemist.
Okay, yeah, I'm Dr. Vandana Dwivedi. And thank you, sir. Thank you. At least I got to hear something related with chemistry. And I teach photochemistry paper. And there I happened to do the same thing, same topic, while I was teaching application of photochemistry. So I have two questions, sir. One is that there are many ways of drug deliveries, but as light is an external stimuli, so how, I mean, I'm always fascinated with the dynamics of engineering of what is going on inside the human bodies, but how we manage to direct the light or a drug to that particular place only.
Yeah.
I mean, how it happens. And second is this, I know a person who makes this Swarna Prasan, just you said in Ayurveda. So what happens is generally she prepares in her own home. She's a doctor in Ayurveda. So when because what she asked me said there are very few publication on the this Ayurvedic medicines, because when they give the medicine they either give it shahad or some other sugar or something, so it is not pure 100% pure that thing. What you say is nowadays we call it nano, but that bhasm is not in pure form. So how do we quantify or like analyze the dimensions of that bhasm? I mean,
Yeah.
in Ayurveda, this thing.
Yeah, no, that is a, so there are two things. The first thing is, as you asked one question, that is the delivery of the light.
Yeah,
So
yes.
the delivery of the light, yes, that is an issue in photodynamic therapy. That the limitation is where you can deliver the light. That's the only part you can treat. So. But there are a number of that cancer indication when you can use the light. For example, if you are using basal cell carcinoma, that is not an issue. If you are using the lung, then you use the endoscope. Through the endoscope, you use the fiber optics and you deliver the light. You can deliver the light anywhere in the lung. That is not an issue. In the oral cancer, that is not an issue. In the larynx, that is not an issue. In the brain, when you are doing the surgery, you are opening the skull, and then you are doing the surgery. So at that time you can deliver the light there also. And in that one, we have also developed the delivery thing so that we can use that. What we do is we use the balloon, because if you just picture the brain, when you remove the tumor, then there is a cavity you are producing. So what we have done is, the way to deliver the light is we use a balloon, fill it up with the saline water, and just if you picture the balloon, and then we put the fiber inside, and the fiber illuminates the whole area, and that way we deliver the light. And besides that one, we also determine that from whatever the material the balloon is made of, that when we are inserting the light, what is the input and what is the output, whether any light is being we lose some of the light. So generally, so that way we can do it. So,
And the drug is there only. And I mean,
yeah, so drug is already injected. So drug is already injected. So when the drug is already injected, generally it takes In our compound, they take 24 hours for the maximum uptake of the drug. So at 24 hours, the drug is already there. And then because it fluoresces, so that helps in fluorescence-guided surgery to remove as much as tumor possible. And then we use the PDT treatment. So because the drug has in the residual part of the tumor that is there. So yes, we can not, but certain places where we cannot use the deliver the light, that is the problematic. But in that one, what can be done is we can use the ultrasound. So because the ultrasound is, because penetration is not an issue. The only thing is in the ultrasound, it is the emerging technology right now. Still, there are certain issues where how much dose of the ultrasound you are going to give, because you have to be very careful not to give very high ultrasound dose, because that can generate heat and destroy not only the tumor, but the surrounding tissue also. That is the question in the light one. The other thing you talk about is the delivery vehicle. Yes, it is true. Generally, and that has been the issue with the Ayurvedic medicine, that how to use it. Not only just these gold nanoparticles or Swarn bhasm. Even if I give you just one simple example, I was using ashwagandha. And ashwagandha, what I did is I took the ashwagandha from the Nainital area. There is Haldwani in that area, and I used the ashwagandha from the Kerala. Now, when I use the ashwagandha from the Haldwani, that is the form where last time when I visited, I got some ashwagandha there. I use in combination with the Taxol, because Taxol, as you know, is a chemotherapy drug. I can reduce the dose of the Taxol by 16-fold if I use the ashwagandha from the Haldwani area. I could not do the same thing when I use the ashwagandha from the Kerala area.
Yeah.
So what I want to say is that ashwagandha is just good, but from where we are using that ashwagandha. So the unfortunate part is in our Ayurvedic medicine, there is no quality control. So that needs to be done. Then if we are using ashwagandha from certain part, whether do we have the same component? See, the thing is, I hope somebody does it. I still believe that it is not that I come from the Uttarakhand area, or that is not the region I'm saying. There are so many in the Himalayan region, in the Jammu and Kashmir, and the Ladakh, and that area, the high altitude. There are so many wonderful, wonderful medicinal plants. I wish somebody does it. It is unfortunate that previously we have so many talented these plant chemists like Ashma Chatterjee, you know, all of the Sukhdev and all these people. They did some wonderful work, but not many people are working on it. I think that part is problematic. And so far as coming to your bhasm particles, in that one, I think first thing what we need to do is, even if that gold bhasm is there, can we in that way somehow purify that in such a way we take only the nanoparticles which are like 5 to 20 nanometer or 30 nanometer of size. Use those nanoparticles instead of taking the whole thing, because what happens is if you use this nanoparticle above 100, that could be problematic, because that can accumulate in the capillaries, and here we are trying to treat the cancer and the person may die with a heart attack. So that way we have to be a little bit careful, and it can be done. I mean, we can use the filters, different sizes, and then remove that one and then start with that one. I think gold has a lot of benefit.
Thank you, sir. Thank you for a very inspirational talk, sir. Thank you.
Thank you so much.
There are some other questions, and as Vandana and Dr. Pandey were discussing, the issue of standardization was always there with Ayurveda and still is there, though some work is going on in this field. There is one question that what are the earlier symptoms of tumor which you have observed? This is the question is basically for clinician, I think, but Can with fluorescence imaging, can early detection of tumor can be done?
I think in that one, photoacoustic will be more useful than the fluorescence. Fluorescence is good for the fluorescence guided, this one. But for the imaging point of view, because as I think Dr. Joshi was talking about, I think the photoacoustic, because they are using in photoacoustic, the ultrasound is the one which plays role. So the deeper penetration point of view, it will be much easier. Actually, as you know, Neeraj, the GE is spending $1 billion on optical imaging, in which they are using the coherent tomography as well as the photoacoustic, because the main thing is still we don't have the three-dimensional images. It is very difficult to do. And so that one, fluorescence, I think is good when we are for regular one, for when we are using the localization and all that stuff, and also when we are using the guided surgery but for the detection point of view, I think it could be problematic.
There is another question, that energy range of photodynamic therapy. So I think in terms of wavelength, you have already addressed, but can you throw some more light? What is the energy range here of photodynamic?
Yeah, so the light, that is the issue, as I mentioned that previously for superficial tumors and other things, that is not an issue. But the tumors are deeply seated, it could be a problem. So for that one, especially the long wavelength, the lights, that will be much more useful. You can go up to 900 and that one. So that will give you at least around about 2.5 to 3 centimeter deep in the tissue. And also it depends from tumor to tumor type also, because the morphology of the tumor changes. For example, if you have the tumor in the breast, it will be much better for the deeper tissue penetration, because the tumors, the tissue are soft. But so that depends on that one. But ultrasound in combination of PDT and ultrasound, I think we can achieve more this thing. And the second thing is, it is always, I don't think one therapy will be useful for everything. I think it is we have to go to the combination therapy, where I think will play important role. And for example, PDT now is being done even in the chemo with the immunotherapy. So there are so many things going on. I think in the combination will work much better, and we will have the better success.
Another question is, what research is underway to improve photodynamic therapy?
Yeah, so there are two things, as I mentioned. The one thing is it is a combination of the light and the drug. So one thing is the equipment. So previously, if you look at it, the lasers, we used to have huge, big lasers. And nowadays, the diode lasers. So now you are like a small box, and you can you can make customized one. So in that way, the technology in the equipment has, especially in the physics, has done wonderful things in which we can use the diode laser, we can do so many different things, and it is much easier. Fiber optics is a tremendous the discoveries and the advancement there. Because previously, when I started the PDT at that time, we used to have a much difficult the time. And now, especially what clinician want is a simple thing. So now, if you look at it, the lasers, you guys all the work now, you can just push the button, you can get the wavelength, whatever wavelength you need. You don't need an additional technician for that. So that is because of to make it more cost effective. So so for the equipment side, I think there is a lot of advancement there. For the drug point of view, the main thing is to make the compound much more tumor specific. So target specificity is the main issue. And we have to be very careful when we are going to target the receptors, because the receptors are all over. They are in the tumor also, they are could be in the some non-tumor part also. So we need to look at it that we have very high expression in the tumor. And when we are making these compounds, the main thing is to make sure first the compound is not toxic, because it is going to stay in the liver, and because that is where the clearance is. So you cannot, there will be next to impossible to make a compound which is only in the tumor. It will be in the other part of the body. But what is the role of the pharmacokinetics, how it is clearing from the system, that is very important to understand. So any chemist who is working on, I think, should have a close collaboration with the biologists, especially the pharmacologist. So by doing this thing together, we can improve the design and make better candidates.
I think role of nanoparticles is also important here. The amount can be reduced.
Yes, I agree. I think nanoparticle, the only thing, Neeraj, the one problem what I have, and perhaps you guys are also have the same problem. Nanoparticle is great, but when people say the nanoparticle, that, what nanoparticle, I think it should be very well defined, because the nanoparticles, main thing is should be non-toxic, it should have certain sizes, it should be biodegradable. I mean, if you make a nanoparticle and it is sitting in the system for a long, long time, it will be very difficult. So that's why, actually, if you look at it in the drug development, forget about PDT, in other drug development, there are not that many nanoparticles which have been approved by the FDA, because the main thing, if you are using any nanoparticles, again, look at their pharmacokinetic profile, how they are distributed in the system, how they are and how fast they are clearing from the system. If they are sitting somewhere there, then our system, our biology of the system, every part in the body is important. And the God has given it there because of some reason. So if you are disturbing that one, if you are disturbing the enzymes, if you are disturbing everything, that could be problematic, not in the short run, but in the long run. We may be trying to treat the certain disease, and that patient may end up in some other complications. So we have to be careful.
Thank you. There's one last question I will take. Is there any photosensitizer which can generate different types of ROS upon different light irradiation?
Yeah, no, this is a very good question, actually, but that's what we have been trying to do. You can make a compound which will make mainly, we can generate mainly the reactive oxygen species, that is your free radical, then the singlet oxygen, but it is very difficult to have a compound with a different light source will do the different things. I haven't seen any of them. And the second thing is that I think we should not waste our time in developing those compounds, because the reason is the singlet oxygen is actually much more reactive in PDT than the free radicals. But if you are treating the hypoxic patient, the patient where there is very less oxygen, that is where the radical ion, the compound which produces only radical ion, because they don't need oxygen. So that's why it could be useful. But by using the ultrasound, some of the compounds, and I don't know why it is happening, because that needs to be studied, and I didn't see anything in the literature why certain compounds, they make only by using the ultrasound, they make mainly the radical ion, and some of them they mainly make the both radical ion and the singlet oxygen. That is still in the emerging field, but it will be a very good exercise to investigate, to use the various type of the compound. For example, if you like the fullerenes, it is the report, I have not worked on that one, but I saw the papers from China. They are using the fullerenes, and they are saying by using the ultrasound, they can be very, very effective. And but the reason in that one, they have not given what dose of the ultrasound has been used and how it is being, the detailed mechanistic part of it is not there, but it is, I think it is good to look at those papers and just try certain things if that is the case.
So I thank Professor Pandey on behalf of all the participants for such a wonderful talk. Thank you very much,
Yeah.
sir,
Yeah, thank you so much, Dr.
for
Tripathi.
giving your precious
And
time.
thank you to Dr. Gupta and all the member of the organizing committee. I know it is so difficult. I'm working on to having this conference in next month. It is a lot of work, and I really congratulate you all having such a nice conference. So good luck and thank you.
And thank you for joining regularly our different sessions.
Thank
So our next speaker is Dr. Neeraj Joshi. So today's session is going towards the life force oxygen. We generally use triplet oxygen. So singlet oxygen can also do wonderful things. So our next talk is also based on it. Dr. Joshi currently serves as lead technologist research at the University of Ottawa with over 6 years of experience in this particular field. He is working in the field of photophysics and photochemistry for, I think, around 12 or 14 years. He is skilled in optical and ultra-fast laser spectroscopy, time-resolved fluorescence spectroscopy, photocatalysis, and application of light in various fields, such as clean energy, water purification, pollutant, and degradation. Dr. Neeraj Joshi has been recognized with over 35 publications and has 2 US patents. He has earned his PhD from Photophysics Lab, Kumar University, Nainital. We had wonderful time together. We had a wonderful group there, and that was the best time after I joined the present institution as a teacher. In their company, my school and college days returned back in the lab. He has expertise in optical spectroscopy, data analysis, photophysics, photochemistry, photon upconversion techniques, optics, nonlinear optics, and spectroscopic instrumentation. I hand over the mic and the virtual floor to Dr. Joshi. Thank you, Dr. Joshi,
Thank you,
for accepting our offer.
Dr. Tiwari, though I used to say Tiwari ji. So thank you, Tiwari ji, again. So I'll share my screen now. I hope you can see my screen, right?
It is there.
Can you see my screen?
Yes.
Okay. Thank you very much. So Dr. Tiwari or Tiwari ji has given my introduction already. So at the last moment, I changed the title and 2-3 slides based on the previous lecture given by Dr. Pandey, a wonderful talk that made a platform. And so I try to make a very easy presentation so that audience from the different discipline can understand and would be easier for students to grasp what I'm talking about. So the title now is the reactive oxygen species generation and application. which is very close to the singlet oxygen actually. So I will start with where the Tiwari was talking about Nainital. So I'm from, not originally from Nainital, but I can say my home is Nainital. I spent a considerable time with Tiwari in various journeys. So we were going on a conference in, I guess, Lonavala. So this is the time that we took picture. And this is my other group members. So we used to go and sit here and drink tea, and there was a Hanuman Mandir just above us. So, okay, so I go behind, and now I would like to share Ottawa in a glance. I will not make a bore presentation. I hope you will like this. So Ottawa in a glance. So this is Ottawa is in summer. It's a downtown. And when it comes to the fall, so we have a pumpkin season. So these are my twin son and their friend, Rylan. And just to give an idea how big they are pumpkins, so you can see these pumpkins are really big in this, and bigger than that, those of actually what you're seeing here. And then in winter, so what you are seeing a largest rink, skating rink in the world, which is available only in the winter, open rink. So basically it's a canal which freezes during the winter for 2 months almost, and people enjoy their skating skills, like all level, all beginner or all experts come and they enjoy their skating in open air here. And then we have a spring season. We recently had a tulip festival. So Ottawa is known for the tulip. But the season is very small for the tulip, just 2 weeks. So now I come to the reactive oxygen species. So you all know that we have in atmosphere 21% of the oxygen, what we actually call the molecular oxygen. And what is then reactive oxygen species are? So basically, by definition, those are a molecule containing one oxygen at least atom and unpaired electrons, one or more. They are very reactive. Reactive means compared to the molecular oxygen. So there are several kind of reactive species. So I will be talking about here only this, sorry, wait a minute. The singlet oxygen C. So I will be focusing on the singlet oxygen. So let's go. So is there a triplet oxygen? Yes. So the molecular oxygen is a triplet ground state, which is, as a photophysicist, and you must have heard that the ground state is always singlet, but the oxygen, molecular oxygen is an exception where the electrons are parallel, the ground state. And their lowest excited singlet state, it becomes like anti-parallel. And this is the first their singlet excited state, and then the second excited state. So this is very useful in many cases. We'll see further. So how we produce singlet oxygen, Dr. Pandey already described it, but again, I will just go. So there are two types, type 1 and type 2. I will just give a brief introduction. So this is called Jablonski diagram. So type 2 is basically, I just mentioned it before, say in the beginning, it's energy transfer. So now I'll explain. So when you have a molecule in the ground state, you shine the light, it goes in the higher excited state. It can fluoresce, it can go to the triplet state, and then phosphorescence from there. And when the population is here, the molecular oxygen is here, so it's a downhill in energy, so there is an energy transfer possible. So then, because of the energy transfer, this molecular oxygen reaches to the singlet and higher and excited state, which is called singlet state, and then it can go to the S2 state. And then this also emits. So this is called the singlet oxygen phosphorescence, which is a characteristic peak at 1270 nanometer, which is that's how you probe that you have a singlet oxygen or not. Means there is other way of to, but this is the one of the, like what you call this, a fingerprint, 1270 nanometers phosphorescence. Though detection is sometimes limited because everyone doesn't have that kind of NIR PMT. but the instruments are available and we have it. So this is a, here you see the blue curve. This is a singlet oxygen phosphorescence, which peaks at around 1270. So I'm not talking about the red one, this, but it's some from our paper, which is recently we published in ChemCom. So we excited our this probe or photosensitizer with 335 nanometer, 6 nanosecond pulse width. And for our photosensitizer rose Bengal, a known sensitizer for singlet oxygen. So remember, so this is a transition from excited singlet to the triplet emission. So this is that makes it unique in terms of if you are interested in the physics and photochemistry. So this is something more about singlet oxygen that we actually utilize these parameters. So in different solvent, it has different lifetime. In dimethyl formamide is 15 microsecond, in acetonitrile 50 to 60 nanosecond. In water is very short. And the diffusion length, how can it diffuse? Because basically it's a gas, okay? So it diffuses a maximum in the acetonitrile, which is around 500 nanometer. So now we go for another deep dive. So we'll talk about something about type 2. That's where we produce our ROS, like reactive oxygen species. So type 1 is energy. So I'm okay. So basically, I explained the type 2, which is energy transfer, but type 1 is we call it hydrogen atom transfer or or oblique electron transfer. So what we need for this kind of hydrogen atom transfer, electron transfer, we need something, a substrate. In this diagram, you see a biomolecule. It can be any organic substrate or any bacteria or anything, any cell or any just a normal organic compound. So this organic compound, the triplet states are highly electrophilic. So there is an electron transfer. Sometimes the hydrogen atom transfer happens, and then the radicals are produced, and then further ROS are produced. So just to give you an example that we are, so in other terms, so one energy transfer mechanism belongs to the photophysics, and hydrogen atom transfer and electron transfer, where we produce the radical and then ROS, that's basically fall in the photochemistry category. So here is it's a work in under progress. So we have a photosensitizer. We excited, it goes to the intersystem crossing, then triplet. And when it is a triplet state, we have so this benzene ring attached with the alcohol and the methyl group. Basically, you can call it as a cell or a substrate or algae or a bacteria. Just consider it as an organic thing. So this organic thing, what happens here? So basically, hydrogen, so one hydrogen atom is transferred to DT and it becomes DTH radical, and itself it becomes another radical. And the oxygen present in the atmosphere and in the solution that reacts with the radical, and that makes it another phenol to ketone product, and another ROS is produced. So that's how this is the another type that you produce the ROS. So that's okay. It's okay. We know how we produce, but what do we do with this ROS? So Dr. Pandey has given one direction. So let's see what we have in other direction. So I will tell you if you have a time. Okay, wait a moment. It started already. Sorry. So just listen to this guy. So just I'm pausing it here for just to let you know. So Nelson is in our team. He's a master student, by the way. So he made a flash presentation for me to explain what we can do with ROS. Go ahead.
Hello, sir. Yes, sir. Just, is
Audio,
there any audio also
audio
to
is
this video?
Oh, is it not available there?
audio is not,
No, no.
it's not
Oh,
audible.
I'm sorry. I thought this is coming. Oh, sorry. Wait a moment. Okay. Hmm. How do I do that? Okay, let's. I rather skip it. I'll just explain. I thought there should be the voice. Okay, so I'll skip that part. Okay. So basically, that guy was saying that we use titanium oxide. So basically, are you listening to me now? Hello.
Yes,
Yes,
Hello.
yes, yes, yes.
Okay. So yeah. So I skipped that part. I don't know why the video's voice is not translating to there. Anyways, so what he was saying, I'm just summarizing here. So if you have ROS and you have any organic substrate, any biological molecule or any microbial substrate, so basically it decomposes the organic. Or you can, if you are working with a biological sample, you can say it goes to the cell death. So photodynamic theory. So I will take a detour from here and I will go to the left and I will work to talk about the water treatment. So for water treatment, what we need a photocatalyst or photosensitizer, basically a light absorber. And what method we choose? There are two methods basically, homogeneous and heterogeneous. So homogeneous, basically what it means, you take a photosensitizer and dissolve it. Basically everything is homogeneous, everything mixed with each other. But that's not useful for the photo treatment. We need a heterogeneous but flow. So what I mean when I say, so let's talk about what kind of catalyst we need. We should have a flow compatible photosensitizer, should absorb visible light. Basically the ultimate idea to put this device in the sun. It should be photostable, it should not degrade itself. And cost effective, of course. If we have to implement a technology, it should be cheaper. So what water treatment is not helpful until it's a flow. So basically it's a schematic diagram. So here in the labs, in the lab environment, so we have a sample, basically some pollutant, polluted water. We have a peristaltic pump, just a pump that goes, and here's the tube. If you see inside the tube, we have a catalyst, kind of a strip, and we shine the light. The that's photocatalyst and the light creates ROS. They kills the bacteria. They purify, they decompose any organic pollutant, and then you put to something to check what we are doing. So we use the spectrophotometer and we check the absorption, like what we do actually in our lab. So we started. So as my background is from Nainital and we do a lot of polymer film work, so I gave my feedback to the team and we said, let's do polymer thing because this is actually what we need. So we made a polymer doped photocatalyst. So I'm sorry, and I want to apologize here. I cannot tell every information because these are industry collaboration projects. So until I have their permission, I cannot tell what actually we are putting in them, but I can show more or less what we do. So these are polymer films. So here in the right side or the left side, which is transparent, there is a plastic film that is a PMMA film. And in the right side, we have the same solution, which is an anthracene dissolved in water and a photocatalyst uh, inside a polymer film. So there's a plastic film doped with a photocatalyst. And we do this kind of experiment. We put under the light, white light, visible light, and we see what happens. So basically this is a thing that's going on in here. So it's a fan. So that fan takes away the hot air and we go. So this is what's happening. So this is a very busy slide. Just I'll walk you through with this. So on the left side, where you see this multiple peaks, absorption peak, it's anthracene. It's a very known structure or known molecule, and their known absorption spectrum. And this the purple spectrum, it's the absorption of a PMMA and a doped with photocatalyst. And this is, which is the what do you call it? Which color? Anyway, I would say pink. Pink color spectrum. This is the spectrum of our light that we were using, that we were irradiating with. So this is the two white light we were irradiating about 92,700 milliwatt per meter square. So and this is the black line. What you see is the just neat polymer film, like we call it the control experiment. So I want to take one moment to why we choose the PMMA. So PMMA is very hydrophobic. So we can use it in a flow setup. And it's transparent to the visible light. And third thing, the flexible. So we can put in any shape for our purposes. So in the 0 minute, this is when the light is off, it's here. But as we turn on the light, you see this keeps on decreasing. What does this decrease represent? It represents this anthracene reacts with singlet oxygen, which is produced by this photocatalyst, and makes something is non-anthracene or degraded, basically. So that's what we see. So and then we call it what we saw in the previous slide, we call it a bench experiment. Then when we saw a bench experiment is successful, so then we use it in the flow. So here you can see I was talking about the diffusion before. So what is happening actually? So the diffusion of the singlet oxygen taking place, going and killing the anthracene. So this is another same way of showing the data. So it's with time and it's a change in absorbance at 370 nanometer. So this is the dark experiment. So dark experiment basically means nothing happens. And this is a neat film, and with the photocatalyst, it decays, basically it degrades very fast. So another important factors are there is no leaching of the photocatalyst. So no leaching, what I mean, so means that whatever the catalyst is in the film doesn't come to the solution. So it stays stuck within the film. And the second thing, this decrease is not because the anthracene is absorbing on the PMMA film. So basically, why we say that? Otherwise, we should have seen something in here with the time, if that adsorbs on the surface. So this is is going on the flow, and right now what we are extending this study, we are testing ibuprofen. Like we take lots of medicine like paracetamol, ibuprofen, and I don't know more name, but they all 80% of the drug is consumed and the rest is wasted, and it goes in the sewage and in the water finally. So we are now trying to decompose ibuprofen and paracetamol using this technique. So now in another project, we are working with a water treatment with a black TiO2, basically a semiconductor. And so there are the black TiO2 and the white TiO2. So this is a strips of white TiO2 and the black TiO2. The black TiO2 is better because it absorbs almost whole spectrum. And you see there are the tubes where we insert, and I show you the schematic diagram how we do this. And here in this experiment, what we were targeting on to degrade was, so basically, and this is setup. So this is the so we call it one pass, but multiple tubes. So here something comes in, goes, and finally we see the product. It's called one pass, multiple tube. It's one tube, but it's a feedback system. So we collect, and then it goes back. So depending on kind of experiments what we do, these are the setups. Simple setups actually. And then what we are focusing here in the degrading is the estradiol. So estradiol is esterone family molecule, which is found in water river, and that source basically is the human. It from our like urine and so many other things that goes away within the water, sewage in the water. And this is also responsible to change the fish gender. So basically if you have a more estradiol in your body, so that can cause your gender change after a certain longer time. So in Canadian municipal wastewater treatment plants can reduce this, means they are working on this thing in our effluent, and we are trying to do and reduce it not just for the Canada, for all over the society, and of course for the world. So we are trying to synthesize or making kind of material we can work on this estradiol to basically either degrade or mineralize and basically change its form so that it doesn't harm the fish gender and in term and other human bodies. So this is like more or less that what we're doing here in terms of the water treatment. And there are so many things I cannot just speak about it, but I have just shown it. And this is our team in here. And thank you for listening me. And if you have any question, I will be happy to answer if I know the answer.
Thank you, Neeraj, for the interesting presentation and very useful application of photophysics and photochemistry. Audience may ask questions now.
If they have any question that comes later in their mind, they can just email me using Tiwari ji, ask Tiwari ji my email, and it's in the front in here.
Just one question.
Yes, go ahead.
Whatever these photocatalysts you are using for this water treatment, are they
Yeah.
synthetic, or is there any natural photocatalyst is there among plants or something?
Oh, so no, I'm not aware of any. So natural photocatalyst actually all plants. Actually, if you are talking about the plants, they have a photocatalysis mechanism by their own. Okay, but in general, we synthesize, we make it more practical so that we can make it for a societal purpose. So for social, like where we need, like in Africa, where we need a really water treatment and we don't have electricity, so we can just put in the water like in the sun and let it run. So no, we synthesize it. We try to make, so we come to the material part. So team try to make a material which is very efficient to create ROS and ultimately clear the water.
Okay.
Thank you.
One thing I would like to ask. So there is certain time duration for the process.
Yes.
So
It.
in case of static water body,
Mhm.
uh, the process can be done more efficiently, or when it's flowing, just flowing water.
So the idea is to we put our device in a tap, you run the water and you get the pure water. Okay, so this is the idea. So basically we want to make it more efficient for the flow. But
Yeah.
for the still water, like a steady water, if it works, is good. There is no. This is even better. Means it's like a bonus for us. But we really want to make it for practical purpose for the flow setup. That's why it has to be in a kind of heterogeneous system. So where one things stay and one things goes away.
It is a very quick process then.
It is
Uh,
quick. So
At
it
the
is quick.
production's
So
time scale, it works.
yes. So yeah. So the so this is a good question actually. So I will say. So if you want to see the overall result, okay. Suppose if I go here. mm, Here, okay. Actually here. So this is the overall reaction what you are seeing, okay, in a bulk. But if you are looking molecule to molecule interaction, this is quick, okay. So if you are just looking one singlet oxygen interaction with one anthracene molecule, it kicks it very quickly. But if you are looking in a bulk, then of course it's a slow process.
That's why I asked this question actually.
Yeah.
Yeah.
That's a good
Then
question. Yeah.
the way we use RO water, it gets cleaned up with the system like that.
Yes, that's true. But RO is mostly basically use the UV light. That's the thing. They don't use the visible light.
Yeah.
And yeah, so we are trying to use the white light, solar powered, those kind of elements are like, that's why my headings are green. So we are moving towards green thing, like more sun, more less green chemistry, you may say. Green
So
application.
can something be done that natural light itself start
Yes,
the
yeah.
cleaning process?
Yes. So I haven't shown those results. We just put our setup in the roof or outside, and we get the results. And
That's
depending on the weather, depending on the like snow condition, not snow, but like what you call cloud condition. Yes, we see the results.
But in India, it will be generally useful. Huh?
Yes.
There is one more question, yeah, from just okay. There are certain questions. One from Khushi, another from Sachin. Uh, how to get pure oxygen using air from ozone breakdown?
Uh, Frankly speaking, I don't know.
From
So I'm
ozone
not
breakdown.
I'm not that good chemist to answer that question, but I'm a good photophysicist to do some photochemistry. That's my answer. But I really don't know what reaction happens and how it goes. I don't know.
Other is about intracellular singlet oxygen.
Intracellular singlet oxygen is okay. So we are now what we are
Detecting
doing,
intracellular singlet oxygen.
yeah. So
So
what we are
DPBF and ABDA be used.
okay. Yes.
That,
So there are ways to create the singlet oxygen. One is the biological stress where you the NADPH and this the one you are talking about, and then we are interested in the light. So light creates our singlet oxygen. Our main focus, like our team, is more focused on the light creating singlet oxygen, and only that ROS, not all ROS.
okay. Sachin has a question.
Yeah. Hello, sir.
Yes.
Actually, I had a question regarding most of these like I was actually visiting one of these lakes in Bangalore, which is considered to be a lake city at one point of time, but not anymore, because of these real estate people. They are kind of using some kind of a vegetation which dries up the lake, and then they can gobble up the whole land to make their apartments and things like that. So is there anything you're working on those kind of aspects as well, or
Yes.
like something
So
can be? Yeah.
no. It's a relevant question and relevant to the not only Bangalore. It's everywhere actually.
Yeah. I mean, I'm just give an example.
Yeah. So yes, we are working on those things. So idea is that we create that kind of photocatalyst, okay? And so basically, the one thing, it's kind of almost impossible to clean all water, okay? But there are steps, okay? So steps means if we get the water from river, we can clean that water. Like but we just cannot clean the river, or we cannot clean the lake. It's almost means there is more other strategies they are applicable, but we are basically more inclined toward, if the water comes for drinking for human, then we want to clean that water. So we are working, so basically we are narrowing down water coming from river, then we have to clean it. So we are not actually just putting everything in river. So we are taking water from river and then trying to clean it to make it drinkable. So, so your question is relevant, but actually we are not directly working on that direction. We are not putting anything in the river or the lake just to clean it. No, we are at least now we are not doing it on those.
Okay. Thank you, sir.
Thank you, Neeraj.
Okay.
I would like audience to open up their cameras so that we can have a virtual group picture. So hope some of my teammates are taking pictures. Thank you, Neeraj, for this illuminating talk and extending your time.
Thank you very much for inviting
we
me.
will seeing you later also, if possible, during presentations, if you can make up.
It
Okay.
seems now, it seems very hard to me now.
Okay.
So I'll have to leave very soon.
Yeah, but that will also take some time. So we will see. Okay.
Okay. Just message me. Okay.
Yeah. Okay. Oh. So our next speaker is Professor Hitesh Mishra. Professor Mishra, is he available? I think.
Yeah, I am available. Yeah, Neeraj bhai.
That's very nice to see you. And I would like to thank Professor Mishra because he has helped us a lot in organizing this conference also. He is working with us in this quick adventure, I can say. So Professor Mishra is also from Photophysics Lab, Kumail University, Nainital. He later worked at the Indian Institute of Science, Bangalore, and prestigious Institute of Fluorescence, Baltimore, USA. Presently, he is a professor in the Department of Physics, MMB VHU. He has requested me not to go in detail in the introduction, but still I would like to say a few things, like he has done groundbreaking contribution to ultra-fast time-domain fluorescence spectroscopy and microscopy, laser and molecular spectroscopy, electronics and photonics, and electronic structure calculations through computations. Thank you, Professor Mishra. I hand over the virtual mic to you, and thank you.
Can you see my slides?
Yes, yes. Yeah.
Okay, okay, okay. So thank you, Neeraj Bhai, and Neeraj from Canada, Sachin from USA. It's a very nice to see you. Okay, and very good lectures, Professor Pandey from Buffalo. Very nice to meet you. So now I thanks the organizing committee to give me a chance to present some part of my research work. This is basically this work is basically done by my student, Dr. Hemlata Bist. She is working as a STEM professor in Bageshwar. So this is the part of her research work. So the topic of my presentation is photo-induced excitation energy transfer of migration in some fluorescent organic semiconductors. Okay, so I will show you the results actually. So the outline of the talk is like that. So what are the fluorescent organic semiconductors? Here I am taking 6 kind of molecules or polymers and their combinations to study the energy transfer from these molecules like aluminum quinoline and tips pentacene. Aluminum quinoline is an N-type semiconductor organic molecule, and the tips pentacene is a P-type material. This is a polymer, fluorescent organic semiconductor polymer. In the second one, I will take two P-type of molecules. So the two kind of F8BT is a polymer, fluorescent polymer is a P-type, and tips pentacene is a P-type. And the third one in the case of AlQ3 and PCBM. This is the N-type material. Okay, and I studied this thing in the solution only because a lot of people the working in the field of material science, they are making the devices by these organic molecules or polymers. But on reviewing the literature, we find that the photophysics of this molecule is not clear. Actually, the molecule in which this the material which design this molecule, the polymers, the solvent in which they make this polymer, the photophysics of these molecules not clear. So therefore, we started this photophysics of this molecule in this pair of molecules in solvent first, and then we make some devices. So I will show you some of my results like that. So all of you know that the long back in 1963, Pope and in their work co-workers, they found the electroluminescent anthracene molecule. Anthracene is a 3 benzene rings, they are fused. And in their crystal, when they make the crystal, they find they are, this was electroluminescence. Very interesting. And after that, some people started to work on the polyacetylene molecule, and they found their electrical conductivity is enhancing the system when they dope this system in the molecule solution, or they make the thin films of that one. So the 2000 Nobel Prize go on that thing, and we all are aware about these scientists. Why organic electronics? Because it is assumed that up to the 2027 that there is a 330 billion dollar market in the coming years, and there are huge application in the field of the memory devices, development of the display devices, power devices, and the sensors. And there are huge publications are coming out in recent years in the development of these devices based on this kind of fluorescent organic semiconductor molecules or polymers. There's a huge application also in the development of AI, self-healing, spintronics, and medicals. So what are the basics of the conductivity in this fluorescent molecule? We know that the organic molecule that contain pi conjugated systems, in that case, the electrons move in these pi bonds that contain singlet and doublet in alternative form. The molecule that contains singlet and double bonds, single and double bonds in alternative way, the pi electrons are started to move. And this create conductivity. Okay, in the some examples of these molecules are this polyacetylene, polyphenylene, and polythiophene, like they are the pi conjugated polymers. And some examples related to the molecules, small molecules, the AlQ3, pentacene, or pentacene. Okay, just a minute. And what about the band gap? Actually, the band gap in these molecules, or organic semiconductor polymers or molecules, the band gap is very less than 3 electron volt. And electrical conductivity lies -9 to 10 to the power 2 ohm per centimeter. nowadays people want to improve the efficiency of these molecules or the efficiency of these devices. For improving the devices, they are adding nanoparticles, plasmonic materials like that. Here, what we are doing, we are added the energy transfer process to enhance the efficiency of these devices by adding 2 or 3 molecules together in the device formation. So before starting the work, I will show you what is the basics of the energy transfer. You know the Jablonski diagram, you know the photophysics of the molecules, they are explained by the Jablonski diagram. Here I am show some modified version because this is the donor molecule, there is not electronic energy transfer. This is the electronic energy state diagram of the molecule. When they absorb radiation, they fluoresce and sometimes they transfer the energy to the acceptor. They can transfer the energy to the acceptor by 2 ways, radiative or non-radiative. And along with this, there are 2 kind of process that takes place: Dexter kind of energy transfer or Foster kind of energy transfer. Okay. So how will we get generally the energy transfer phenomenon, whether the FRET is taking place or not? For the FRET mechanism, the essential thing is there should be overlap between the emission of the donor molecule and absorption of the acceptor molecule. Okay, and this is the diagram. This is the in this diagram the overlap area. We find out this overlap integral by this formula, and critical transfer by this formula. And the rate of efficiency we can find out. This is the R0 critical transfer distance upon this formula. So what is the rate? Actually, in this case, if it is the dipole-dipole coupling, if it is the resonance kind of dipole-dipole FRET mechanism, then the distance, the rate is directly proportional to the 6th power. Okay, so in the case of the excitation energy transfer, its range may be from the picosecond, nanosecond to the milliseconds in organic molecules and inorganic molecules. And in the radiative energy transfer, generally what happens, donor molecule absorb radiation when they emit that emitted photons are absorbed by the acceptor molecules. But in the case of the non-radiative energy transfer, in the case of the non-radiative, there is some interaction takes place in the donor and acceptor in the excited state, and the resonance energy transfer takes place. And the resonance energy transfer is again 2 types: short distance and long distance. Long range distance, so dipole-dipole coupling and dipole-quadrupole or multipole coupling. That is the Dexter. So the molecules which I am using here, their structures and their basics are I presented here. The aluminum is the N-type, TIPS penta is a P-type, and PCBM is a N-type molecule. PCBM is a derivative of carbon-60 actually. And MEHPPV, it is again a P-type molecule, and F8BT is a P-type fluorescent molecule. The whole work deal with the fact here I am presenting is the solution phase. And this is the initial precursor of the device solution. Basically the chloroform solution is the initial precursor of the device for making the thin films and devices. Okay. And this kind of research work, there is a development of organic field effect transistors, organic photodetectors, or organic solar cells, optical sensors, optical light emitting diodes, and lasers. This kind of system is in this kind of system we are working here in BHU Varanasi. So first part of work, this published in 2021, the photo-induced excitation energy transfer between ALQ, this is N-type organic semiconducting molecule, and to the P-type polymer, TIPS pentacene, P-types fluorescent organic semiconducting molecules. So this is the absorption spectrum of aluminum quinoline. This is a very famous molecule, and this is the concentration effect. When we normalize it, we observe that there is no change in the absorption spectrum. Okay, it means that there is no dimer or oligomers formed in this molecule when we increase the concentration. And when we take the emission spectrum of that, a different concentration, it looks like that. And when we normalize it, there's no change in the emission spectrum. It means there may be very less if there is energy migration. So it is very, very less. Otherwise, there is no energy migration, or there is no any excited state excimer or exciplex formation takes place. So molar absorption coefficient of this molecule is very good, and the Stokes shift about 6,837. Actually, in this molecule absorb radiation. This is the ligand to metal to ligand energy transfer band. This is the ligand to metal charge transfer band actually. this 380 nanometer band in the transport. ELQ is most widely used for the host materials, and it is the excellent stability and electron transport ability. And this is the TIPS pentacene photophysics. TIPS pentacene absorption looks like that. When we normalize, there is no change in the absorption spectrum. This indicates that there is no ground state diamond formation takes place. But in the emission spectrum, when we excite the same sample with different concentration, so look, there is a shifting. Very low concentration, if we have two peaks, but when we increase the concentration, this band is shifted. This indicates there is possibility of energy migration due to the overlapping. And this absorption spectrum, this shows the vibronic absorption spectrum. This is the first excited state having different vibrations. TIPS pentacene has already extensively investigated by electroactive part of the different photonic devices due to its high hole mobility and photostability. This is the lifetime of donor molecule and this LQ3 and acceptor molecule pentacene. The lifetime of this molecule is very large, 17.16 nanosecond, and the lifetime of the acceptor molecule is 10.6 nanosecond. Okay. This is the overlap absorption and emission spectrum of donor, acceptor, and donor and acceptor, donor emission and acceptor absorption. So here, in this case, the overlapping is very less. Therefore, energy migration is not taking place in the donor. But here, in the case of the acceptor molecule, the overlapping is very large. Therefore, there is a possibility of energy transfer. Energy migration takes place. And here, in this case, in the case of energy transfer, what is the difference between energy migration and transfer? Migration means energy transfer takes place in the same kind of molecule, and transfer means energy transfer takes place to different kind of molecules, donor and acceptor. If donor, then this is the energy migration. Okay, and these are the alpha and beta. They are the interaction parameters, strength of the interaction between donor and acceptors. So we find that the critical transfer distance in donor acceptor is about 10^15 per nanometer per meter centimeters. And the critical transfer distance is about 42 angstrom. Look, when we are increasing the concentration of the acceptor in the presence of the donor, this is the absorption spectrum of the donor, but in the presence of the acceptor molecule, the intensity of the vibronic absorption band is increases. But in the emission spectrum, what we observe, the intensity of the 500, nearly 500, this is the 500 emission is the emission of the donor molecule, aluminum quinoline, and its intensity decreases on increasing the concentration of acceptor molecule. And here, the intensity at the 630 onward, the intensity of the peaks are increases and with redshift. Okay, what our observation is the intensity of the donor is decreases, intensity of the acceptor is increases with redshift, and at very high concentration, the donor emission is got some structures. Some structures started to take place. The reason behind that, the intensity decreasing of the donor means energy transfer takes place from the donor to acceptor. Energy is increasing of acceptor means it is getting energy from the excitation energy from the donor molecule. And if there is some change in the donor emission at very high concentration, this indicates the radiative energy transfer. Okay. Now the lifetime data. The lifetime of the donor is single exponential 17.16 nanosecond, but in the presence of the acceptor molecule, the lifetime is best fitted in the Foster equation at high concentrations. And this is the critical transfer condensations and the -5 mole. How we will distinguish when we are fitting this data, the decay data, the middle one, when we fit in the single exponential, chi-square is very high, and then double exponential, even it is single exponential high, even in the second exponential it is also high, 1.17. But when we have fitted, in the double exponential 2.33, and in the single exponential single exponential 2.33, double exponential it is about 1.53, and in the presence of the Foster fitting, the chi-square is best, and distribution of the residuals is also very good. So this indicates that Foster kind of energy transfer takes place from donor to acceptor. Okay, and our at low concentration, our equation, the decay equation fitted in this equation, a diffusion equation, and at high concentration, our equation is fitted in the Foster kind of equation, and this is the gamma in the reduced concentration. these are the observations of the observed and spectroscopically calculated values, and we find that at very high value of the concentration, these values are started to resemble observed value and spectroscopic values. So in this, when we plotted the concentration along with the efficiency of energy transfer, we divided this region. We have got this kind of a spectrum, the curve, and we divided into 3 parts. The first part, at very low concentration, regime efficiency of energy transfer and rate of energy transfer do not significantly due to dominance of donor diffusion. But in this case, in between the dot lines, the second regime, where the rate of energy transfer and efficiency of energy transfer drastically increase, indicating direct donor acceptor energy transfer. And after that, after 10 to the power minus 5 mole concentration of TIPS pentacene, higher than that, the higher concentration, the rate of energy transfer and rate of efficiency of energy transfer appears to be saturated, because stationary molecules of the donor acceptor pairs are formed in the excited state. Because there is a possibility there's these 2 molecules, p-type and n-type molecule, they diffuse and combine. When they diffuse and combine in the excited state, they form a diffusion layer. As simply when we take the p and n type of diode materials, when they combine, we got a depletion layer. Okay, by that. And when we plotted the curve of acceptor concentration, which rate of quenching of the lifetime, we found that this is the formation of the diode. Actually, when we analyze the data, we found that the donor decay, when we monitor the emission 500, but the donor at the peak intensity of the donor, the lifetime of the donor decreases like this, while the lifetime of the donor acceptor is also decreases. There are 2 double exponential fitting is there. One is the donor acceptor. This is the formation of the complex in the excited state. Okay, this is the saturation started takes place, and this is the curve which shows that on increasing the concentration, the rate of quenching is started to first decreases and then it's getting saturated. But at 650 and 375, the Stern hormone quenching plot looks like this. Acceptor, and for the acceptor emission, it's 700 nanometer, 650 nanometer, and at 700 nanometer, we are getting a straight line. And the rate of Stern hormone quenching and decay quenching efficiency is about 1.7 to the power 12, and Stern hormone quenching is 2.9 to the power 4 per mole. So by this, we get the Stern hormone quenching plot for the excimer turns in for a non-linear 550. Earlier we saw the 5 linear, it is at 550 nanometer, it is non-linear Stern hormone quenching plot. It becomes the linear, representing only the site contribution of the sites that are not readily available for the quencher. So when we plotted the curve of donor acceptor mixture of the emission spectrum with peak fit analysis, also indicates that a very low concentration of the excimer is very high, this D star A, but on increasing concentration of the donor of the acceptor in the presence of fixed concentration, the intensity of the excimer decreases. This is support the lifetime data. So it means that we are getting the emission from the donor, we are getting from the emission from the acceptor, and donor acceptor combination, excimer formations emission we are also observing. So this is the lifetime data of the acceptor, and we are getting the lifetime of the we are observing a rise time also in the decay of the acceptor. Here is the amplitude is negative. This negative amplitude in the rise shows the rise time when we are monitoring at 650 nanometer. This means energy transfer. This is also support that energy transfer takes place from the donor to acceptor. So this is the final energy level diagram. I represented this the whole work in an electronic energy level diagram. And interesting is that when we excite the donor molecule, it transfer their energy to MLCT state. This is the emitting fluorescence state of the molecule, and it forms the excimer. Form the excimer, and this excimer and the energy transfer takes place from donor to acceptor. So this excimer also emit, and the acceptor also emitted. Okay, so this is very interesting work. So to understand this, a mechanism of excitation along with the excited propagation between the compound and opposite polarity. to understand whether there's this kind of excimer form in the 2p type of molecules or not, we studied the 2p type of semiconductors, because in the n and p type there is a possibility of formation of the excimer. But what happened in that case of the 2p type or 2n type of molecules? So for this one, we studied this F8BT molecule and this dipsopentacene. Both are the p-type molecules. So this is the p-type semiconductor polymer, and this is the molecule. And this work is published in Journal of Physical Chemistry B. So this is the absorption and emission spectra of pentacene and F8BT polymer, and this is a very good. It has very good absorption bands here at 554 nanometer and 320 nanometer, and it shows a very bright green emission. So in maximum at 547, very less stroke shift. F8BT is the electron donor acceptor p-type semiconductor conjugated polymer copolymer derivative of polyfluorine. It consists of fluorine and the electron donor and benzothiazole as the electron acceptor unit. Due to the presence of delocalized electron in the backbone of the conjugated F8BT, shows strong stacking interaction, elective charge carrier transport, and enhanced electrical conductivity. And this is the lifetime of the F8BT molecule. Its lifetime is very small. It is about 1.1. It's about 1 nanosecond. Okay, both at the 550 nanosecond and 730 nanosecond. Okay, and this is the overlap integral of the donor itself. F8BT itself, its overlap integral is very less, but overlap integral of the donor and acceptor is very high, and critical transfer distance in the case of the donor and acceptor is about 53.12 angstrom. Okay. Now the results, the absorption spectrum results in the when we are changing the concentration of the acceptor in the presence of fixed concentration of donor. Look, very interesting results we are observing. On increasing the concentration of the acceptor, it looks like this. This is the concentration of the acceptor we are increasing, but emission spectrum we are getting very good interesting results. The emission of the donor is decreases. F8BT emission is decreases and started to get some structured emission. And this structured emission in the case of the donor in the presence of the acceptor at high concentration indicate that there is a radiative energy transfer. But here in the case of the acceptor emission, the fluorescent intensity of the acceptor increases along with the red shift. This means that there is an energy migration and energy transfer, both are taking place. Okay, and when we are plotted the lifetime decay time curve of the donor in the presence of acceptor, we observe that the decay of the donor is decreases and best fitted in this Foster equation. And when we are plotting the energy transfer efficiency with acceptor concentration, we are got this kind of diagram. The first one is the Foster one, the black one, and the red one, and is the spectroscopic values, and the LAF is the Huber and this LAF theories. So at higher concentration they are matched, but at the lower concentration they are not matched. It means their diffusion can also take place in this molecule at lower concentration. Okay, so I'm not going detail, and this is the acceptor decay dynamics. Here we also again get a rise time in the decay of the acceptor molecule, and the wavelength of decay where we are positive is 730. Okay, and we are getting both the lifetime of the donor and acceptor and the rise time also. This rise time indicates that energy transfer takes place from donor molecule to acceptor. This is again proof that. But in this case, we are not getting any excimer formation kind of things. This is interesting. Okay, so this is the mechanism of energy transfer between the 2p type of semiconductors. As we know, when we take the 2p kind of semiconductors with joint, there is no deflection layers found. So in the solution also, we are getting this kind of results. And there is a huge application of this FLEC mechanism to improve the efficiency of photovoltaic devices. The third one is the FLEC between two N type of molecules. Here we take the aluminum phenol as a donor and PCBM as an acceptor molecule. In this case, we got a very interesting photophysics of PCBM. Actually, this is the absorption spectrum of PCBM. It is just related. This is nearly at the absorption spectrum of carbon-60. And interestingly, that when we increase the concentration of the PCBM molecule, the absorption in the visible region is very weak, and from 200 to 400 meters absorption is very strong. Okay, so in this case, there is no any ground state formations take place. It means it is not forming any kind of dimer or agglomerates. So it is not forming in the ground state. But when we take the fluorescence spectrum of this molecule, when we excite it from 375 nanometer, it shows two emission bands. One in the range of the 400 to 500 nanometer, and another one from the 600 to 700 nanometer. Okay, and when we excite it from the 500 nanometer, we are getting this from 600 to 700. Again, this kind of emission spectrum. And interestingly, when we are increasing the concentration, earlier when with very low concentration, the intensity of the 650 nanometer is higher as compared to the 700 nanometer. But on increasing the concentration, the intensity of this band, 650 band, is decreases, and intensity of this 720 nanometer intensity increases. This indicates that without donor, here I'm talking about without donor, we are getting three things very interesting. First, it gives this form the monomer, and this monomer form the dimer in the excited state or increase in the concentration. Second, we are getting the excited state emission also, and this emission comes from the charge transfer state of this molecule. The CT emission, and this is the monomer emission, and this 700 band is the excimer emission. Again, the lifetime analysis at different emission peaks. At 430 nanometer, we get 3 lifetimes. Average time is about 1.78, and at 650, we are getting only single lifetime, and it is about 3.08 nanosecond. But at 720 nanosecond, the lifetime is about 3.10 nanosecond and 1.47 nanosecond. This indicates that the lifetime of the excited, the CT band is about 1.78 nanosecond. The lifetime of the monomer is about 3.08 nanosecond, and the lifetime of the excimer is about 1.47 nanosecond. Now, the energy transfer work related to these two molecular system. So, donor aluminum can behave as a donor, and this PCBM behave as an acceptor molecule. The critical transfer distance we calculated about 27.81 for this overlap, and in the emission spectrum, what we observe on increasing the concentration of the acceptor molecule PCBM, the intensity of the ALQ3 molecule, the fluorescence intensity of the ALQ3 molecule decreases. And here the intensity of this excimer band is increases. Look, what is the difference between these two? When there is no donor, the excimer emission is this one. But in the presence of the donor molecule, there is a 5-fold enhancement appears in the excimer emission. This is a very interesting thing. And this kind of property of this molecule can be used. This pair can be used for the making these devices, organic solar cell devices, or this photovoltaic devices, sensor devices also. And this is the time domain measurements. Again, in the time domain, we are getting the lifetime of the donor is decay donor is nearly constant, and it's decreasing, but it's not that much fast. And the lifetime of the and the critical transfer distance is decreases like this. And this donor lifetime in the presence of the acceptor fitted well with the Foster equation. And this is the acceptor decay dynamics. Here in this case, we are not getting any rise time, but because the rise time is very fast and our estimates might be not detected, but we get the lifetime of the donor. It looks like this, and in the case of the monomer, lifetime is fixed, but the lifetime of the and this is the tau d is the lifetime of the this is the lifetime of the tau is the lifetime of the excimer, tau m is the lifetime of the monomer, and tau d is the lifetime of donor. The donor lifetime is decreases, while the lifetime of this is the same, and the amplitude of this tau e means excimer emission. Excimer amplitude is increases. It means excimer is forming more and more when we are increasing the concentration. So in this way, our time domain meter very well correlated with the experimental finding in the spectroscopic measurement, absorption and emission. So in conclusion, when we are plotting this diagram, so in this case, energy level diagram, so this is the donor molecule Q3. When we transfer the excitation energy to the this PCBM, it forms the excimer. The first pairs in the first pair, they form the aluminum quinoline and tips pentacene, they form the exciplex. But here we are getting the excimer emission. Okay, and the emission from the acceptor itself. These are some uses, some application part which we publish in some papers, and these are the devices which we make with this is ZNO quantum dots and tips pentacene. So look, this is the absorption. The black one is the absorption in the ZNO quantum dots, and the blue one is the absorption spectrum of tips pentacene. Here, emission, there is no emission appearing in the case of the tips pentacene when we excite, because the concentration of the tips pentacene is very less, and there is a very thin layer of this on the device. But and the concentration and the emission of the this is the red one is the emission of the aluminum. This is the emission of the ZNO. The ZNO emission is very strong, and the emission of the tips pentacene, there is no emission of tips pentacene, but in the presence of this ZNO, when we are doping this ZNO quantum dots, the intensity of this one is decreases, and we are getting the emission from the tips pentacene. This is very good. And this is the responsibility and detectivity curve. And this is also proved by this time domain measurements. Okay, so this is the lifetime. The first one is the decay curve of this ZNO. In the presence of this tips pentacene, the ZNO lifetime is decreases. This again proves that the energy transfer takes place. And this is very good system because without because here at 700 nanometer, there is no fluorescence from the tips pentacene, but in the presence of quantum dots, its fluorescence density increases a lot. The second one is the fabrication of ZNO quantum dots for FNBT and tips pentacene heterojunction based UV visible photodetector. It is based. This is based on this hopping of the energy, because this ZNO quantum dots transfers energy to FNBT, and FNBT then transfers energy to the tips pentacene. So these are the absorption and emission spectra of the device. And this is the transient response and the responsive detectivity of the device which we fabricated with MOX, without MOX, and with MOX. Okay. So in summary, in the case of the excitation energy between aluminum quinoline and tips pentacene molecule, diffusion and strong interaction of the donor acceptor molecules was found and modulate the Fred dynamics by the formation of exciplex. In the case of the two p-type of fluorescent organic semiconductors, F8BT and tips pentacene molecules, radiative and non-radiative energy transfer takes place. In the case of the two n-type of molecules, it appears that energy transfer occurs via Fred mechanism and thereby the five-fold enhancement in the excimer of the emission of the excimer. Anti-Casa emission at the blue edge of the wavelength region does not participate in the Fred dynamics. The organic semiconductor device of these bands are widely reported in the literature, so the detailed knowledge of the energy transfer and its outcome will help to upgrade the optical and electronic properties of the devices. These findings will have implications concerning the application aspect of the choosing suitable donor and acceptor materials and its concentration to exploit energy transfer in fluorescent semiconductor pairs in the development of various photonic devices. Potentially, this study might help to have deep to understanding the mechanism of Fred from the viewpoint of improving performance of photonic devices. I thanks Dr. Hemlata Bist. She is the assistant professor in Kanda, Uttarakhand, and Dr. Abhinav Pratap Singh, research associate at IIT BHU. Professor Jeet, in which with whom we did some measurements regarding the device, and Dr. Professor S. Joshi, spectroscopy division from IPR. A special thanks to Professor Joshi because he helped me a lot. Thank you.
Thank you, Professor Mishra, for this illuminating talk. Audience may ask their questions. raise hands or write in the chat box. Uh,
I have a question.
Hmm?
Sir, very
मैं
interesting, very
हाँ हाँ
interesting.
हाँ नीरज अच्छा हाँ
सर मैं
यस
हिंदी में ही
नीरज
पूछ लेता हूँ, है ना? बहुत
हाँ हाँ
हिंदी बोलने को
यस
है
यस
ना?
हाँ
ठीक है ना? तो आपने बताया कि इसमें डायमर भी फॉर्म होते हैं, तो स्पेसिफिकली किस स्पीसीज का एनर्जी ट्रांसफर किस में हो रहा है, ये कैसे आइडेंटिफाई कर पा रहे हैं? मैं इसको थोड़ा नहीं सोच पाया।
किस देखो
आई मे बी आई
in the first case where one P and one N type of molecules. Okay, the energy transfer takes place from donor to acceptor molecules along with excimer formation. So
yeah.
excimer also transfer excitation energy to the this acceptor molecule. In this,
Okay.
can you catch this energy level diagram?
Yes,
Hmm.
yes, 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 yes,
है
yes.
ना? So in this one,
Mhm.
so aluminum quinoline transfer their excitation energy to the acceptor molecule, and
Mhm.
it forms the excimer at very low concentration, because on increasing concentration, the concentration of excimer increases. This part of this excimer formation, we got the information from the time domain measurements.
Right, right. Okay,
But in
ठीक.
the case of, look, there are two P type of molecules where you are not getting this excimer formation. Only the energy transfer takes place directly to the acceptor molecule. Okay. Excimer formation means excited state dimer formation. Or
नहीं,
excitoplex
right,
formation
right,
takes place in this PCBM molecule.
right.
Publish this part in general luminescence. So this one. So here that energy transfer takes place from the donor to acceptor and then to the
Yes.
excimer.
Yes,
Acceptor is
yeah,
the PCBM molecule.
sorry,
Acceptor is the
yeah,
PCBM molecule. Yes.
yes. So here, this is the lower excimer, okay? So,
Yes. Excimer is lower. Excimer is always be lower
yeah,
in the case of
yeah,
the
yeah.
formation. Yes.
So from donor, so I'm just trying to just get my clarity. So donor to the S2 acceptor, okay, or the
Acceptor,
first one, or and the excimer. So
excimer.
what are the rates or the time for this transitions for energy
Look,
transfer?
yeah, very nice. You can calculate the rates from these equations. Actually, these
I
time
see.
domain measurements. I have not measured these rates, but you can
Okay,
measure
okay,
the time domain from the
okay.
time domain measurements. I think no time, we
Thank.
are not measured the, yes, not measured, but we can find out it.
Right, right,
Okay.
right, right. Yep. Thank you.
Then it is in nanosecond range.
yeah,
Because
just in the slide you shown,
yeah, slide
donor
shows.
lifetime it also seems constant. It only a certain concentration it has increased.
No,
Like
look, intensity of the lifetime of the excimer is constant, but its amplitude increases. Look, in the
yeah,
second
amplitude is
one,
changing.
amplitude increase. Amplitude increase means
Lifetime
excimer concentration is.
lifetime is same in
It
all
should
the
be.
cases. Yeah?
No, it should be constant. It's okay. But
Yeah.
its amplitude increases means
Concentration.
the concentration is increases
Concentration.
of the excimer formation. And look, the monomer amplitude, monomer lifetime is constant, but its amplitude is decreases. It means monomer start to form excimer.
Yeah. Monomer is converting into excimer. And
Excimer, yes.
the other thing was that this charge transfer emission was blue shifted.
It is due to the radiative energy transfer. The emitted photons by the donor, they are absorbed.
Absorbed.
Yeah, by the acceptor actually.
Okay. Thank you. What is the difference between floor? There are certain questions. I will take up only the few of them. Okay. How is excitation energy transfer utilized in organic LEDs?
It improves the efficiency of light emitting.
Okay.
Like that, light in the case of the last one, look, the emission intensity of the excimer is very 5-fold high as compared to this. When we added the donor, the efficiency of excimer emission is 5-fold high. So it means the LED, what we are photonic device which you are making it is 5-fold high, more.
Other one is one simple question: is there difference between fluorescence and phosphorescence in Jablonski diagram? And these are all questions.
Fluorescence and phosphorescence is very simple one.
uh,
In Jablonski diagram,
Dr. Sapna, can you unmute Dr. Mohan Singh
donor,
Mehta? Dr. Mehta has
what is
some
the difference
questions.
between the fluorescence is the same spin state. If let us suppose you excite the molecule, go in the excited state and relax and comes in the first excited state. Okay, if the emission comes from the same spin state, that is the fluorescence, and if it is goes from the singlet to triplet and then opposite spin states, the radiation, whatever the radiation is coming out, that is the phosphorescence.
It will be in
Then the
lower
lifetime of the
energy,
phosphorescence is
energy-wise, it will be lower. So,
is the millisecond or microsecond or seconds, but the lifetime of the fluorescence is very high in the organic molecules, so it is the life decay time is about picosecond or nanoseconds.
Dr. Mehta has some questions.
Okay,
Yeah,
Dr. Mohan Mehta ji, yes.
first of all, I must thank
Mohan Mehta ji, please
Dr.
open your
Fission.
screen also, video.
Okay, I'm in the house, so you know the condition. So anyway,
Okay.
I have the basic question regarding the energy transfer. So
Uh-huh.
if I see the slide what you shown here,
Mhm.
so if we see the acceptor absorption and donor emission, so the left and the right parts. So the donor emission energy must be the higher than the acceptor absorption energy, right?
Definitely,
But
definitely.
the spectrum is in opposite. We are getting the opposite spectrum. So in one paper, I read that if this is the case, energy transfer cannot be possible. I don't know if it is true.
I couldn't catch you. I couldn't catch you.
So if you
What do you
see
mean
that
by?
overlap of the absorption and emission, so the absorption means the donor, right? The donor emission. When donor will emit, then only the acceptor will absorb, right?
Yes, yes.
So the donor emission should be at the higher
Right.
energy side than
Yes.
but if you see the overlap part, so this does not looks this is opposite. If you see the peak to peak. So in one paper, exactly, people are using as energy transfer. But in one paper, they have specially quoted and so I don't remember the name.
I have no idea about that. But
So
here
they
it is.
wrote this kind in this situation, it is not possible to have energy transfer. What do you think?
I have no idea about that. Sorry, but
So
this is
I
the
get
case.
confused with this paper totally. The many times they clearly wrote. So have you means explored some other mechanism if this is the case?
Regarding what?
Which
The energy
particular
transfer. If we
figure?
don't consider energy transfer, so what other mechanism can be possible in such cases?
No, I have no idea. Sorry.
One more thing, when we calculate the efficiency using the steady state, I think lifetime is okay. But if we calculate the efficiency with steady state, what do you think it is? How much means correct we can calculate? Because it comes to huge amount. Just ED over ED, right? 1 minus this.
You have to make the correction of the first. You have to make the correction
Yeah,
of the donor
correction the
emission.
spectrum, right?
The correction of the spectrum. Then it will come
Using
correct.
the correction of the machine only, right? So even in this case, in one of our sample, it keeps about 80-90%. So I don't believe, though I stopped working on this. Is it true?
No, energy transfer can be 90%, no problem.
But the overlap does not show this. Overlap shows similar like your case. Means some little bit
There's
of 30,
the
40%.
overlapping means the overlapping of the electronic states. Look,
Yeah,
look, in the case of the radiative energy transfer, the emitted photon is absorbed by the acceptor. But here I am talking about the non-radiative energy transfer.
Yeah, non-radiative, okay.
Non-radiative. There is some resonance kind of things takes place in the excited state. So energy transfer, one is decreasing down, one versus it is and another one is excited.
Okay. So in your case, have you calculated the efficiency using steady state and the time resolve? How much difference you get?
In
any case, in any of the pair?
I am not finding it here.
I didn't see also.
I'm not finding it here because might be it is not calculated here, but
Just
here we are calculating the rate
how
of
much
energy
difference
transfer.
it comes.
Yes. So
Okay,
in
anyway,
different regions, we are
thank
getting
you,
different kind of things. Between these two
yeah,
lines,
this is the
dotted
formula,
lines,
I understand.
so in these
1
two
minus
dotted lines, the
FD over.
energy transfer efficiency is very high, but in the lower concentration, due to the diffusion, the efficiency rate of energy transfer is very low. and at very high concentration due to the excimer formation, it becomes a saturated.
Okay,
It is like that.
thank you. I think time is too. I think
Thank you, Dr. Mehta.
Sajid.
Yes.
Thank you so much. And I again thank the audience for being patient. So after this lecture, we will be moving to presentations. I request all the presenters to be brief, stick to the time, and focus on results. The judges for this round are Dr. Hem Joshi, Dr. Hridesh Mishra, and Dr. Neeraj Joshi. So we'll be occupying you till late in the night. So I think four
No
or five
problem.
presentations are there. One oral presentation is there, and I think 4 flash presentations are there. So 8 minutes for the oral presentation and 4 to 5 minutes for the flash presentation. So I think all the judges are present. Sapna?
Yes, sir.
Yes, sir.
Neeraj ji, please send me the list of the students.
I think I sent you just now.
There is no name of the students is not there.
No, other
Only
list.
their table is there. So it is good if you send the
Other
table
list.
along with the
One
name
is
of the students.
one is this thing. Just wait for.
हेमदा नमस्कार
हेमदा
बहुत अच्छा
प्रणाम
लगा
आज।
आपको देख। हाँ मैं ठीक हूँ। आप कहाँ अहमदाबाद में ही है?
आजकल यहाँ
कहाँ लखनऊ या अहमदाबाद?
फिर जाएंगे लखनऊ, यहाँ आ जाएंगे।
अच्छा 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 अच्छा
एक्चुअली
चलिए।
क्या था, तबीयत ठीक नहीं था उनकी, तो
अच्छा अच्छा
उसकी
अच्छा
वजह से यहाँ मेरा मेडिकल सारा इधर है, फैसिलिटी वगैरह यहाँ
हाँ
से
हाँ
आ, तो
अच्छा
इसलिए
अच्छा
चाहिए।
ठीक है बढ़िया है। अच्छा लगा आपको
मैं
देख करके बहुत
मैं
समय
आज
बाद।
हेमदा
मुझे
मैं आज
हाँ
देखिए।
हेमदा से पहली बार मिल रहा हूँ
और
पहली
नीरज
बार मिल
ठीक
रहे
हो?
स्टेज पे।
हैं।
हाँ
अच्छा,
मैं सर प्रणाम, आज आपको पहली बार देख रहा हूँ
हाँ,
मैं। इतने
फेस टू फेस
इतने
शायद
साल
पहली बार देख रहे हैं हम,
वही तो
है
इतने
ना?
साल आपके संग काम काम किया, लेकिन देखा आज पहली बार। प्रणाम, आपकी वजह से ही थोड़ा बहुत कर पा रहे हैं हम जो कर पा रहे हैं सर।
भी यहाँ
नहीं
से
आपके आशीर्वाद।
हम सभी लोग जो नैनीताल से निकले हैं उसमें हेमदा का पूरा सहयोग है। इसमें दो राय
वही
नहीं है।
सर, कोई दो
जो
राय
थोड़ी
नहीं
बहुत भी फोटो फिजिक्स आती है वो हेमदा की वजह से आती है।
हाँ, नीरज और मैं कभी नहीं मिले हैं, पर्सनली मिले भी
हाँ,
नहीं है, एक
पर्सनली
दूसरे
मिले भी
को
नहीं है,
जानते हैं।
बस।
So first presentation is of Dr. Neetu Pandey.
Okay.
Is Neetu present? By the time I will send the list to Hridesh also.
एक पेन दे दो मुझे। नाम तो सुना है। सर की वाइफ नहीं है क्या? मंजू पांडे, असिस्टेंट प्रोफेसर, गवर्नमेंट डिग्री
अच्छा
कॉलेज,
ये वहाँ है
तलवार। तो संजय पंडित तो स्टूडेंट
थराली थराली यानी ये वहाँ है गढ़वाल में कहीं। ये है नीरज जोशी सर, ये खतरनाक हो गया
वो हिमदा है हमारे।
हेमचंद जोशी
स्पीकर
IPR।
I think Neetu, you can start with your presentation.
So my screen is visible.
Yes.
And am I audible, sir?
Yeah, you are audible.
Yeah, thank you. Thank you so much, sir. First of all, I would like to say thanks to all the organizer who has given me this opportunity to present my work. And secondly, I would like to say thanks to all the organizers because I am able to see all of my seniors after a long time in a single screen. I am also from the photophysics laboratory, and all of my seniors like Hen Joshi sir, Hridesh Mishra sir, Neeraj Joshi, Neeraj Tiwari sir, all of my seniors. Thanks, sir, for your wonderful lectures. Today I am going to present the talk on the deactivation channels of the coumarin derivative 6-methoxy-4-methyl-coumarin and its theoretical and experimental aspects. So before we are instructed to do our work in a 8-minute timing. So this is the basics of the deactivation channels of any molecules wherein interact with any materials. Light is interact with any material. So I will skip.
Neetu,
Yes,
just
yes,
made sir ने नीरज इसको प्रेजेंटेशन मोड में लो।
Yes, I am skipping this. So I would like to talk about some coumarin derivatives and what motivated me to do this work. Actually, coumarin derivative is a well-known natural products, and it is very useful. And natural products containing benzene and pyrrole ring, and found naturally in the fruit, seeds, leaves, roots, and in a very high concentrations. Its derivative are useful in various application fields, and specifically the methoxycoumarins are an important subset of coumarin family. These coumarin exhibit a polarity-dependent fluorescence and widely used in environment-sensitive probe for various systems. Actually, methoxy, mainly in methoxycoumarin, 7-methoxycoumarin and dimethoxycoumarin are well studied, but other derivatives like 6-methoxys and others are not studied well, and actually they are in the excited state. The excited state or deactivation channels of 7-methoxy or a dimethoxys is always questionable due to their fast internal conversion and some fast internal conversion in non-polar solvents. So this has motivated me to do this work. So I studied this molecule in a different. It's a very basic work, I know, but I am going give some new insight on this molecule. Actually, first I studied this molecule in a different polar and a non-polar solvents. So I find that whenever we go from the non-polar solvents like hexane to a like a polar solvent like water, we can see that here the quantum yield in a water is very high as compared to the non-polar molecules like benzene. It's around 0.14, or while in the water it's around 1.17, and the radiative rate is also increased in case of water, and lifetime is also increased whenever we go from non-polar solvents like benzene to a water. So why is this so? Whenever we go from acetonitrile, like there is the quantum yield is around 0.23 to the water is around 0.17. It's a huge difference in their quantum yield. So is there any other effect rather than the polarity? So I checked this molecule in a different binary mixtures like acetonitrile and water binary mixtures. So I found that the radiative rate and time lifetime analysis that it shows a linear relationship. It means no such other specific effect are observed rather than the polarity. So actually in coumarin molecules, due to the it is earlier explained that in a coumarin, due to the non-bonding electrons and to pi stars occur, analysis of radiative and non-radiative rates constant in the solvents and binary mixtures, indicating that the pi to pi and n to pi are strongly solvent dependent. In non-polar solvents, n to pi star character for S1 due to the proximity effect or a coupling and mixing of S1 and S2 states. In polar solvents, the energy gap between the S1 and S2 is increased, thus reducing the biogenic coupling. But I studied this molecule. I did some theoretical calculations through theoretical calculations through DFT. Then I found that if we check this molecule theoretically, I did not found such a result like it was earlier explained that the proximity effect is the main factor for is low quantum yield in the non-polar solvents. Like experimental and theoretical result are well matched with that in case of 6-methoxy 4-methyl coumarin. It's comparable when we calculate is theoretically the absorption come around 338, while the same is we absorb in case of non-polar like toluene, it's around come around 340 nm. So they match with this, but when I check its potential energy surface or something, so I found that the coupling of pi to pi and n to pi state in case of decreases in polar solvents, as we can see in this figure, the S1 state and S2 states are well separated in case of non-polar solvents. So this earlier explained deactivation channels of this molecule are not as we cannot say that they are not like that. So I further studied or did some theoretical calculations on that. That I found that some different deactivation channels like deactivation channel like carbonyl stretching mode, and here I am not showing this theoretical studies as due to the time lag, but I did this with the theoretically that carbonyl stretching mode, and as well as carbonyl stretching mode maybe happened, and as well as carbonyl stretching mode maybe decrease the low maybe decrease the radiative rate of this molecule in a non-polar solvent, as well as there may be another possibilities of cleavage of pyron ring in an excited state. So there are two possibilities. Then I check theoretically. So I found that the pyron ring may be break in case of non-polar solvents, and this is suppressed by the polar molecule. So we are getting more radiative rate in case of the polar solvents. So further I studied this molecule in different types of so I further studied this molecule in a different pH. I found that whenever we increase the pH of this molecule, the no variation in the absorption spectra is observed, from pH 1 to 12, but at the pH 13, we found the absorption maxima shifted to 320 nm, and its emission is drastically decreased whenever we are increasing the pH of this. So we can say that there may be cleavage of the pyron ring
You are not audible, Nitu.
Actually, sir, due to the internet connectivity, I am disconnected.
No, it's fine.
Yeah.
I suggest you
then-
just to summarize what was the finding of this work. You
Yes.
say
okay.
that internal conversion is increased in non-polar solvent, and why the gap increases with polarity. Just summarize.
Yes, sir. Sir, I did this molecule in a different pH. I found that the pyron ring is opening, and it's generally decreasing the decreasing the radiative rate of this molecule. Further, I studied this molecule as we see that whenever we are decreasing the pH of this molecule, its intensity increases. So I further studied this molecule in a different concentration of H2SO4. So it's drastically increases radiative rate. So there may be possible. We found that there is no change in the absorption spectra, but in a emission spectra, it's drastically enhances radiative rate. So there may be a different deactivation pathways occur in a strong acid that photoprotonation takes place, and it's increasing the enhancement rate of this molecule further. So I will conclude by work that in the present investigations, I have studied the photophysical investigation of 6-methoxycoumarin in a different solvent and binary mixtures. Further, I studied in a different pH and acid, increasing the acidic concentration of this molecule in a H2SO4. I found that the low quantum yield and the fast relaxation process in the non-polar solvent, which may not be due to the earlier explained the coupling or a proximity effect, but it may be due to the carbonyl stretching mode or a opening of the pyron ring. Maybe possible deactivation pathways of this molecule in a non-polar solvents and showing a low quantum yield. Further, the ring cleavage might be the possible radiation deactivation pathways for the like in case of porcelain in a strong base, and the photoprotonation in a strong acid may be photoprotonation in a strong acid may be happen, and this type of study is helpful for the can be utilized for the proof of inorganic acid indicators. So I would like to acknowledge all of my senior in this all of my senior of photophysics laboratory, as well as some of my data I collected from the TIFR and I also from the GNU. So I would like to acknowledge all them for this work. Thank you so much, sir.
Cleavage may be responsible for ring cleavage, may be responsible for non-radiative deactivation. How
Yes,
are you sure that it is ring cleavage?
Sir, actually, I did some theoretical calculation, which I have not shown in this.
How theoretical calculations are correlated with ring cleavage?
Sir, I checked I found that whenever some of the
You are not audible. So, any other questions are there?
I had the same question. The
Yeah.
Professor Joshi asked.
Are you able
Cleavage
to hear me too?
Cleavage might lead to
Yeah.
permanent change, maybe the change in absorption.
Absorption and emulsion. Okay, so we move to our next presenter.
Sorry, sir, it's disconnected again due to the internet
Just
connectivity.
30 seconds you can answer here.
Yes. Yes, sir. Pardon, sir.
हेमदा आपको पूछना है क्वेश्चन पूछिए.
Hemda was asking how the cleavage is related with your experimental data. The hypothesis or whatever the evidence you have for cleavage, do they demonstrate in the experimental result or any theoretical result?
Like if we increase the pH of this molecule, the opening of pyrrole ring exists, and it's drastically decrease the radiative rate of this molecule. Further, I studied this molecule. I did some theoretical calculation on that. I found that I break this ring opening and then found the result that is happening. That's is decreasing the radiative rate of this molecule.
Okay. Hemda, any comment?
Have you done this theoretical calculation with different solvent, PCM model or SDM model? And did you find that the ring is open in that on optimizing?
At PCM model, I did this
And if you
calculation.
use the PCM model, when you optimize the sample, this compound in the PCM model,
Yes,
that
sir.
ring is opened on
Yes,
optimizing?
sir. Yes, sir. Yes, sir. No, sir. Yes, sir.
How it is possible?
Yes, sir. I break this, like I open the molecule, the pyrrole ring. I open this.
No, you put in DFT
can
calculation, you put the open pyrrole ring or you close pyrrole ring, and when you optimize, it is open. On
Yes, sir.
optimizing the pyrrole ring, you opened or
No, sir. Sir, I make the structure of open pyrrole ring and then I calculated this.
No, that is not the cause. You cannot do the theoretical calculation like that. On optimizing the pyrrole ring in that solvent, it opens on optimizing. That means it is enclave. Okay.
Yes, sir.
Okay, thank you, Neetu. The next presentation is by Nisha Fatima. Is Nisha there?
Yes, sir, she is there.
Dr. Nisha Fatima.
This conference basically photophysics conference.
Today is
photophysics Nainital.
Dominated by Nainitalians.
Yeah, you go ahead. Yeah.
A very good evening to all of you. Myself, Nisha Fatima, from Protophysics Laboratory Department of Physics, TSB Campus, Nainital. Today, I'm presenting my work, that is photoluminescence properties of 7-hydroxyflavone in aqueous medium, proficient fluorescence enhancement. In this work, we have represented 7-hydroxyflavone as a water sensing probe by studying its photophysical characteristics in different water and in the mixture of water and organic solvents. As we know that water is one of the most important and is essential substance, not only in daily human life, but also in chemistry. It influences not only the yield of chemical and drugs, but also their activity and application in polar solvents, in which especially water is miscible. And we have found that water also influences several characteristics of excited state organic molecules. And the basic study is on sensing the water in different organic solvents. So for that, colorimetric and fluorescent sensors have been a good choice for the detection of water. And we have chosen a flavon derivative, that is hydroxyflavone derivative, which is a promising group of organic molecules in a sphere of medical sciences and pharmaceutical activities. Hydroxyflavone has a unique feature of high sensitivity, significant photostability, and a large Stokes shift. That's why we are using 7-hydroxyflavone for the detection of water. At first, in the steady state analysis, we have observed the absorption spectrum in different solvents such as ethanol, DMF, and THF. And we have added different fractions of vector of water, different fractions of water in these solvents. And on increasing the water fraction, we have found that a main absorption band, which comes around near 290 to 310 nanometer, the absorption spectra redshifts, and in higher concentration of water, the band at 375 nanometer approx generates in the longer wavelength region. This may be due to some ground state species formation. Next is we have studied fluorescence spectra of the same samples of absorption. We have found that in main emission appears in solvents near 400 and 450 nanometer. On adding the water, these main absorption band decreases, intensity of this main absorption band decreases, whereas emission at green wavelength region appears, and it enhances on further increasing the water concentration. And figure 6 shows the fluorogenic response of 7HF in different different samples of plain neat solvents and water binary mixtures. It is specifically shows the fluorescence turn-on response. Next is we have studied these parameters to analyze the complexation nature of 7HF with H2O in these solvents by job spot, and we have found that there is 1:1 stoichiometry between 7HF and H2O in ethanol, whereas 1:2 in DMF and THF. We have also evaluated several spectral parameters, and we have found that Stokes shift increases on adding the water. Oscillator strength also increases, as well as due to the enhancement in the intensity of fluorescence, quantum yield increases. Intensity enhancement factor is 34-fold in THF water combination, whereas approx 18-fold in DMF H2O and approx 5-fold in ethanol H2O. It also represents, if we come to the sensing part, it represents the lower detection limit. In THF, it's 0.008%. In DMF, it's 0.014. And in ethanol, it is 0.389. Further, we have also evaluated or measured its fluorescence lifetime parameters, and we have found that in this part that the anionic species dominates due to the fluorescence spectra formation at 525 nanometer, 527 nanometer, and the longer wavelength band that appears in the absorption. And same results are comprehended by lifetime analysis also, that anionic species in the higher water fraction dominates, and there is also a participation on hydrogen bonding also. Further, we have evaluated these complexation mechanism by given a scheme in the figure 9. We have also evaluated this study with the theoretical analysis, and we have found that the absorption spectra of 7HF in water by using IEF PCM model and the anionic species comes near about the experimental values. And the lower HOMO-LUMO gap also comprehend the redshift in the absorption spectra. Next, we have taken this study to the practical applications also, and we have analyzed some food samples and commercial products and treated it with 7HF, and we have used a mobile phone application that is color analyzer app, which has used these colors of these samples and converted it into the RGB and lab color modes, and the changes in these color modes, color data has been analyzed, and it represents the sensing nature of 7HF. So finally, we conclude that 7HF shows the fluorescence turn-on response on addition of water. It is also represent lower detection of limit, which is much below the most fluorescence sensors. The main mechanism is anion formation and hydrogen bonding. And we have also demonstrated its practical application by using mobile phone and a color analyzer app. So finally, we conclude that inherited large Stokes shift of 7HF comprises with turn-on response is a promising feature developing new sensing materials for the detection of H2O, not only in real samples, in biological environments and commercial products also. Thank you. Thank you so much.
My question is that in 7-hydroxyflavone, you say that intensity increases because of ESIPT intensity, as well as Stokes shift increases because of ESIPT. Then in some cases, you say that it is the anion that is found that is responsible for it. What is the exact mechanism for fluorescence enhancement when even small amount of water is present?
So at first, when we have included the little water fraction, the intensity...
Whether it is the ESIPT is enhanced or
anion
it is
formation.
anion formed, what
it
is
is
the
anion
actual
formation. Anion formation.
Anion is formed.
Yes, sir.
In the introduction part, somewhere you have written that it is ESIPT that is responsible for fluorescence enhancement as well as Stokes shift.
No, sir. I have mentioned that hydroxyflavones based on excited state proton transfer have been found to be highly useful.
So actually the aim of this work is to quantify trace amount of water in organic solvents.
Yes,
so
sir.
you should be sure what is the exact mechanism. Even small amount of water comes there, clusters will be formed with it. That may also result in fluorescence enhancement.
Yes, sir. I have represented it in the scheme.
Now you say that you can use smartphone with this using this particular method. What actually which parameter you will use and optimize with your smartphone?
So we have used color analyzer app and we have evaluated the RGB color modes, which represents different
But whether your smartphone camera, simply by images, you will be able to get exact water content?
Yes, sir. We have tried it several times and then we have taken the average form.
Or you have to quantify it with some machine learning so that you can actually know what is the actual amount of water.
Yes, sir.
Okay, now other people.
Nisha, this property shows by only this molecule 7-hydroxyflavone or other molecules also, this change in color of the detergent?
So some other molecules also shows, but those
so how
are
you distinguish?
those molecules have some metal content in it. They are toxic metal contents. Some metal complexes have been formed, and then these type of work have been done in some of the molecules.
Regarding this enhancement in that is the proton transfer, or earlier Himda already asked it.
So it's an ion formation. I have represented.
What about the Stokes shift? How much there is Stokes shift?
So Stokes shift is about in THF it is In THF, it comes out to be 13075
Can you show me
centimeter.
the absorption and emission spectra together? Any slide? Because I have some doubt over there. In emission spectra, yes, a band is up here. Okay. Because at 450, it gives the emission spectrum and absorption.
Yes, sir.
400 to 450. Where is the absorption? Can you show me the absorption, please? The first, yes. 450. So what about the excitation spectrum of this? You not shown
So
the excitation.
excitation spectra clearly, excitation spectra resembles with the absorption spectra.
Exactly resemble with the.
Yes, sir.
What about this? The longer wavelength emission.
Yes, it also appears in excitation spectra also.
And what about the shorter wavelength, the 450 nanometer emission? What is the excitation spectrum?
So the same thing, same type of results were observed in excitation spectra also.
Well, you are not getting the anion absorption in the
Anion absorption of longer wavelength region we observed in excitation spectra also.
But what about the 450 nanometer excitation? Did you observe that?
Yes, sir.
And here in this case, yes, in the third spectrum, why
Yes,
this
sir.
much is absorbed that much high?
So because that molecule is hydrophobic, and in higher water content, it starts to form some lumps type. So it becomes scattering there.
No,
Due to
there is the absorption
insolubility of-
spectrum. In this spectrum, in this absorption spectrum,
Yes, sir.
the optical density is up to 8 or 0.6 nearly in those two
Yes, sir.
samples. It
Yes,
absorbs very strongly here in the 350 to 500 nanometer. Why it is like that?
So it's because anion's OD increases, and it increases the longer wavelength region due to scattering also.
Scattering of what?
So scattering
compound?
due to the colloidal type of sample.
Why it has become colloidal?
So because the molecule is hydrophobic, and it becomes to form some precipitate in the higher concentration of water.
Okay. When you are doing this experiment, you are adding water in the reference also?
Yes, sir.
It should be clear. It should not be there.
So, Nisha, so you
Yes,
were
sir.
detecting trace amount of water. So what
Yes.
is the limit of detection? Like what's the minimum you can detect?
So
And
minimum we have detect 0.008% in THF water combination.
0.08%. Okay, so have you ever seen the THF bottle itself or any water
Yes,
bottle,
sir.
any solvent bottle? So
Yes, sir.
there is always water impurity with that. Like it's always less than 1%.
Yeah.
All solvent. So unless you, what do you call this? Unless you take out if you dry the solvent, okay?
Hmm.
So is this the 0.08%? It sounds it sounds very low. So okay, at what you said 0.08%, and how much change you see that? Like how do you recognize that? Say that's a change at 0.08%.
So intensity decreases as well as the
By
in
how much?
absorption spectra changes much. Its OD increases little bit.
Okay. So is there any standard deviation on, like when you say the 0.08%, do you consider any error part in it? Like how much accurate, how much confidence you have in saying 0.08%?
So we
Is there
have
any
evaluated
error?
by standard deviation method and by slope and concentration slope 3 sigma by K. We have evaluated by that formula.
Okay. I'm done.
Okay, sir.
Thank you.
Thank you, sir.
Thank you, Nisha. Our
Thank
next
you, ma'am.
presenter.
Thank you so much.
Our next presenter will be Nupur Pandey, Sanjay Pant, Nisha Fatima, Mohan Singh Mehta from Photophysics Laboratory, Department of Physics, Center of Advanced Study, DSB Campus, Kumaon University, and Laser Spectroscopy Laboratory, Department of Applied Physics, Delhi Technical University. Nisha, are you ready? Hello, Nisha, are you ready?
I think it's Nupur.
Our next presenter is.
Hello.
Hello. Yes, Nupur, you can start your presentation. Your screen is not visible, Nupur. Your screen is not visible, Nupur. Hello.
Hello.
Yes, Nupur. Can you share your screen?
Yes, yes, wait.
I think there's technical issue from your side. Is the net slow with net connection?
At that time, we can move to next presentation.
Yes, yes, sir.
And Nupur can come back later.
Yes, sir.
है ना?
Next presenter is Maitri.
Am I audible, ma'am?
Yes.
Okay, let me share my screen first. Ma'am, is my screen is visible?
Yes, 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 Maitri.
So, good evening to all. I am Maitri Libar from the Department of Physics from Graphicera deemed to be University, Dehradun, Uttarakhand from India. The topic for my presentation is about the nonlinear mixing of two laser beams in a semiconductor film and the resonant terahertz radiation generation. So the outlines of my presentation is about the electromagnetic spectrum, introduction to the terahertz radiation sources, and how basically what are its mechanism, how the terahertz radiation generates. The problem which I will discuss is
I would like to interrupt you for a minute. You can focus on the results.
Oh, yes, sir. So there are basically the three radiation generation mechanism which we use in our problem. One of is the photoconductive antenna, that is compromises basically structured compromises of the two metal electrodes, which may be of the any metal like a gold. Or when the femtosecond laser pulse is basically illuminating through the gap between them, it produces a photocarrier and static bias fields. So that is a major source that produce a broadband terahertz radiation. And basically its process called to be photoconductive because its principle is based upon the photoconductivity, and it works like an antenna for the terahertz emission. The another method is the optical rectification, when its femtosecond laser pulse was incident with the nonlinear crystal material who having a susceptibility of the second order. So it produces a different frequency component and produce a DC polarization, which results the emission of electromagnetic waves in the terahertz region. The problem which I have taken that I will discuss is the terahertz surface plasmons in a thin semiconductor film by a nonlinear mixing of the two laser beam. So when the two laser of having a different frequency and pulses of different wavelength, so when they are fall over a semiconductor thin film, so they impart oscillative velocity to electron and a beat force that for term to be as quantum-motive force. So the later beat, when they are combined with ripple, they produce a current, and resonantly they excite the surface plasmons over the surface. So I have chosen the semiconductor indium antimonide for my problem. And basically as semiconductor have much lower permittivity as compared to the metals at terahertz frequency range. It also have a possibility to tune the response of plasmonic structure by varying the carrier concentration. So with the help of the Maxwell third and fourth equation which I have used, so we able to get our wave equation, which is a generalized form of our wave equation. So we get the three solutions for our wave equation: one for glass region, another for between the glass and semiconductor region, and one for the free space region. So on solving our solutions and applying a boundary condition for x equal to a and x equal to 0, one able to know about a dispersion relation. So after then, when I plot the dispersion graph, so I have plot a graph for the dispersion relation for the free space, and one for the without collision frequency and with collision frequency. So what I have seen that when the effect of collision frequency is taken into consideration, it results in a broader resonance and shorter propagation length of surface plasmons. And due to the collision among the electrons, it shows a damping effect even also, and that results a more damped and dispersion curve. About some excitation part of the how the terahertz surface plasmon get excited. So when two laser beam, they are linearly polarized in y direction, and they're incident obliquely on the planar structure. So their laser, they're imparting the oscillative velocity to the electrons, and it also exerts some quantum-motive force on them, which later further gives a nonlinear current, and which is a major source for the electromagnetic radiation in the terahertz range. So I have plotted the normalized terahertz amplitude for the surface plasmons for my parameters. So in the graph, I have seen that when the terahertz surface frequency was increasing, there was a decreasing in an amplitude, and it also decreasing the thickness of the film of basically a semiconductor. So the highest coupling will be take place at a particular thickness and a frequency. So basically the highest coupling will be taking place at when my thickness is about 0.3. So in the conclusion, what I have found, basically the thickness of film is a very critical parameter for the tunability of the proposed device. And in the end, I would like to conclude it with some of its applications, as terahertz are widely being used in wireless communication sector because it have a high frequency as compared to the radio waves. It also used in concealed weapon detection, as the terahertz as non-ionizing radiation have stronger penetration depth, so one can replace the X-ray like a CT scan can be used. Another application, it used in the medical imaging because it is a non-ionizing and it don't damage the living tissues and the DNA. It also been used in a skin cancer identification. The last one is for the use in astronomy, even also as for the deployed scientific satellites and for the sensors in astronomy, terahertz radios, they're offering the possibility for the wireless transmission of the higher data rates. And thank you for giving me an opportunity for presenting my presentation. Thank you.
What is the actual motivation behind this work? How you solved the equations to find out the terahertz contribution. So what is the motivation? Can you show me the dispersion relation again?
Yes, sir.
Just show me the dispersion relation. Dispersion relation, you have this surface plasma relation without collision and with frequency. There is hardly much difference. How you got this small difference?
So your voice is not clear.
This
my next question is, what is the new information your work is giving about the terahertz generation?
are you able to listen?
So sir, these terahertz radiation, they have been widely used in imaging and spectroscopy and communication due to terahertz because they have unique properties and capabilities.
So the present approach you have taken, how it is different from other approaches?
So it will be different for the different cases. If we take in gold, so the difference in the collision frequency and without collision frequency, the gap will be there. The damping effect will be more as compared to the semiconductor.
How other?
Did you plot the plasmonic angle? Or it is changed with this collision frequency? Hello?
So pardon, sir.
Did you plot the plasmonic angle? Are there a difference when it is collision? With and without collision? What is the plasmonic angle?
So basically, when angle of incidence is nearly equal to angle of resonance, and when reflectivity is drastically below the 50%, so at that particular point, when the terahertz surface plasmon excited at that point, when laser component, it's equal to the wave vector of our surface plasmons.
No, it's okay.
So
But
at that point,
did you get any change in the plasmonic angle? Did you know plasmonic angle? In S and P waves? When you plot the P wave curve, you got the plasmonic angle, right?
yes, sir.
So are there a change with and without collision? Generally, when you place gold nanoparticle layer on the glass surface, the plasmonic angle shifts, right? So what about this collision? Okay, no problem. From my side is over.
By changing the dielectric constant, it can shift the plasmonic angle without changing the collision frequency. By changing the dielectric constant of the surrounding medium, we can shift the plasmonic angle.
Okay. Okay, beta.
Thank you, sir.
Okay.
I'm again inviting Nupur Pandey. Should I run your PPT, Nupur, now this
Yes.
time?
Yes, please, yes.
1 minute. Is it visible? Is it visible?
Yes, it is visible, yes.
Okay, you can start.
Okay, am I audible?
Yes.
Please focus on the results.
Okay, sir. So here, a very good evening to all. I am Nupur Pandey. My today's presentation is about fluorescence quenching of 3-aminoquinoline by halide ions. So here we have studied the influence of halide ion on the fluorescence properties of 3-aminoquinoline in aqueous acidic solution using steady state and time domain measurement techniques. This is the absorption spectra. Can you change the slide?
Yes. 1 minute. Just a second.
Okay.
Is it okay?
Okay, this is the absorption spectra of 3-aminoquinoline in absence as well as presence of halide ions. No significant changes are observed on the absorption spectra, which shows the ground state complex formation is not there and rules out the possibility of static quenching. Next is we recorded the fluorescence spectra of 3-aminoquinoline upon adding various halide ions. Maximum concentrations we used here, as it can be seen from this picture, which under the UV light, that fluorescence is maximum quenched upon adding iodide ion compared to bromide and chloride ion. Very less quenching is observed in case of iodide ions. And then, please can you move the slides? Next page.
Next.
Then we systematically studied the fluorescence spectra of this 3-aminoquinoline upon adding varying concentrations of iodide and bromide ion. We observed that the quenching is nearly about 6-fold in case of iodide ion and nearly about 2-fold in case of bromide ion. However, at different excitation wavelength, that is 370 nanometer, a similar pattern has been observed. No changes were observed in the shape as well as peak position of the fluorescence maxima. Please change the slides. To comprehend the nature of fluorescence quenching, we have plotted the fluorescence intensity as a function of bromide and chloride ion concentrations using a well-known SV relation. The plot is linear all over the range of this all over the selected range of the concentration, and from here we have calculated the quenching constant and bimolecular quenching constant, which is again more for iodide compared to that of bromide ions. Please move to the next slide. Now, so the decrease in the fluorescence intensity, even with a straight line of SV diagram, we cannot get an idea about the nature of the quenching. So here we perform the time resolved measurement analysis to ascertain the mechanism of fluorescence quenching of 3AQ by iodide and bromide ions. The decays were collected at excitation wavelength of 375 nanometer, and the fluorescence decay of this 3AQ fits best to a single exponential function and shows a decay time of 19.68 nanosecond. Upon adding
iodide ion, the decay time is maximum reduced up to 3.474 nanosecond, and in case of this bromide ion, it is reduced up to 6.60 nanoseconds. So the slope values obtained by the SV plot using fluorescence lifetime and fluorescence intensity are nearly same, indicating that the quenching should be dynamic in nature. So that here we can say that the reduction in fluorescence intensity along with the reduction in fluorescence lifetime substantiates the existence of pure dynamic quenching, and the possible mechanism should be electron transfer from halide ions to 3,8-aminoquinoline, and as well as the participation of the heavy atom effect. These analyses are significant in the following ways: that the nature of fluorescence quenching is purely dynamic up to the specific range. SV constant of the system is higher than some of the previously reported values, and fluorescence decay is mono-exponential, thus making the quenching analysis uncomplicated. So this is all about the results. Thank you so much.
Case you found that it is dynamic quenching. So your
Yes.
Stern-Warmer plot for intensity and lifetime both matches.
Yes, yes. And the constants are nearly
If you
same.
plot
from
I0 upon
lifetime.
I versus concentration and tau 0 upon
Yes.
tau versus concentration, they are similar
Yes.
plots or different?
They are similar.
Why? But it is a dynamic quenching. There is no ground state complexes.
Yes, so from the SV data, we cannot we cannot comment about nature of the quenching. So when we perform the lifetime analysis, and we found that the lifetime is reduced upon adding these ions.
No. If there is no ground state complexing or no static quenching, only dynamic quenching there,
Yes.
then of course
Yes.
your fluorescence intensity, Stern-Warmer plot for intensity, as well as lifetime should be same.
Yes.
It should not vary as per
Yes.
fluorescence.
In case of static quenching,
process.
lifetime does not change in case of static
You say that
quenching.
there is no change in absorption, so no static quenching is there, I assume.
Yes, from the absorption graph, we say there is no complexation between the probe molecule and the quencher concentration.
My second question is that what is the actual quenching mechanism? Because it doesn't appear to be the heavy atom effect. So what is the quenching mechanism here?
It may be electron transfer. And for iodide ion, we can say that these iodide ions triplet formation is also enriched, which strengthens the intersystem crossing. It can possibly be the de-excitation pathway.
Can you show me your figure 5? Here, in case of your bromide and iodide,
Yes.
the initial concentrations, trend
Yes.
is quite different. In case of iodide, it's different, and in case of bromide, it is quite different. Why it is there?
In case of bromide, okay.
Whether
So,
it is due to some experimental uncertainties or
yes, sir, there is some concentrations are more in case of iodide ions compared to bromide.
now other people.
Nopur,
Yes, sir.
why the rate of quenching of iodide ion is very high as compared to the chlorine or bromine?
Sir, I think it
What is
is
the reason behind that?
efficiently This quencher molecule deactivates the excited fluorophore more efficiently compared to bromide.
Why? Why iodine quench more fastly as compared to chlorine or bromine?
Sir, okay, due to more electron transfer compared to bromide and these chloride ions.
Energy transfer from where?
Their the outer electrons of this iodide ion can influence more the molecule's
This is the
electronic
collisional
structure, we
quenching
can say.
or this is the flat mechanism?
Sir, according as per the results shown, we have demonstrated collisional quenching, dynamic quenching.
The Nupur, which will have bigger size, iodine or chlorine?
Bigger size, I think iodine.
Okay. Who will hit hard? Like
Not, I think it is really, it is the size of the iodine is
Yes.
larger compared to chlorine.
Yes, actually this trend is along with the ionization
Did you
energies
find,
also the
did
quenching
you
trend.
find the rate of quenching for all the three halides?
Rate of quenching, no sir.
You find the external blockage for both chlorine and
Rate of
iodine?
quenching, yes, we have calculated for bromide and iodide,
Not chlorine.
not chloride.
Why chlorine is
Actually,
not
the
quenching?
quenching was very negligible.
That's why I'm asking. Why iodide quench very fastly as compared to chlorine? Anyway, okay, from my side.
Okay, sir.
Should I move to the next presenter? Judges?
Yes,
Okay.
go ahead.
Yes.
Next presenter is Bhupendra Kumar from LR College.
Am I audible?
Yes, sir.
Okay. Am I visible?
Yes, sir.
My screen.
Yes, sir.
Good evening to all. Myself, Bhupendra Kumar. I'm assistant professor in LR College. I am highly thankful for my HODs, Sir Dr. Neeraj Tiwari, and the organizing committee who gave me the chance to explore to share my research work. The topic of my research work is terahertz radiation generation from non-linear bulk non-linear materials. In present scenario, there are three big challenges for future generation, like in medical science, energy, and security. As we see in the day first of this seminar, there is issues for energy and how to generate the energy from different materials or different types, like nuclear energy, nuclear fusion, nuclear fission in ITER. If you're talking about the terahertz is a gap between microwave and infrared electromagnetic radiation. If we are talking about its frequency is near about 10 raised to power 12, and its wavelength is near about 300 micrometer. Why we are using, why we are finding terahertz radiation? Because most of the chemical substance and most fundamental molecules like water molecule or oxygen molecule, their rotational and vibrational absorption lines lies in the terahertz region. This terahertz radiation can penetrate through many non-polar and non-metallic materials such as paper, textile, woods, and plastics. And another property of this terahertz radiation is that it will reflect from metals and absorbed by polar molecules. This radiation is not so much harmful like as X-ray. So it is very useful in the field of medical science. So how to find out the terahertz sources? There are both the sources from like natural source and man-made source. In natural source, there are black body radiation and cosmic rays. While in man-made sources, laser-driven terahertz source and electron beam interaction-based sources are used. This is the simple diagram for natural sources like cosmic rays background and black body radiation at room temperature. In my talk, I will explain the optical generation from electro-optic materials, that is a non-linear material which produce the terahertz radiation by applying femtosecond laser pulse. What is the non-linear materials? The materials whose polarization density depends upon the electric field intensity of applied light. So here in optical rectification, the process due to which terahertz is generated, that is known as the optical rectification. When two laser pulse of near about same frequency omega 1 and omega 2 are incident on a non-linear crystal, its polarization density will change according to the formula Pi equals to this. And due to this optical rectification, the radiation which is generated lies in the terahertz region. We are using the non-linear material, that is the lithium niobate, and that is the periodically poled. Periodically poled means its polarization is alternate. So it is the ray diagram which we are using for our theoretical model. From left side, the femtosecond laser pulse is incident, and right side or perpendicularly we are getting the terahertz radiation. Optical rectification. What is the optical rectification? Optical rectification is the process in which non-linear polarization is generated by the incoming laser fields by the second order non-linear susceptibility in the case of very short. May I audible?
Yes, you are.
Okay. So here's the ray diagram. We are using femtosecond laser pulse, and there is a non-linear medium whose second order susceptibility is non-zero. Then a single pulse of its polarization density, rate of change of polarization density produces the terahertz radiation. Key points are here. We are using the femtosecond laser pulse and cryogenically cooled, periodically cooled lithium niobate. And we find that in our theoretical model, if we change the periodicity of our medium, then the intensity of this generated terahertz wave will change. So that depends on the periodicity length, and width, and also the temperature of the medium. The phase matching can also be achieved with the properly choosing the period that I'm seeing. The idea of using phase quasi-phase matching material with periodically inverted sign second order susceptibility for terahertz optical activity. Based on this, we will investigate the range of experimental parameters which optimum density of terahertz we found. So these are the uses of terahertz radiation because it is very useful in medical science and security. That's explained by previous. Thank you, sir.
Can you show me the figure where you have used 2 femtosecond pulses, 100 femtosecond and 200 femtosecond?
Yeah, near about
terahertz intensity. Can you show that figure?
Just a minute.
Omega 1 and
That
omega 2.
You have shown two.
This one.
Yeah, this one.
No, next figure.
Okay.
No, next.
Yeah.
Here. So you have shown terahertz intensity versus this one. So you have used 2 femtosecond pulses, pump pulses. Why just doubling by this pulse width, the terahertz intensity almost diminished?
Right.
Can you explain it? Why it happened?
Because the nonlinear material respond quickly for the.
Just I would like to know from you that if you want to generate terahertz pulse, now you are using pump pulse and femtosecond pulse.
Right.
So if you have some optimized femtosecond pulse to get optimized intensity, or you can arbitrarily choose any femtosecond.
We are generating a theoretical model for this and calculating by third and fourth Maxwell equation.
So you have simulated intensity.
Right.
Okay. Yeah. So somewhere the factor of pulse width will be coming there. What is the relationship?
Pulse width.
Yes, the pulse width of the pump pulse.
That is output intensity doesn't affect the pump pulse width. There is no relation with this. Sorry for this.
Can we expect better intensity with 50 femtosecond pump pulse?
The intensity will decrease.
No, my question
450.
You have simulated the
sorry.
There should be certain relationship between the pump pulse and the simulated terahertz intensity of the terahertz.
Right. We are just going home for this. So I will.
Can you summarize what is the actual achievement of this present work?
By using this, we are generating terahertz, and there are so many uses of terahertz radiation, like every field in energy, in medical science, because the energy of terahertz is less than the X-ray, so we can use this by in place of X-rays, because X-rays is very harmful for tissues like cancers and all these diseases will.
In how other people can.
What is the frequency of your incident? This femtosecond pulses.
Just
in figure number 8.
This is 100 femtosecond pulse, 1.5 watt out of power of this. Energy is 500
This is the
microjoule.
femtosecond, but what is the frequency? Because you generated 10 hertz, 10 terahertz frequency, right?
Yeah, near about 10
So
or point 3 to 3 or 4. Yeah.
what is the incident one?
Energy of incident laser is near about 500 microjoule.
No, not energy, frequency.
Frequency,
But
I can
what is the in the second harmonic generation? What do you do? Let us suppose when we passed simply when we passed a 1064 nanometer laser to the second harmonic crystal, it gives the 532.
Okay.
Right? Generally,
Right.
it is like that in the second harmonic generation, non-linearity effect. So what
Right.
about here? In figure number 8, this is the some. Can you go in the slide number 8?
Last one.
Slide number 8.
8. Okay. Yeah.
Here you are using omega 1 and omega 2.
Yeah.
So
So
the
the
omega 3 is
generated
the
difference of both the frequencies of lasers.
okay.
Because it is in optical rectification, we are using the DC polarization because in DC
Generally,
polarization,
what type of material this signal
non-linear
we achieve?
materials. Non-linear
What kind of?
materials.
Can you example some of them?
Lithium niobate.
Okay, lithium niobate.
Yeah. And some other also there like
But lithium niobate crystals,
yeah.
when you excite by this 1064 nanometer radiation, it gives 532 in visible
Yeah.
light. But how it will you are getting in the terahertz
No,
range?
no, omega 1 and omega 2 is near about the same, not doubling or this one. Because DC polarization is only generated then omega 1 and omega 2 are near about.
Oh, okay. I am not clear. Okay, no problem. From my side, it's okay.
Thank you, sir.
Thank you, Mr. Bhupendra. Now there are no more presentation in this section.
Okay.
Thank you, judges.
We have material science presentations.
Yes, sir.
So I would like to thank Dr. Hem Joshi, as it's already too late. Thank you for being with us and judging and giving your nice talk. Thank you so much, Himda. And Dr. Hridesh, if he likes to be with us, it would be a kind gesture, but if he
No, I am here. I am here with you, but sometime I will go to take
okay.
food or like that. है ना?
Okay, so judges for this material science section are Dr. Neeraj Joshi and Sapna, you can go ahead.
Okay, sir. First presentation is of Dr. Rajesh Kumar. Dr. Rajesh Kumar, are you ready?
Yes, ma'am. Yes, ma'am.
Yes, then you can share your presentation.
Okay, ma'am.
Let's first introduce the judges, I think.
Sorry, sir. Yes, sir. One.
Start, ma'am.
No, sir. Sir, please you introduce the judges.
Then give me just give me some time actually.
You can start.
You can start.
Yeah.
By the way, I will
We'll
just
take a break.
contact over phone. Then I will tell you.
Shall I start, sir?
Yes, yes.
Good evening to everyone. I am Dr. Rajesh Kumar and I am performing my research on
1 minute, Rajesh. Your screen is not visible.
Okay, ma'am. Yeah.
By the time you can contact Dr. Deepa that Dr. Verma is there or not.
So he is there, sir.
It's okay, ma'am?
Yes.
Okay. Good evening
No,
to
no,
everyone.
no, no, it's not okay. Your screen is not visible.
Yeah, by the time
We
we
can
are
move.
ready with Dr. Neeraj Joshi and we know about Dr. Deepa Verma and Dr. Hades is also there with us. So other judge is Dr. Arvind Kumar. Thank you, Dr. Arvind, for being with us so late in the night.
Thank you very much for inviting me.
He is Associate Research and Development, Nexus Power, Bhubaneswar. He has been postdoc fellow Institute for Advanced Study, Shenzhen University, China. Served NPDF fellow, Indian Institute of Science, and ITER Bhopal. Research associate under DRDO Diet Program on Nanomaterials, Department of Applied Physics, Defense Institute of Advanced Technology, Pune. He is a PhD from Defense Institute of Advanced Technology and MTech in Laser Science and Application, Devi Ahilya University, Indore. Thank you being with us. You can now start the presentations.
Rakesh?
मैम प्लीज नेक्स्ट वन कंटिन्यू कर दीजिए मैं स्लाइड की प्रॉब्लम चेक कर रहा हूँ
Okay.
जी
Next is Sandeep Shirohi. Are you ready, Sandeep?
Yes, ma'am.
Sandeep,
Yes,
you
yeah.
can show your slide.
आग लगा सभी चीज को तो नेट चल रहा है तुम्हारा हॉटस्पॉट से कनेक्ट करते जरा उसमें आओ तो
Is it visible, ma'am?
Yes.
So first of all, very good evening to one and all present over here. Myself, Dr. Sandeep Sirohi, Assistant Professor, Department of Botany, Hariom Saraswati PG College, Dhanori, Haridwar. So today is my presentation on significance of quantum dots in sustainable agriculture, that is QDs. So, ma'am, is it moving?
It's showing blank. It is showing a blank slide. You can do the screen show.
Stage show.
No,
It's visible now.
it's
So now
it's
visible.
Yeah,
Okay.
yes.
Yes. First of all, we'll discuss about the introduction of the QDs because these are practically electrons and these has a very nanoscale size and outstanding contribution in the field of nanotechnology as well as in the field of biotechnology. And due to its varying innovation and
Sandeep sir, can you
yeah,
make it in presentation mode? Because
sir, I think it's doing some problem.
yeah. Okay.
But sir, now it is now not moving now that now sir it is working. Okay, thank you sir. And over the past few years, the different nanotechnologies have the synthesized the different kind of QDs, and they are showing the very innovative and approaches towards their in different fields like electronics and other life sciences fields. So these past few years, the different nanotechnologies synthesize different kind of QDs. These forms different kind of LCDs, making their way into agriculture and become worthy to mentions. They may be of the different types like different core cell type QDs, alloyed QDs, and different core type QDs. And as far as is synthesis is concerned, they can be synthesized by the different approaches that top down approach and bottom approach. In these approaches, the top down approach, the different QDs are prepared from the larger nano microscopic material to the silicon, while in bottom upper approach, different atom and molecule that can integrate it together and form the micro scale different QDs. So its significance are concerned, they are very useful electronic and optical properties as photovoltaic cells and play very significant role in the biological sciences. And because this, if we're using the different kind of QCs, they directly enhancing the photosynthetic rate. And once the photosynthetic rate is increasing, the overall development and the growth of plant is increasing and directly proportional to the yield of the plant. And it also play in the very important role in the field of pharmaceutical sectors for the production of different kinds of metabolites that can play very important role for the manufacturing of different kinds of drugs. And these QDs are also very important role in the field of agriculture, and it is proven that it can enhance the photosynthetic efficiency in different greenhouses, and it can also detect the different pathogens or different disease causing agents. And we can use the different kinds of pesticides and nanopesticides by the help of different QDs, and it can also enhance the photosynthetic rate and growth rate of the different kinds of the plants. And it can also support the organic farming and the vertical farming that is the present day need, because the population is increasing day to day, but our land area is constrained. So vertical farming is the need of present day. Then it can also the
Hello, Sandeep.
precise
Just to
farming.
Hello, Sandeep. Your
Yes,
slides are not moving. Are you moving the slides?
not moving, ma'am.
You are on the introduction slide now.
No. I am just in mid of the slide.
Okay.
This one. Is it moving
Okay.
or not, ma'am?
Now
Now it is.
moving. Now it is moving.
But okay. So it's precise farming because with the help of different QDs, we can prepare the nanopesticides, and it can also nano fertilizers are used for the development of the growth, and it's significantly economic burden that is posing the traditional chemical pesticides. And different disease management also is the different today present day demand, and with the help of different QDs, we can surface functionalized QDs are prepared for different disease management. And utilizing for the nano area in the field of agriculture, different QDs are act as a fluorophores and improvement of the different crop yields, as different AI technologies are used to detect the which kind of pest is required, and whenever we need the irrigation and which kind of different nutrient is required. So these are the different artificial intelligence technology for developing the productivity and sustainability in the step towards the sustainable agriculture. And here is the experimental slides in which the enhancing the photosynthetic rate. If we are using the different kind of QD film, that the photosynthetic rate is increasing in the greenhouses, and it directly proportional to the growth and productivity of the plants. So we can conclude it that it's play very significant role in the agriculture, and with the use of AI, we upgrade the lifestyle of the present day farmer, that is precise farming and enhancing the rate of photosynthesis that directly influence the growth and development of the plant, and enhancing the quality yields. And these we can also play important role in the toxic detection in food products. So with these words, these are the references. I have taken the content, and thank you.
Dr. Sandeep, I have one question. How
Yes.
much is economically viable? Because
Economic-
synthesizing quantum dot, how this process economically viable for agriculture aspect?
for
Because synthesizing quantum dots, it's a tedious process, as well as it's heavily investing process.
Yes,
Okay,
yes, sir.
so
Yes, sir.
there is too
Absolutely.
much money involved,
Yes,
and
sir.
we require a cheaper product, which
Yes,
is
sir.
not much costly for the farming purpose.
Yes, sir. It is very significant, important role play in the developed country, because where the different organic farmings are grow in the mass gross level, organic farmings are using. But in our country, it's very hard to adopt in present day. But in future, this kind of technology has play significant role for the fulfilling the present day demand.
Okay. So you have shown the cadmium sulfide quantum nanorods and the other. Because if you look at the cadmium is a toxic material.
Yes,
Okay,
sir.
and anyway you are using near to any food product, how you can maintain that, how you can eliminate the toxicity problem.
So with the help of QDs, we can just treated the crop, not the food product.
No, the crop if you are treating the crop,
Yes, sir.
the cadmium is a toxic material.
Yes,
Okay,
sir.
so
Yes,
if
sir.
you're treating a crop,
Yes, sir.
there is a possibility that cadmium goes inside the crop. Okay, and that
Yes, sir.
that definitely comes give influence to the products, crop products. So
Yes, sir.
how you can maintain, because that's a big question, and if there is some studies, it is
Yes, sir.
FDA
Yes, sir.
approved or not.
Yes, sir. This some studies are must be required for the identification of the toxicity of this cadmium.
Mm. Because if it is not FDA approved, then it is very dangerous.
Yes, sir. Definitely. And it's if it's biomagnification process is going on, that concentration of cadmium is enhancing that, directly damaging the metabolism of the human being.
Yeah.
Yes, sir.
Sandeep, I have a question.
Yes, sir.
So, so I was looking for a number, like after using the quantum dots, this was before and this was after growth in like harvest or whatever number. Do you have any idea how much it enhanced the productivity or anything in terms of number?
In terms of numbers, sir.
Yeah.
Sorry, sir. The data, just now I don't remember the data, that it's something is there, because only 10% energy is absorbed by the plants, rest of the is waste. And then once we enhancing the absorption of light, that directly influence the growth of the plant. But data is
Yeah, so yeah,
missed.
I get that point, but you enhance the absorption, like
Yes, yes, sir.
intake of the light, but how much it
How much it,
reflects to the
yes, yes.
total in the result,
Yes,
basically,
yes,
in
yes.
the intake magnitude.
Definitely, I'll, yes, sir. This is data is missed.
Sandeep, how it increase the crop yield actually? What is the mechanism behind that? How these nanoparticle increase the crop yield actually?
Sir, nanoparticle not directly increases the yield, just enhancing the rate of photosynthesis. Once the photosynthesis rate is enhancing, the growth and development of the plant is automatically enhanced. And the growth is,
No, it's okay. Then how it is enhancing the photosynthesis?
sir, in greenhouse shaded, if we use the different QDs films, so the absorption of the light is enhanced.
Why? In the case of, because in the there's a chlorophyll, right?
Yes, sir.
Why the chlorophyll absorption is enhanced?
Because, sir, chlorophyll has a restricted wavelength of the absorption of the light. But when we use the QDs, the wavelength of the light is increased. That's why they absorb the more light.
The wavelength of light increase means?
That means
So
visible
you are
spectrum.
okay, Dr. Sandeep, you are treating the polymer film of the greenhouse uh, with the quantum dots,
Yes, sir.
or you are directly spraying the quantum dot top on the crop.
No, sir. Different kinds of films are there.
Okay. So you are talking about selective wavelength selection.
Yes, sir. Selective wavelength selection.
Okay.
I couldn't understand how this quantum dots enhance the photosynthesis. Mechanism of for enhancing the photosynthesis by the nanoparticles, especially by this cadmium one, which you are studying.
Okay. Can I interrupt? Can I give some suggestion?
Yes, sir.
Okay.
Please,
Yeah,
sir.
yeah, yeah.
So there are studies that blue light is absorbing. Blue light is stimulating the growth of the crop.
Yes,
So
sir.
when you select when you coat the greenhouse film with some particles, and those particles are allowing only a specific wavelength towards the plant. So that particular wavelength will boost the photosynthesis process. So there are few studies going on in Singapore. They are doing such kind of thing. They, they are they have a completely blue greenhouse.
Okay,
So
sir.
they are using blue LEDs for this particular purpose, and they are studying to improve the yield of the crop.
Actually, I think you can correlate it with this the plasmonic effect, separate plasmons, because by due to separate plasmon the absorption enhances.
Yeah.
So when these
But
kind of chlorophyll molecules are near to the nanoparticles, their absorption will be enhances.
Okay, sir.
Yeah. But there is a cheaper way for the wavelength selection. Why?
Not only wavelength selection.
Because
If you have a sunlight, there is a huge number of wavelength, right?
no, yeah. So why to use
Mhm.
why to coat the polymer film with the quantum dots? And
No,
if
no, it's okay.
and
You coated the
and
film
and
by
if
the quantum.
yeah, so the problem is that if the rain comes and those quantum dots, for an example, cadmium sulfide, cadmium is a toxic material that will go to the
Definitely.
land, and that increase the toxicity of the
Toxicity. That's
soil, and
not only
that
soil. I think if the
soil as well as
nanoparticle
the
size are very
as well as
small,
the crop.
I mean, if the size of the nanoparticle is very small, they can go by mitochondria inside the
Yeah,
pores
yeah.
from the leaves from inside the plants.
It's a very
And they can
dangerous
move.
process.
Yeah. Yes.
Yeah, I think you need to look at some different process to for the specific wavelength selection
Yes.
to improve the yield of the crop rather than using toxic nanoparticle top on the greenhouse films.
Definitely, definitely.
Okay.
Okay, thank you, Sandeep.
Thank you, sir. Thank you very much. Thank you very much for your kind suggestions, sir.
Yeah.
Thank you, Sandeep. Now we are moving to our next presenter, Shrikant Devta. Actually, he is from USA, and he has requested due to different time zone to schedule his talk earlier. So, Shrikant, are you ready? You are not audible, Shrikant. Hello, Shrikant, you are not audible.
Unmuted.
Hello, Shrikant, you can start your presentation. Shrikant, please unmute yourself. Hello, sir. Neeraj sir, can we move to the next presentation? Shrikant? No.
You move ahead.
Okay, sir. We can move to the presentation of Rajesh Kumar. He was facing some technical issue. Now, Rajesh, are you ready with your presentation? Rajesh? Rajesh Kumar? Yes, I have unmuted you. I have unmuted you. Rajesh, I have unmuted you.
Okay, ma'am. Am I audible, ma'am?
Yes.
Okay. Good evening to everyone. I am Dr. Rajesh Kumar, and I am performing my research on environmental friendly approach for the adsorption of Rimazole brilliant blue dye from its aqueous solution using zirconium ferrite nanoparticle. Rimazole brilliant blue dye is an anthraquinone dye. It is non-biodegradable and it causes several health issues when it is used above its permissible limit. There are several methods have been already reported for the removal of these dyes. Some of them are chemical method, ion exchange method, reverse osmosis, membrane filtration, solvent extraction. But all these methods have some drawback like involvement of hazardous organic solvent, toxic byproduct, drastic reaction condition. So here we have used adsorption technique for the removal of these dyes. For this purpose, here I have synthesized mixed oxide nanoparticle because it possesses high adsorption capacity, high selectivity, high surface area, more active site than bulk material, high water insolubility, reusability, and eco-friendly in nature. So the synthesized nanoparticles are better adsorbent than other conventional adsorption. So these are the images of my lab experiment. Synthesis of zirconium ferrite nanoparticle were done using co-precipitation technique. In this technique, zirconium oxychloride octahydrate solution and iron chloride hexahydrate solution were mixed together with continuous string. After that, NaOH solution was added dropwise till the pH of the solution was reached to 10. It resulted in the formation of brown precipitate, which are kept in water bath for 24 hours. After that, wash and filter the solution with the help of Buckner funnel and dried the solution in an oven, and after that crushed and sieved the sample, and the prepared sample was subjected for characterization. These are the results of characterization. First one is XRD analysis. XRD confirms that the synthesized nanoparticle possesses two broad peaks, which shows its amorphous nature. Second one is SIME analysis. SIME report confirmed the agglomerated surface morphology, irregular shape, porous nature, and high surface area, whereas EDX analysis confirmed the presence of iron, zirconium, and oxygen element in the synthesized nanoparticle, where the ratio of zirconium and iron is found to be 70:30. The TAM analysis report confirmed the agglomeration and spherical particle size, and the particle was found in the range of 20 to 50 nanometer. And the BET analysis confirmed the surface area, which is around 392 meters square per gram, and pore volume were found to be 0.17 centimeter cube per gram, and mean pore diameter were found to be 6.07 nanometer. Next one is TGA analysis. TGA analysis confirmed nearly 20% weight loss at 100 degrees Celsius, 25% weight loss in the range of 200 to 600 degrees Celsius, and the weight loss around 100 degrees Celsius is likely to be attributed with the evaporation of water content. And zeta potential analysis confirms the isoelectric point, which is found to be 3.92. FTIR analysis confirmed the following peaks, which is around 4.42 is FeO ZR moiety, 540 is FeO moiety, 1346 confirm ZROH, and 1570 also confirm ZROH moiety, and 3414 confirm the stretching vibration of water molecules. These are the adsorption study. The toxic dye were adsorbed using bed adsorption technique. In this technique, the adsorbate, which is dye, was used in wide concentration range, which is 10 to 50 mg per liter, and optimum adsorbent dose were added. After that, mix the solution, and it was stirred in thermostat shaker water bath, and after that filter and centrifuge the solution, and the filtrate was subjected for UV visible analysis. These are the result of adsorption parameter. First one is adsorbent dose. Here we have found the optimum adsorbent dose is 0.03 gram per liter, and the optimum pH was found to be 5, and the optimum adsorbate concentration was found to be 10 mg per liter, and optimum content time was found to be 16 minutes. Here we have used 3 adsorption isotherm to analyze the adsorption technique. First one is Langmuir adsorption isotherm, second one is Friendlich adsorption isotherm, and third one is Temkin adsorption isotherm. These are the graph of this adsorption isotherm. Here we have found that the adsorption data shows best agreement with the Langmuir adsorption isotherm model rather than Friendlich and Temkin adsorption model. These are the conclusion of my research. First one is synthesized nanoparticles shows 86% adsorption of Ramazole brilliant blue R dye from aqueous solution under an optimized reaction condition, and the adsorption capacity was found to be 153.47 mg per gram. The adsorption mechanism followed Langmuir isotherm. Next one, furthermore, the study emphasized an environmental responsible and cost-effective technique of producing synthesized nanoparticle, which align with a larger commitment to sustainability. The green chemistry approach minimizes the use of hazardous chemicals and reduce environmental impact compared to traditional method. And the data suggested the synthesized nanoparticle is potent adsorbent with a wide range of application in solving water pollution challenges. And last one is further research could explore its performance under different environmental conditions and its scalability for commercial use. And last one is acknowledgement. I am thankful to organizing committee of this conference to give me the chance to present my work. I am also grateful to my supervisor, Dr. Sahraj Ali from Chemistry Department, DSB Campus, Nainital. I am also thankful to UGC New Delhi for providing me JRF and SRF fellowship. ISR Kolkata, IIT Roorkee, BHU Varanasi, IIP Dehradun, ARF, JNU, and Kumaon University Nainital and Bhimtal campus for providing instrumentation facility. I am also grateful to my family and my lab mates. These are the list of my publication which I have published during my research work. And thanks.
Thank you, Rajesh.
Yeah.
Thank you.
Yeah, Dr. Rajesh, I have one question. Can you go to the
Yes,
synthesis process of zirconia ferrite nanoparticles?
Okay,
So have you performed calcination at certain temperature in inert atmosphere?
Yes, sir. Before XRD, I have calcined the sample around 800 degrees Celsius. And
Okay.
after that, yes.
In inert atmosphere or in air atmosphere?
In inert atmosphere, sir.
Okay. So under tube furnace?
Then muffle furnace.
Muffle furnace, how you are purging the gas?
Sir, I have sent my sample to IIT Roorkee for that purpose.
Because muffle furnace is for you cannot use gases in muffle furnace. You require tubular furnace for to have an inert atmosphere. Okay.
Okay, sir. Okay.
Okay. So just can you briefly tell me about the mechanism how this dye is absorbed by this zirconia ferrite nanoparticles? Because
Sir,
the iron content is as I know, iron content is used to absorb used to have attraction with the dye nanoparticles, dye
yes, sir. Yes, sir.
particles.
Yes, sir. Sir,
And
yes, sir. Sir, zirconium ferrite nanoparticle were used as an adsorbent, and by using batch adsorption method, we have removed the Ramazol brain blue dye. And here we have used different concentration of zirconium and iron to compare the adsorption capacity, and we have found that when we increase the concentration of iron, then the adsorption percentage was increases.
okay, so these are these nanoparticles are porous or the solid
Yes,
one?
sir. Sir, these nanoparticles are porous in nature.
Porous in nature. Okay.
Okay.
Rajesh ji,
Yes,
can you
sir.
go in your diffraction slide?
Sorry, sir.
Diffraction spectrum, XRD.
XRD.
Okay. Yes, sir.
What is this? This is anomalous or crystalline?
Sir, amorphous.
Amorphous, but it shows
Sir, because here we have used the origin software to remove the noises of this graph.
But spectrum
No,
looks like the crystalline nature of the
if
compound.
Yes, sir. Spectrum looks like a crystalline in nature, but the prepared sample was amorphous in nature.
But why you remove that one? By
Sir,
this you cannot say this is a crystal amorphous.
yes, sir, because the reviewer asked me regarding that you can remove the noises of your XRD and clear the.
Okay. The second question, like the Langmuir plot, the last slide, before last slide.
Okay. This one?
Yes, how you say this is the Langmuir is the best one? Because
Sorry,
I
sir.
think Langmuir absorption isotherm is the best one. How you say that?
Yes, sir. Sir, because here we have found the regression coefficient which is around 0.999. Whereas in case of Fundich acetone which is around 0.97 and for Temkin acetone which is around 0.98. So we can say that it is found Langmuir acetone better than other conventional Fundich and Temkin acetone model.
Okay. What is the difference in these three?
Sir, Langmuir is a surface phenomena. The adsorbent molecule was adsorbed only on the surface of the molecule, whereas in Fundich is a multi-layer adsorptions.
Okay. And what about the Temkin?
Sir, Temkin basically is confirms the gaseous stage of the molecule also, which is I cannot explain easily, sir.
Okay, no problem.
Okay, Dr. Raish, one more question. This nanoparticle, they are reusable or not?
So it is reusable, and I have reused
Reusable.
the yes, sir.
How many cycles?
Sir, 5 cycles.
5 cycles. And cost of the production, how much it is?
Sir, it is cheaper than other
Approximate 10,000, 20,000.
No, sir. It is around less than 10,000.
Less than 10,000. So you can produce if your study is means it's up to the standard commercial one, then you can produce and you can sell you can sell those particles.
Yes, sir. Yes, sir. Sir, yes, sir. Thank you.
Because the research, if your research is not commercializing, then
Yes, sir.
if you are doing such kind of work, then I think you need to look at the commercialization of your work.
Yes, sir. Yes, sir. Sir, at first, I am looking forward to for patent, whereas I have submitted my proposal. After that, we get go through the commercial purpose for the job.
Okay, is that not necessary? Without patent, you can have your commercial one, and
Okay, sir.
simultaneously you can file the patent. That's
Okay,
not a
okay, okay,
problem.
sir. Okay, sir. Okay, thank you, sir. Thank you.
Okay, okay.
Let's move to the next presentation.
Yes, sir. Next presentation is of Mr. Aman Kumar and Anuj Kumar. Aman, are you ready?
Is Srikant there? Okay, okay. Let's go ahead with the notes.
Yes, ma'am.
हो गया यार
Jai to all. Thank you for this giving opportunity. My topic is about to study of structure and electronic property of peroxide compound. I will present my work under this content many-body system, many-body method, approximation by DFT, Wing 2K interface, and some results. Many-body system made of a large number of interactive particle, atomic, molecular, nuclear, condensed matter, biologic system, and many-body approximations consist of a two-type approach: wave function based method and density based method. And a little introduction of DFT. DFT is a very popular for the quantum mechanical multi-body problems. And 1998 award the Walter Cohen in chemistry won the Nobel Prize. And Wing2Gain written for the constant formation DFT using the FTLAW method, and thermodynamic property have been obtained by the software GIFT2K based on the quasi-harmonic device model. This is the first page of my software Wing2K. Result. We start the calculation. We need some input parameter: space group, lattice parameter, crystal structure, atomic position, structure property of a stable with compound with minimum energy and corresponding minimum volume. Electronic property, BALO3 conformation of the in spin of state in band gap is a 5.47 electrovolt, and spin down channel is a no band gap, and conformation of the density of state, total and partial density
You are not audible, Aman. Hello, Aman. Aman. Hello, Aman. You are not audible. So shall we go to the next slide? Till Aman is. Hello, Aman. Okay. Now I'm again inviting Shrikant Devta for presentation, as Aman is facing some technical issue. Shrikant, you can present your work.
Please unmute him.
Yeah, I have done it.
Hello,
Yes, you are audible.
am I audible now?
Yes.
Okay. Okay. So my screen is visible?
Yes.
Okay. So a very good evening to all of you. Thank you for staying so late to attend the talk. The title of my talk is Light-Driven Microrobots and Their Potential Application. I am Dr. Srikant Devta. Currently I am pursuing the postdoctorate in University of Delaware, USA. I have done my PhD from IIT Bhilai.
So I will now I will present my PhD work. So in this talk, I will discuss about the basic of micro robots, then their different design strategy and their potential application. Okay, so the idea of micro robot was first introduced in a movie screened in 1966, that is Fantastic Voyage. And so constructing micro robot involves drawing inspiration from the biological motor, particularly the autonomous propulsion of the protein motor, as we can see in the video, and their capability to transport the large vesicle particle through the hydrolysis of biological energy unit like ATP. So the first synthetic micro robot was designed as the molecular motor or nanocar, due to which 3 scientists got the Nobel Prize in year 2016. So there is a beautiful quotation of Sir Richard Feynman that there is a plenty of room at the bottom, indicating towards the opportunity lies in the micro and nanoscale object. So micro robot is a microscale cordless device which is designed to perform various tasks, and its size is very small. It's around 1/50 times the diameter of our human hair, and they are designed to perform multiple tasks ranging from the biological application to the environmental remediation. So I am skipping some of the part due to the time constraint. Okay, now we can see that a normal spherical particle can behave like a micro robot if it can break the local symmetry. It can break the symmetry locally. So that means if we will make a particle in such a way that if half side of the particle is chemically active and other half is inert, then it can break the it can break the chemical symmetry in the medium, and due to which only one part will take part in the reaction and other part will be inert, due to which a chemical gradient will form and the fluid will flow, as a result of which the particle will move. Okay, so this is the basic idea behind the propulsion of the micro robots. Now we can think of designing a micro robot which can be where we can trigger their chemical reaction depending upon the light condition. Means when we will turn on the light, the micro robot will perform the motion, and when we will switch off the light, the chemical activity will shut down and it will stop. So this is the motivation behind my study. Therefore, we have designed the light-driven system. For designing the light-driven system, initially we have used the commercially purchased silica microparticles. Then we broadcasted the silica microparticle over a silicon wafer. Then on the top of the silica particle, we have deposited the semiconductor material TiO2. And the SEM image and EDEX mapping shows the elemental distribution and confirm the asymmetric structure of the micro robots. Now, as you know that TiO2 is a photocatalytic material, is a semiconductor photocatalytic material, and the silica is a chemically inert. So when we shine on the light corresponding matching with the band gap of TiO2 material, it will generate the electron hole pair, which will participate in the chemical reaction with the surrounding medium, as a result of which a chemical gradient will form and particle will move. So the mechanism of propulsion is totally dependent upon the light condition. So as we can see in the plot, that when light was turned on, the micro robots are activated and move in all random direction. But when the light was turned off, it confined to a particular space and they did not move anywhere. After that, we optimize all the parameters associated with the micro robot to get the maximum speed, like the concentration of the fuel medium, photocatalytic layer, or the intensity of the UV light. After optimizing all the parameters, then we modify our micro robot with a thin layer coating of magnetic material nickel and some gold nanoparticle on top of it. I will discuss why we have done this. Then the modified micro robot are used for capturing and transportation application. In the first image, you can see that the micro robots are capable of capturing the multiple cargo particle, and they can transport them from one point to the another point. And due to the magnetic coating, when we apply the external magnetic field, the direction of propulsion can be guided. Means we can perform a guided transportation of the cargo particle. And in the second, it's a video. We can see that this is our micro robot Janus, which is a Janus shape structure, and when it's approaching near to the bacteria, it's capturing the bacteria. Actually, this white color rod-like structure are the E. coli bacteria, and so whenever the micro robots are approaching near to the bacteria, it's capturing the bacteria, and at the same time they are transporting them from one point to the another point. The reason behind capturing is can be understood through the classical DLBA theory, where the van der Waals for attraction is playing a major role in mediating this attraction. So this micro robot can be used for various biomedical applications. So in the next study, we have used the micro robot for sensing application, where we have used the silica microparticle. On top of it, we have coated the nickel TiO2 and one special dye, that is fluorescein. Fluorescein has an important property that its fluorescence behavior change with respect to the pH of the medium. Now our micro robot is dual optical responsive, means it performs the active swimming as well as fluorescence behavior depending upon the wavelength of the external light. Then then we perform a detailed study on the fluorescence behavior depending upon the pH of the medium by using a spectrometer. And as you can see that the micro robot is responding to the external pH of the medium. And after getting this confirmation, then we use our micro robot for on-demand local pH and sensing. And we have followed this scheme where we have created a source site by using a syringe pump, and a high pH was flown into the solution. Then the micro robots was activated by the external light medium. Then we guided their path by using the magnetic field to reach the exact position. After reaching the exact position, the micro robots detected the local pH change. And as you can see in the plot, that the micro robots are capable of detecting the local change in pH of the medium. So this study is very useful for biomedical point of view, because in cancer cell or tumor cell, they have different pH with respect to the normal healthy cell. So we can detect the cancer cell or the tumor cell at the early stage possible. Okay, so in summary, we have designed the light-driven micro robots. After designing, we have used them for micro manipulation, as well as we have used them as a pH sensor. So finally, I would like to acknowledge my supervisor, Dr. Dhruv Pratap Singh, with whom I have done all the work. He is currently an assistant professor, all my lab member, and the CIF facility and IIT Bhilai for giving me the opportunity. Thank you.
Hello.
Hello.
What is the mechanism of this? Why this movement is stopped when you are switch off the light?
Okay. Okay. So basically, the movement is due to diffusiophoresis. That means when we are shining the light, the TiO2 is producing the electron hole pairs, which is participating in the redox reaction with the surrounding fuel medium. So whenever we are switch off the light, then what will happen? Then the photocatalytic material will not produce the electron hole pair. That's why it will suddenly stop moving.
Okay. Okay.
Yeah.
Okay.
I have one question.
Yes, sure.
Are there any agricultural applications like pollination or pest control?
Mostly, yeah. I mean, some of the group are doing artificial, in agriculture or some pest control thing. But we are mostly working in the micro robots. Main purpose of doing micro robots is understanding the non-equilibrium dynamics or the behavior of, they're understanding their physics of the non-equilibrium system, as well as using them for various biomedical things, biomedical application due to their small size and as well as their external control, like this thing. So in agriculture, I think some of the groups are doing, but I don't have an extensive idea about it.
Did you use microwave to kill the bacteria, because when it is moving and capturing the bacteria or virus, whatever it is. So did you use microwave to kill the bacteria?
No, actually, we have not killed the bacteria in this study. What we have done that we have coated the gold nanoparticle on top of the micro robots. So what is happening when it is approaching near to the bacteria? It's just attaching the bacteria through van der Waals attraction. And
Okay.
yeah, if we will do the plasmonic effect, if we will shine the proper means laser light around 532 nanometer laser light, then it can do the photothermal effect and it can kill the bacteria.
Yeah, this is a very good idea actually.
Yeah, it can do. Yeah, we are planning on that. Yeah.
Yeah, it's very good.
So I have one more doubt I have.
Yeah, tell me.
Can you control its efficiency?
Efficiency in the sense, like yeah, means efficiency. If you will say the speed or their direction of, means for micro robots, the
Yeah.
efficiency is like mostly like their speed. Means yeah, we can control their speed either by changing the concentration of the fuel medium or the intensity of the light, or by changing the thickness of the photocatalytic layer. Okay, and to control their direction of movement, we have to use magnetic field to guide their motion.
And what is the role of this nickel layer?
Okay, actually nickel is a magnetic material. So when, as we can see in the image, as you were, that when we are turning on the magnetic field, we are providing a directional movement. Means we can steer their motion. The directional motion we can get by using the magnetic field. So the nickel is a magnetic material and it responds to the external magnetic field.
Okay, but it means you are not using that particle in this light activated motion.
No, that is not for light. For light, we are using the photocatalytic layer, and nickel is for magnetic control. So we are using light as well as magnetic control. Yeah.
Your photocatalytic is this TiO2 contains silver, right? Gold, right?
Yes. This is our means we have deposited TiO2 over the silica particle. So silica is normally chemically inert and TiO2 is active. Yeah.
Active. Okay. Yes.
Yeah.
Okay. Very good work. Very good work.
Thank you so much.
Are these micro robots used in within body also for diagnostic purpose?
Yeah, it can be used. Means it can be used for like drug delivery or something like killing the infected cell, or it can it can be done. Means transporting the drugs or invasive surgery. People are doing in this, and we are also trying to do this thing.
Means research is going on.
Yes,
Not
research is
confirmed.
going.
Means it is under research.
Some of the group have been reported that the micro robots can be used in mice, or they have performed various experiments in the mouse, because whenever you are planning to do it for mankind, you have to pass various experiments. So first you have to confirm in the lab, then you have to do different animal model, then only you can try it with human being. So yeah, it's means people are trying with like a mouse, and they have succeeded with the mouse.
And what is the size of the nanoparticle?
Actually, we are using the microparticle, and its size is around 2 micron.
Okay, microparticles. Okay.
Yes, yeah.
Size is very big, right?
Oh, we can reduce the size also. Means we can reduce the size, but for this work, I have used the 2 micron silica particle.
I understand.
Yeah.
Because working on the mice, it should be nano.
Yes, it should be nano, and but it should be
Microparticles being stuck. Yes.
Otherwise, what people do, they design various biodegradable type of stuff, which you will go inside, and it will not harm the life of the mice, like that.
Okay.
Yeah. So, do you have any question?
No, not from my side. Thank you.
Thank you.
Thank you, Shrikant. Our next
Thank you.
presenter is Deepak Chaudhary, Manendra Prashant Yadav, and Uptesh Verma. Deepak, are you ready? Deepak?
Good evening, everyone. Myself, Deepak Chaudhary from CCS University, Meerut. My work research is on the topic replacing lead with bismuth in halide perovskites. Halide perovskite.
Your slides are not visible. Deepak, your slides are not visible.
Yes, ma'am, I am trying. Halide perovskites. They represent a cation at the corner.
Yeah, it's visible right now.
Yes, visible.
My research is on the topic replacing lead with bismuth in halide perovskites. Halide perovskites. A represent the cation at the corner, B cation at the body center, whereas X represent halide at the face center. The Goldsmith tolerance T is calculated by this formula. If the value of T is greater than 0.9 and less than 1, then the structure will be cubic. If the value of T is greater than 0.7 and less than 0.9, then the structure will be tetragonal or rhombic. If value of T is less than 0.7 and T value greater than 1, then the structure will be non-perovskite. If value of T is greater than 1, then 2D layer structure. Halide perovskite materials have received a lot of attention in the photovoltaics due to their exceptional optoelectronic properties such as tunable band gap, high absorption coefficient, and long charge carrier diffusion length, which make them promising candidates in solar cell. However, concerns over load, lead toxicity constrain their widespread commercialization. The National Renewable Energy Laboratory data, the efficiency of the solar cell has reached up to 26%. Characteristics of halide perovskites. The characteristics are soluble, they are soluble, processable, easy synthesis, tunable band gap.
Proceed with your own results. You can focus on your results. That will be better. Okay, please go ahead.
Deepak, you're not audible. Deepak? Okay. Maybe he has found due to technical issues. Now we can move to our next presenters. Mr. Chop Singh, Arvind H. Jadhav. Chop Singh, Mr. Chop Singh.
Okay, Deepak is there. Let's check.
Yes, sir. Yes, sir. Actually, there are many participants, but they are not available. Like next is in line with Sapna. She's not. I think is Sapna there?
No, is Deepak there or he has left?
So, 1 minute, I will check again. So he has left.
Am I audible?
Yes, sir, you are audible. So he has left. Deepak has left.
Am I audible?
Yes, sir, you are audible.
Is Deepak there or he has left?
Sir, he has left. Maybe he has got some technical issue.
Okay, just put a message, okay, and move to next.
There in line, there are 3 presentations like Sapna, Rakesh and Tuiba Miraj, but they are not present there. So I am moving next to Mr. Chop Singh, Arvind and H. Jadhav. Mr. Chop Singh. He was there up till now.
Chetan Avasthi is there?
Yes, sir. I'm
Chetan
here.
Avasthi. Yes, sir.
Okay, I will present.
Yeah, go ahead.
Am I audible to everyone?
Yes.
Greetings to everyone. I'm Dr. Chetan Avasthi from Jamia Millia Islamia, New Delhi. I am here to present my work titled Unveiling the Potential of PDSA2 van der Waals heterostructure for Next Generation FATs. As we all know that electronic components are the backbone of today's technological advancements, and FAT, that is field effect transistor, is a fundamental component of that electronic item or a component. And the channel material is the channel material has a major role, which requires higher on current and higher mobility with a layer dependent features. But it is observed that single material cannot provide that kind of superior performance. But this problem has been solved by these researchers with the development of semiconductor heterostructures like by Alfred and Herbert Promer, for which they awarded the Nobel Prize in Physics in 2000, which as it revolutionized the high-speed electronics industry. And among all the heterostructures, two-dimensional heterostructures are promising because of their higher mobility, higher on-off ratio, and low turning current and lower leakage problems. So in this work, we have fabricated two distinct type of PDSA2 and MOSA2 heterostructures to the mechanical exfoliation and demonstrated their ability to modulate electrical response when applied electricity. So this figure shows the block diagram of the fabrication process involved, so which includes generally optical microscopy, taking alignment machine, and contact patterning for the electron beam lithography and thermal evaporator, which is going to, and lift-off processes. So we can see here, this is the optical microscope image of the fabricated device. So here we have used HBN, like hexagonal boron nitride, as a substrate to provide a cleaner and disorder or defect-free and flat surface. So we can see here there are 4 electrodes, 1, 2, 3, 4. So depending on this configuration, like 1, 2 is for a pure MOSA2, and 2 and 3 it is a heterostructures, and 3, 4 also heterostructures. But depending on the configuration, we have just divided. We are termed as a type 1 and type 2 heterostructure. So in this paper, we have just compared the MOSA2 response with the type 1 and type 2 heterostructure. So for this, we have confirmed the or characterized the material with the AFM and Raman. So from the atomic force microscopy, we have confirmed the thickness of the flakes like PDSA2 is 7.2 nanometer, MOSA2 is 6.3 nanometer, and hexagonal boron nitride is 8.5 nanometer. Then we have confirmed to the Raman spectroscopy and find these characteristic peaks. And then we have performed the electrical characteristics through these connections. We can see here 1, 2, 3, and 4. So we can see here, like we have done this, we have, because it is in MOSFET configuration, so we have done this at drain to source voltage at 1 volt and vary the backgate voltage from -60 to 6 volt. And then we can observe that like the black one is pure MOSA2. So type 1 heterostructures has a higher on-off ratio than the type 1 heterostructure has a on-off ratio in MOSA2. And type 2 heterostructure has a higher mobility and higher on ratio, which can also be confirmed through the output characteristics shown here. So, and we can see here, like this, from this graph, we can also conclude that electrons are the majority carriers here. So through the band diagram, we can see here the work function of that material. So we can conclude here that the electrons are transporting from the MOSE2 to PDSE2. And this is the comparison table of the comparison that compares electrical parameters. So we can see here, like in the type 1, heterogeneity is almost 2.5 times higher on-off ratio here. And while in type 2, we can see we got a higher mobility. So depending on the application or depending on desire, we can use any configuration. And further, we have compared our heterostructures with the other heterostructures formed. So we you can see here, this one, the blue one, I got a higher on-off ratio than the other materials. So in summary, I can say our findings support the dual strategy of the heterostructures for innovative design at the miniature scale. And for this work, I will thanks my supervisor, my collaborators of from Taiwan, my lab members and colleagues, and also technical assistants from Center for Nanoscience or AIRF JNU and UGC for providing me fellowship. Thank you.
One or two quick questions.
Yeah, you can ask.
Chetan, can you go in the Raman spectrum? Chetan, yes. So these are in crystalline nature, right?
Yes, it's a single crystal.
These are single crystal. And the third one is, so there is a layer in the black one is the lead selenide.
No, black one here is a palladium selenide.
Palladium selenide, sorry.
Yeah.
Yes. And the red one is the molybdenum selenide. And then there is a mixture.
Yeah.
In the mixture, the intensity decreases and some of the bands disappear of the molybdenum sulfide. Right? Is so?
Yeah. So here it is not disappear, but we can say it's a weakening. Because this is a pure material. And the laser Raman spectroscopy also depends on the depth of the material. We can say thickness of the material. So we can see here, like in the structure, here is the lower one is a boron nitrate, then MOSE2, then PDSE2. So for MOSE2, I use this area. For PDSE2, I use this area. But for heterostructure, I use the overlapping area, which is almost 6 to 12, like 14 nanometers. So it is more thicker. That's why it seems
So
like
palladium selenide is the uppermost layer, or
yeah, upper layer, palladium diselenide, black one.
Because the structure is changed actually related to this. The black one is the palladium, and the last one is the palladium plus molybdenum, right?
Black one is palladium. Red one is here in Raman's graph. Red one is molybdenum diselenide, and blue one is heterostructure, or we can say overlapping area.
And there is shifting also. The peaks are shifting. What do you mean by this? What does this indicate? The shifting of the what is this? Why there is peak shifting in the blue one? Blue one compared to the black one, the peaks are shifted.
The change in intensity also.
This intensity is because of the thickness. But actually I have measured, so I found that there is very, very negligible shifting because it is a van der Waals heterostructure. So there is a very less interaction between the layers.
But shifting is there. The shifting means some bonding takes place, right? Between the MOS2 and the palladium selenium.
Yes, sir.
So it might be some interactions takes place. There's for frequency shifting.
Yeah, but sir, actual interaction is very less.
Are the interaction less in this MOSE2 or lead? Sorry,
Palladium.
PD palladium. Yeah, it is the less. It is less interaction.
Yes.
If interaction is less, then the peak should not be shifted. If it is strong, then only it will be shifted. And intensity.
Actually, I measured it I have not mentioned here, but actually it is published. So I measured there is a very less shifting, like maybe in the 0.02 centimeter per inverse only.
Shifting is very less?
Yeah, very less. Or we can say there is no shifting in the peaks.
Look,
that confirms
look, 250 wave number signal is disappear in this Blue line. The
Right,
200,
this one.
the 250 nanometer signal near this, sorry, this one, the black line, and you are getting the two sharp signals in the blue one.
Just
Near to
could you speak
250
loud,
number.
like, yeah, sorry.
250.
Yeah,
It's a huge
yeah,
difference.
Chetan, I have one question.
Yes.
One.
How much controllable this process are? What's
Sir, actually, this process is very controlled. Like the first step is crucial here. You can say this because this is a mechanical exfoliation. So first we are, scotching, or we can exfoliating from the bulk. So this step is very crucial, and after that, every process is very controlled. But this is very, it is very hard. Like, or we can say, I can say, like, if I exfoliate like 10 to 20 flakes, then I'll got a mono layer or a 5-4 layer out of 1, 2 out of 10, or 3 out of 10 only.
Okay. So it's a mechanical exfoliation.
Yes.
If you do CVD or molecular beam epitaxy
yes,
to develop this material,
yes,
in that condition, how much it will be controllable as compared to your existing process?
Sir, if I will just compare with this result or this experiment, so the main, the main controlling parameter is the synthesis. If I'll synthesize, so I need to control the synthesis of CVD.
Yeah.
Sorry, control the process of CVD. Yeah, but
CVD
sir,
or epitaxial process.
yeah.
The thing is that the exfoliation process, you will not get the uniform size of the flakes.
Yes.
And the thickness is also not controllable. That's the major issue, and there will be a defect while when you are peeling out the material from a bulk structure. So there is a structural defect that will for any electronic device, that's the major issue, structural defect. So how you can control?
Sir, actually, in our experiences or from the literature, mechanical for testing, generally people prefers mechanical exfoliation because as compared to CVD or other synthesis procedure, mechanical exfoliated flakes have a lesser defects because it's just peeling of the layers. But in CVD and other methods, there are too much chemicals. There may be too much contamination. That's why we got a very low mobility in CVD samples as compared to these.
That's the standard process, but if you go for the continuous production of such kind of devices, then you need to have a very controlled process. Because you have done this experiment, so I think you might know graphene first paper by Andrigem and Navas. Yeah, so they just peeled off from the HOPG, and they have performed the electrical conductivity measurement. But that is not feasible for
large scale production. Yeah,
large scale production or for device application. For R&D, for in the lab application, it is okay.
Yeah, R&D is okay.
For publishing paper, it is okay. The Bell Lab and the Intel, they are trying to find out the process for utilizing graphene or carbon nanoribbons.
Silicon nitride also.
Silicon nitride. So to utilize to make large devices, and they are struggling a lot.
Yes, sir, I agree. Yeah, but through mechanical exfoliation, we cannot go to large scale production. Yeah.
Okay. So have you any idea in your mind that you can, the research you have done, you can utilize in a different way? Because in India, I think we are going to establish a semiconductor industry.
Sir, we can we can make this type of microstructures like MOST2 and PDST2 sputtering also, or PLD also. Yeah. but there should be less lattice. There should be less lattice mismatch. But the problem is, for research purpose, we got a very lower performance in other like sputtering methods. But it is possible. So we need to, it will take, at least my experience, it will take a lot of time to optimize these fabrication process, especially.
Because Chennai, the government are establishing the semiconductor industry.
Yes, yes.
And there is a few company, those are developing chips. So they are also looking for scaling up their production line.
Yes,
And
yes.
they are trying to find out a better solution, because all are they are using silicon as a source material to make chips. And the silicon technology is okay. Let it be. I think your work is good. You need to do little bit more to go to the industry.
Yes, sir. I will do. Yeah. So for industrial, we need to go to PLD and sputtering.
Yeah. Okay.
Chetan, one just quick question. Just one thing I need to ask is that you made this heterostructure with by using just mechanical exploration, right? First you mechanical exploration of MoSE2 and then randomly just PDSE2, right?
Yes, yes.
Okay, great then.
Thank you, Chetan. Is there anybody left in the audience who have to present their work? They can raise their hand. So with this, I want to thank all of you for being with us till this late. Actually, it is 12:44 a.m. in the night and still there are 23 participants in the Zoom. So this is really very encouraging. The main motivation of organizing this event was to unite eminent people from all spheres of physics, researchers, faculty members, and students, and we tried our best to make it possible. On behalf of the organizing committee of the conference, I would like to thank all of the eminent speakers of all 3 days for coming to this gathering and enlightening us with their knowledge. I would also like to thank all the presenters from various institutions who gave their presentation. I would like to thank our college principal, Professor U.P. Singh, for his encouragement in organizing this conference. Many thanks to the Director of Self-Finance Group, Dr. Sarita Sharma, for being a big support. My heartfelt thanks to Dr. Neeraj Tiwari sir for conceiving the idea of this conference and giving us this opportunity to deliver our best. I would also like to thank the entire organizing committee team, Dr. Jaya Singh, Dr. Deepa Verma, Ms. Aratna Jain, Mr. Deepak Kumar, and Mr. Bhupendra Kumar for tirelessly working daily for this conference. Many thanks to student volunteer team and special thanks to Ayush Dubey from BSc 4SEM for making all the creatives we used during the conference. I also want to thank other faculty members of our college for their consistent support. I again want to thank all the students of our college for being the big support during all these 3 days. Thank you, students. And I am also a part of IYNS, that is Indian Youth Nuclear Society, who has jointly organized this conference. And for this, I want to thank Dr. Nitin Singh and Dr. Samyak for being a consistent support. And special thanks to Mr. Khanjan Joshi, PhD scholar from IIT Delhi and IYNS member, for consistently helping me technically during all these 3 days. Thank you all. Now I invite Dr. Nitin Singh, President IYNS, to say his few words and share his.
Thank
you, Sapna.
Thank you. Open their, just a minute of interruption. Videos so that
I won't
quick
take
picture.
much of our time. It's
Sorry, sir,
already
I
too late.
forgot
But
to open my
no,
video.
I just wanted to say a couple of things, mainly for students. Maybe you can convey later, not now. That when they are presenting, they should also start very beginning with the idea of what is the big picture. what is the role their research is basically contributing to at a large, whether it's the society, whether it's the country or a world or a population, whatever. That gives you the confidence and way forward and importance of your work, which is really important to understand. And secondly, they should also focus on the current cutting edge technology or research global sense, so that they can actually figure out where they can lead in future. So it was a great journey. I enjoyed all 3 days. I enjoyed all the presentations, a different kind of material, all of it. It was nice to reconnect back to physics after a long time. And one thing which I would like to say kudos to the organizing team, that they made a balance of gender parity during the speakers' time, which is really not an easy task, which is really a commendable job. So thank you very much. Thank you to all the people who are involved, and all the very best. And we will continue to collaborate further. Importantly, to mention that IYNS is working towards encouraging students of all levels and various sectors to connect with the industry, global institutions to grow further. So happy to connect whenever you want. All the very best and a very good night.
Yes.
Thank you, Nitin, and all the IYNS team. Samyak, Anjan, Sapna.
Thank you, sir.
Great
Yeah, I'm
pleasure.
also part of Lajpat College also.
And Dr. Sachin, Neeraj, Deepa ma'am, Chetan.
And I invite all of you to
and our
ITER.
judges.
Yeah.
Yeah, thank you so much. And all the participants. Thank you and very good night. Hope we meet again.
Yes.
Soon.
Soon.
In another endeavor.
And this is really an international conference.
This is also
During the
there.
night time, and very good. It's a very good way of interacting in a very simple way, in a relaxed mood. We all are interacting and sharing our ideas.
With
Yes.
limited resources and yeah.
No, it's a
The
nice
conference should be like that. Otherwise, we are wasting our time in moving here and there, flight
Conserving the
and
resources. Yeah.
yes. And this is a good use of the resources. Yes.
It's a low carbon
Thank
emission
you, Dheeraj bhai.
conference.
Yeah.
Thank you.
Thank you, Tiwari ji. Thank you, everyone. Thank you for organizing this
Thank
wonderful
you.
event.
Thank you
It
for
I
was
already
good.
sent the comment, the marks to you, Tiwari ji.
Yeah, you take your own time. Yeah.
I sent.